नहीं वीडियो तो चल रहा है। नहीं हम जा रहे हैं, ये क्या है सर जी। हाँ सर, तो वीडियो उसी में पूछ रहा हूँ, क्यों नहीं आ रहा वीडियो? आता है वहाँ पे? हाँ आता है, तो मुझे सर का वीडियो क्यों नहीं आ रहा? जी जी इसको ये क्या है? तो एक जगह तुमने वर्ड में देख रहा था कोर्स कन्वीनर और कोर्स को examples are quantum crystal systems which provide guaranteed secure communication and quantum computers that is manipulated by quantum mechanically and will solve some problems currently intractable conventional computations. You're right. Fluorescent biological compass. कंपास बोलते हैं, कंपास तो वो भी तो चेंज हो गया है। हाँ उससे तो मतलब जो आप सर सर कैमरा ऑन है? मैं क्या ये ऐसा तो हमारा नहीं होता, सब कुछ दिखा भी रहा, आप लोग की फोटो तो सब आ रही है, हमारा नहीं आ रहा है। हाँ सर, वो हम लोग का भी जो है वीडियो हमको खुद ले गया है, इसलिए तो मैंने कहा चेक करा दी पहले, वीडियो ले मेरा पता नहीं क्यों नहीं ले रहा। अच्छा चलिए देखता हूँ क्या होता है।
द्विवेदी सर जी सर हमको बता दीजिएगा व्हेन आई हैव टू स्टार्ट द प्रोग्राम। ठीक है, अभी थोड़ा सेक्रेटरी सर को प्रॉब्लम हो रहा है, वो अभी उनका वीडियो नहीं हो पा रहा है, प्रॉब्लम है इश्यूज है। ओके सर, अभी एक बार सेटल हो जाए। ओके सर।
स्टार्टिंग दिखा रहा है।
गुड मॉर्निंग सर। गुड मॉर्निंग।
इसी चलता है। अभी क्यों ले रहा है अंदर?
नमस्कार सबीना मैम।
नमस्कार सर। गुड मॉर्निंग सर।
नमस्कार मैडम। गुड मॉर्निंग सबीना मैम।
गुड मॉर्निंग सर।
Good morning, Dr. Dwivedi.
Good morning sir. Good morning sir.
I'm available now.
Okay sir. Okay sir. Good morning sir. Now we can see you sir.
Good morning. I have joined by cell phone. There was some problem in the laptop.
Good morning sir.
Good morning.
Good morning. So let Professor Anuradha Misra also join, then we will start the program.
Okay. Professor Dwivedi, is there any camera off from your side?
No sir, not from my side.
Because whenever I am switching on, then it's getting off automatically.
Okay, I will check from
होने लगा है.
I think my camera is also on from your side.
Okay, I'll just check sir.
ठीक है Have it on.
Good morning, ma'am. Namaskar, मैं आरके द्विवेदी. Professor Pathak, could we start now?
Yes, we can.
Dr. Satyaprakash Singh.
Okay, sir. I'll start with the proceedings. Okay. Okay, sir. I'll start. A very good morning to all of you. Am I audible to everyone?
Yes.
Okay. Most respected Honorable Secretary, College Governing Body, Reverend S.P. Lal, respected Principal Dr. Joseph Daniel, distinguished Chief Guest Professor H.S. Mani, FNA, FNASc, CMI Chennai, guests of honor Dr. Anirban Pathak, FNASc, JIIT Noida, and Dr. Anuradha Misra from University of Mumbai, Head of the Department of Physics, Dr. R.K. Dwivedi, all my dear colleagues, distinguished delegates, and my dear students. I, Dr. S.P. Singh, on behalf of the organizing committee and on my own behalf, welcome you all to the inaugural function of the Science Academies virtual lecture workshop on Elements of Quantum Information, organized by Department of Physics, Christ College Kanpur, and sponsored by Indian Academy of Sciences, Bangalore, Indian National Science Academy, New Delhi, and the National Academy of Sciences, India, Prayagraj, from March 12 to 14, 2021. Prayer is an action. It is the process of talking with God with energy in order to achieve a purpose. So let us begin this inaugural ceremony by seeking the blessings of the Lord Almighty with a prayer. I now request Dr. Sabina Bodha for the word of prayer. Sabina, ma'am.
Thank you, Dr. Satyaprakash. Now we bow our heads or start the program. Dear Heavenly Father, thank you for this opportunity that gather attend the inaugural function of this seminar. We start the seminar on great presence. We are also seeking your grace and your blessings upon this seminar. And we pray that whatever knowledge we gain from this seminar will help us to benefit our society
Joseph Daniel, invited guest, distinguished participants of the workshop, friends, ladies and gentlemen. First of all, I take great opportunity to welcome you all to the inaugural session of Science Academies virtual lecture workshop on elements of quantum information, which is being organized by our department from today till 14th of March 2021. Our college, Christ College, Kanpur, established in 1866, is the oldest college of the city, carrying a historic heritage of supreme educational service and standards. The college began as an SPG mission school in 1840 to educate Christian children and those who choose it. First called missionary school, then Christchurch school, it grew into a college affiliated first to Calcutta University in 1866, then to Allahabad University in 1892, later to Agra University in 1927, and last to the Kanpur University, which is now known as Chhatrapati Shahuji Maharaj University. Now, it's a minority co-education college of Church of North India Agra Diocese, managed by Christ College Society, Kanpur. The college has the Faculty of Arts, Science, and Commerce, BCom, MA, MSc, MCom, and PhD degree of Chhatrapati Shahuji Maharaj University, Kanpur. The Department of Physics is first sponsored, that is Department of Science and Technology sponsored first department. The short duration lecture workshop are an important segment of the activities of Science Academies, Indian Academy of Science Bengaluru, Indian National Science Academy New Delhi, and the Indian National Academy of Sciences in India Prayagraj. The primary focus is to enhance the quality of science education at graduate and postgraduate level in our country. These lecture workshops are primarily aimed at helping our postgraduate students to know about the frontier area of research and providing them a platform to have interaction with renowned experts and teachers to add value in their teaching. Friends, quantum mechanics is one of the most fascinating subjects to study. If you go into the history, it evolved during the first quarter of 20th century to understand the behavior of physical systems on the atomic scale, the atoms, the molecule, and their emission spectra, as classical mechanics governed by Newton's law of motion was found to be inadequate to understand the atomic dynamics and the spectra. Planck's law in 1900, Einstein's photoelectric effect in 1905, Bohr's model in 1913, matter waves and wave nature duality in 1924, for which 2 Nobel Prizes were awarded, one for the discovery of matter waves to Louis de Broglie and other to Davison and Germer for experimental verification of matter waves. Not only this, Heisenberg's uncertainty principle and the discovery of quantum mechanics itself were awarded 2 Nobel Prizes, one to Heisenberg and the other to Schrödinger. And you will recall that photoelectric effect, black body radiation, Compton effect, emission of line spectra that could be explained by the quantum physics only. There have been many fascinating discoveries since then. If we talk about the applications, you are all familiar with quantum mechanical tunneling, quantum Hall effect, quantum confinement in narrow systems, and standing tunneling microscope, because these are the very common terms that every postgraduate student is familiar. Quantum mechanical tunneling is being used in electronics like tunnel diode, lasers, optoelectronic devices, etc. The fractional quantum Hall effect is a topological ordered state corresponding to a long-range quantum entanglement. Standing tunneling microscope is used for imaging the surface at the atomic level. Coming to the early emerging applications, we now have quantum chemistry, quantum optics, quantum computing, quantum cryptography, superconducting magnetic, etc. Quantum computers are expected to perform computational tasks much faster than the classical computer. The binary bit 0 and 1 of classical computer are replaced by quantum bit, are known as qubit, which are made up of using physical systems such as spin of electron or orientation of photons, etc. We are all familiar with Google and IBM over quantum computer supremacy. Quantum teleportation is a technique to transmit quantum information over arbitrary distance. Quantum cryptography allows secure transmission of information. All these applications have revolutionized the development of science today. We are fortunate enough that we will be enjoying many of these applications in the post-lunch session daily for the coming 3 days. This workshop will be conducted by renowned teacher and researcher Professor along with experienced and renowned resource persons all over the country. Professor Anirban Pathak, Jaypee, Noida, Professor Anuradha, Misra from University of Mumbai, Professor Singh from Academies, Professor Singh from ISC Bangalore, Professor Raghavan from TIF Mumbai. Each day will have a series of lectures of 75 minutes duration with two pre-lunch devoted to the basics of quantum mechanics and two in the post-lunch on exciting applications of quantum mechanics. There will be a special lecture that will also be delivered by Professor Anuradha, Director CSIR Chandigarh. This workshop I am giving the complete knowledge of basics of quantum mechanics along with the essence of recent advancement in the wonderful exciting of quantum communication. The coming 3 days are giving all of us a lot of information in this area. This workshop gives a great opportunity for all teacher friends and my dear student participants to learn several new things. Thank you very much.
Thank you, sir. I feel very privileged to invite our dynamic principal, Dr. Joseph Daniel, for his invaluable address on the occasion. Principal, sir.
Thank you. Respected Jaypee Lal, the Secretary for the Governing Body, distinguished guests, dear colleagues, friends, students, and participants. Good morning and welcome to the inaugural session of the virtual lecture series on elements of quantum information, organized by Physics Department of Sciences College in collaboration with Indian Academy of Science, Bangalore, Indian National Science Academy, New Delhi, and National Academy of Science, India, Prayagraj. First of all, I would like to congratulate the entire team of Physics Department for organizing this virtual 3-day lecture series on topic elements of the quantum mechanics. As a student of chemistry, I am a little bit familiar about quantum mechanics because we used to study quantum theory to define atoms and molecules. Quantum theory describes basically the nature and behavior of matter and energy on an atomic and subatomic level, which gives a better picture of the rule of the universe in smaller scale. Classical theory fails to explain the existence of particles in more than one place or more than one state of being simultaneously. This is the essence of the modeling of atom. These are really in terms of classical theory or mechanics, but true as per quantum theory. This is true that very small particles and light behave differently from objects we encounter in normal life. The first quantum assumption appeared at the beginning of the century, put forward by the Nobel laureate Max Planck, quanta as an individual unit of energy. This electromagnetic radiation energy was defined as this unit called quanta. The wave particle duality put forward by Louis D. Broglie in another way, particle wave physicist could explain the state of an electron in an atomic model or a hidden atom proposed by Niels Bohr. The assumption of angular momentum as a multiple of h by 2 pi, a quantum assumption, is used to explain the energy state of a hidden atom. The Heisenberg theory is uncertainty in the precise and simultaneous measurement of two complementary properties of moving particles like electrons is correlated to classical theory. Incorporating the Schrödinger wave equation, the atomic model was developed which could explain most of the properties of atomic particles. Thus, and Academies defined as a very large in size compared to its nucleus. And atomic mass is concentrated on a small area of the atom, that is nucleus. The behavior of matter and energy at the subatomic level is still different. To explore the structure of matter at the shortest distance and the highest energies, the Large Hadron Collider LHC experiment was carried out in 2009 and found that a total of 59 new particles in addition to Higgs boson were discovered. Here arise many fundamental queries, like what force holds these nucleons together at the nucleus, and why protons are charged whereas neutrons are neutral, even though both are shy quarks. Why neutrons are captured by the nucleus, how neutrons are changing into protons, what happens if quark is removed, one quark is removed from the neutron or the proton. So there are many questions more coming. Quantum chromodynamics says quarks are electrons, quarks and electrons are the two building blocks of matter. The LHC has discovered 59 new hadrons, and with each new hadron discovery, we improve our knowledge of nature's law, leading to the better description of the most fundamental properties of matter. The co-ordinator wrote us the information is which is disruptive technologies of transistors, lattice, superconductivity, and above all, the nuclear power. There are many more applications of quantum mechanics or quantum theory to come. This opens up an entirely new area of possibilities in science, technology, and information processing. Two such most promising, as per my understanding, applications of this theory are quantum computing and quantum cryptography. The quantum computer manipulates the quantum state of qubits in a controlled way to perform algorithms. The fact that qubits can be entangled makes a quantum computer more powerful than classical computers. With the information stored in superposition, some problems can be solved exponentially faster. Similarly, quantum cryptography uses the principles of quantum mechanics to encrypt data and make it virtually unhackable. The concept of quantum key distribution makes it impossible to forward or copy of the key without being detected. These applications are, as per my understanding, the infinite state, and many more applications are yet to come. Today we have with us a galaxy of eminent speakers to discuss in detail these aspects of quantum mechanics, the theory, and its present and future application. On behalf of the entire science community, I welcome each one of you to the Friday lecture series on application of quantum mechanics. Thank you, and over to Prof. today.
Thank you, sir. The incredible leadership, timely and proper advice, and the freedom in decision making provided by you has been indispensable for us in organizing such academic activities in the past. Thank you, sir. Our chief guest, Professor H.S. Mani, was supposed to be available with us this morning, but due to some reasons, in fact, his wife has been admitted in a hospital due to COVID, and he is also under watch. He could not spare time for this inaugural program, but he has sent his message, and I request Dr. Anirban sir to read out the same for us. Dr. Anirban sir.
Yes, thank you, Professor Singh. So, Professor Mani was integral part of this planning of this coursework from the beginning. As director of this course, means he was part of every discussion and choosing the faculty members, planning the course, means which one will be taught first, which one will be taught later, and so. Although he is not physically present, everywhere his presence will be reflected. So I wish that he would have been present here, but he asked me to read his message, and I am doing that. The Honorable Secretary of the Board of Governors, Reverend S.P. Paul, esteemed Principal, Christ Church College, Dr. K. Daniel, Dr. Misra, Dr. Pathak, Dr. Dwivedi, Dr. Singh and respected participants. First, I apologize in not being present in the inaugural ceremony of the workshop. It is beyond my control. I welcome all of you to the 3-day workshop on elements of quantum information sponsored by the 3 academies, namely the Indian Academy of Sciences, Indian National Science Academy, and National Academy of Sciences, India, Prayagraj. As physics teachers, it is one of our important duties to constantly update our knowledge and communicate them to the students. Such workshops are being conducted to help us in attaining this aim. Quantum information is certainly a very important area, and already many institutions are updating it. Here we have 2 faculty members, Anuradha and Anirban, who have been constantly updating the syllabus of their respective institutions, namely University of Mumbai and Jaypee Noida. They are experienced teachers, and I am sure you will be richly rewarded by listening to them. We also have some lab sessions. Dr. C.V. Chandrasekhar, who will demonstrate quantum simulations. Dr. Vijay Raghavan will tell us how quantum computers are built. Aditi Dev will give a talk on quantum communication. And finally, Dr. Ananta Ramakrishna will talk on metamaterials. All of them are recognized experts of the field. Let us all use this opportunity to update our knowledge and enrich our undergraduate and graduate programs.
Thank you, Dr. Sir, for the message. It is a proud moment for all of us to have Dr. Anirban Pathak as guest of honor. Dr. Pathak is a fellow of the National Academy of Sciences, India, FNASc, Institute of Electronics and Telecommunication Engineering, IETE, and Optical Society of India. And at present, he is a professor of physics at Jaypee Institute of Information Technology in Noida. I cordially invite you, sir, to address us on this occasion. Dr. Pathak, sir.
Sir, it's a pleasure to be present in this inaugural program, and especially when the program is organized by all 3 science academies of India and a college which is one of the first colleges in India. It's established in 1966. Means hardly there were colleges at that time, and it's constantly teaching and encouraging the students, producing so many good students. I know few of them who are involved in research, who are graduated from Christchurch College. So it's a pleasure to join in that program, and I believe that those who are present in this some of them will also become bright researchers in future, especially the students. So regarding the academies, somehow India has 3 science academies. The first one was established in then Allahabad by Meghnad Shah, and that's National Academy of Sciences in India. And then, for some reason, Professor Raman started another academy in Bangalore, which is Indian Academy of Science, and later on, with the effort of Meghnad Shah, INSA was established. But all 3 academies are functional, they work in coordination, and there are division of work in which sector. But main motto is to promotion of science. And one most important thing in promotion of science is to teach teachers, and then teachers can dissipate that among the students. So this kind of workshops are often arranged where teachers and students both participate, and especially NASI organizes many such workshops, and there is even a book edited by me and Professor Pathak, which accumulated the lectures delivered at NASI workshops on quantum mechanics. And so the idea is that to make the part of the lectures will be on the coursework kind of thing. So normally the morning lectures or the pre-lunch lectures of this particular workshop is designed in such a way that pre-lunch lectures will be the conventional quantum mechanics, which will create the foundation and the background, and then in the post-lunch we will mostly talk about applications. And the applications will primarily move around quantum information. And then in the Academies program, there was a provision when the program was physical and physics lab. Since the lab could not be arranged in this mode, virtual mode, so we have tried to make a kind of virtual lab. So keeping that in mind, Professor Vijay Raghavan, who is an experimentalist who is in an effort to make superconducting quantum computer, somewhat analogous to the quantum computer available in IBM in DIFR. So he will show part of his lab and give a lecture on how to build a quantum computer. So that will be your exposure to lab, but not really visiting the lab. CM Chandrasekhar will talk about quantum simulation, and he will show how IBM quantum computer and such quantum computers can be used even from your mobile phone to do quantum computing. So a kind of exposure of lab will also be given, and I will also try in my lecture to give, especially in the second lecture, that how quantum cryptography is done in the lab, to give you some exposure. But the other two lectures, like today's lectures of mine, and will create a framework for tomorrow's lecture so that you can understand it easily. And all these lectures will also be focused on the theory part, but second half will all be on application. So this is in mind. And then regarding the questions, don't wait for the end. In between, we will ask you, give some windows to ask questions, and you can ask questions in that. Or you can raise hands, write in the chat box, and even those who are listening it in YouTube, they can post questions as comment on the chat room in the YouTube, and those questions will also be answered. So we'll try to answer all the questions, but just don't start asking questions in the middle. If you have a question, wait till it is asked to ask the questions, or just write in the chat room. Okay. So there is a special reason for organizing this kind of workshops, and as one of the previous speakers told, that the national mission on quantum technology and applications will be launched soon. Already we have a program called QuEST, Quantum Enhanced Science and Technology, and now, as a member of drafting committee, we have prepared a DPR, detailed project report for national mission on quantum technology and application, and it will be launched very soon. And there will be various centers, and especially those who are from Kanpur. IIT Kanpur is an active center in quantum computing, and you can have internship, exposure to experiments, and many things in IIT Kanpur. And there are many other centers in UP, including HRI in Allahabad, and you will have gradually exposure to do this during when the speakers talk about their work and things like that. So I believe that it will be a nice exposure, and I also want to tell you that not only that post-second quantum revolution, which we are now will discuss, that quantum things come in your life, even today's computer you use with semiconductor, and semiconductor has band gap, and band gap means that energy is discrete. The word discrete means quantum. Unless there was, if it is classical, every energy was allowed, there was no semiconductor, no transistor, no iPhone, no mobile phone, no Zoom meeting. So our life is governed by quantum mechanics, but those are effect of the transistors are effect of the fast quantum revolution. But most of the second half we will see about the effect of second quantum revolution. But to understand that, it's fundamentally important to understand the foundation. And the greatest effort in this workshop will be taken by Professor Misra, who will give 6 lectures and create those foundations. So I hope you will enjoy, and the discussion will not end here. Means post-workshop also will get some questions, mails, and with the interested participant we will share our mails, and if you have questions you can ask it later also. So this workshop is planned for a while. Professor Mani, Professor Dwivedi, and Professor Misra and I spoke a lot. We discussed many things and planned it accordingly. So keeping this in mind, we hope that it will be a nice workshop, and I thank Professor Dwivedi and all the other members of his institute, including Professor Daniel, Professor Paul, Professor Singh, for organizing this, and all the participants for accepting the invitation and joining in the program. Thank you.
Thank you, sir, for your informative speech. It is a matter of proud privilege for all of us to have Dr. Anuradha Misra as guest of honor. Dr. Anuradha Misra is the professor and head of the Department of Physics at the University of Mumbai. I cordially invite you, ma'am, to address the gathering present over here.
You are muted.
So, dear Reverend Lal, Dr. Daniel, Dr. Pathak, Dr. Dwivedi, Dr. Singh, and all the dear participants of the lecture workshop, a very good morning to all of you. It's indeed a pleasure to be attending this workshop at Christchurch College, Kanpur. Kanpur has a very special place in my life because I did my MSc and PhD from IIT Kanpur, and I have been taught by Professor Mani, about whom people just mentioned. And it's indeed a pleasure to have been discussing with him and to deliver these lectures under his tutelage once again. I would like to congratulate the management of Christchurch College for organizing such an important meeting, because this kind of meeting in these difficult times are really very welcome change from the routine life, and they provide the motivation to keep on working in a positive sense. Science academies have been doing a wonderful job of providing support for such meetings. I have myself organized several workshops for teachers under Science Academies program, and Professor Mani has been very kind to be a teacher for those programs. That was some time back. And many of the Bombay teachers have benefited from these workshops. The topic of today's workshop is very relevant, as have been mentioned by people before me. Quantum information, quantum cryptography, quantum computers, these are all going to play a very major role in the next couple of decades. This is the age of data science, and data science is going to play a very important role in medicine, in climate research, etc. In fact, in all of our societal needs, we will be using data science in a big way. So, and our nation has a lot to catch up in this area. So I hope workshops like this, in particular the efforts of Dr. Dwivedi, Dr. Singh, and Professor Mani, will encourage many of you to enter this field, organize similar workshops, and educate your students also about these topics. Once again, I thank Dr. Dwivedi very much for giving me this invitation. And I look forward to the lectures. I'll be giving the formal part, the basics of quantum mechanics, and many of you are familiar with this. I hope you get something new from my lectures. Thank you.
Thank you, ma'am. Thank you very much for your valuable information. It is indeed a matter of pride for all of us that Reverend S.P. Lal, Secretary College Governing Body, who despite his very pressing engagements, has kindly accepted our invitation for presiding over the inaugural ceremony. I invite you, sir, to deliver the valuable presidential address. Secretary, sir.
A very good morning to all present here. On behalf of the Christchurch College family, Kanpur, I would like to extend a very warm welcome to our chief guest of the workshop, Professor H.S. Mani, course director, the guest of honor, Professor Anirban Pathak and Professor Anuradha Misra. It's very unfortunate that Dr. Mani could not be with us this morning due to her wife's illness. We pray to God for his healing touch upon Mrs. Mani and for her quick recovery. I would also like to appreciate the efforts of our college faculties, especially to our principal, Dr. Joseph Daniel, Dr. Rajesh Kumar Dwivedi, the head of the physics department and course convener, Dr. Satyaprakash Singh, course co-convener, for organizing such a relevant and fruitful workshop for the understanding of future technology. As per my reading and knowledge, what I understand about quantum information is that the quantum information system is a startup for a most successful information technology in coordination with physical sciences and its application. I consider it as a hybrid technology which has best parts of information technology as well as physical sciences. This field of quantum information technology has the potential to generate radically new information processing devices. Examples are quantum crypto systems, which provide guaranteed secure communication, and quantum computers, which manipulate data quantum mechanically and could thus solve some problems currently intractable to conventional computations. Further, day-to-day applications and uses depends on quantum physics for their operations, like fluorescent lights, in which mercury has ability to emit light in the visible range. Biological compass is a very natural phenomenon used by migratory birds and other insects, also works on the principle of quantum physics and enable the migratory animals to follow the magnetic path for the migration. In the field of model science of bioinstruments, some major diagnostic devices are based on quantum information system like electron microscopy, lasers, GPS, MRI, and NMR, and our most used technology today, that is telecommunication, is also example of quantum information tools. In my view, this quantum information has made life easier by its applications in a very positive way. I wish a great success to this workshop for the welfare of humanity and progress of science as well. Thanks to one and all the best for this workshop. Thank you.
Thank you, sir, for giving us your precious time. Your constant guidance and support helps us a lot in organizing this workshop. On behalf of the organizing committee and the entire family of Christchurch College, I express my gratitude to all our guests, faculty members, delegates, and students for their presence and participation in this program. I would like to make a special mention of our course director, Professor H.S. Mani, who is the backbone of this workshop. Due to him only, we are able to organize this workshop in our college. We are extremely thankful to him for all his inspiration and guidance. I would like to thank the technical team who provide all the support in organizing this workshop. Hope the academic deliberation by some prominent resource persons will provide us a lot of inputs, which is going to be quite beneficial, especially for the postgraduate students and young researchers in all their future endeavors. With this, we come to the end of the inaugural function. Thank you very much. Very shortly, we are going to start up with the first session of this ongoing virtual lecture workshop on elements of quantum information. Again, thank you very much. May I request Dr. Dwivedi sir to please tell me when to start the first session? Shall we start it right now, or we will wait for 1 or 2 minutes?
You can start after 3-4 minutes because 10:45 is the time.
Okay, I'll start at 10:45. Okay. Okay.
So it's only 2-3 minutes are left.
Okay. Okay. Okay.
Hello. Hello.
Hello, ma'am.
Yeah, am I audible?
Hello.
Yeah, just checking the mic.
You are clearly audible, ma'am.
Should I start sharing my screen?
Ma'am, within 2 minutes we will start.
Okay.
At 10:45, sharp at 10:45, ma'am, please.
Just let me know. Yeah.
But ma'am can share the PPT presentation in the meantime. Madam,
I can start loading the
share
PPT.
your
Yeah.
lecture. You can.
Ma'am, you can share the PPT, then I'll start with the proceedings, ma'am. I have to coordinate this session. Sir, shall I start? It's 10:45 now.
Start now, yeah.
Okay. So, I welcome you all to the first session of the ongoing lecture workshop on elements of quantum information. In this morning session, we have Professor Anuradha Misra with us. Before inviting her for her presentation, let me share some of her credentials with you all. After completing her MSc and PhD from IIT Kanpur, Dr. Misra has joined University of Mumbai in 1994, and presently she is working as professor and head of the physics department at University of Mumbai. An eminent educator and excellent researcher, her area of specialization is theoretical high energy physics, and her research area includes light front field theory, LFFT, resummation in quantum chromodynamics, spin physics, physics beyond standard model, to name a few. She has more than 70 research papers in refereed journals of national and international reputes, and she has completed 5 research projects sponsored by various funding agencies like DST, DE-BRNS, and DST-SERB, of which are of eminent importance. She has conferred with many awards and honors such as INSA Visiting Fellowship for the year 2013-14, Senior Associate at ICTP Trieste, Italy, Research Award of University of Mumbai 2018-19, to name a few. She has been the resource person in various science academies refresher courses on statistical physics and quantum mechanics, and also in UGC-sponsored refresher courses held at the Department of Physics, University of Mumbai in the last 21 years. Now I request most cordially you, ma'am, to deliver your first lecture of the morning session. Dr. Misra, ma'am.
Thank you, Dr. Dwivedi, for a very kind introduction. So, as mentioned, I'll be talking about basics of quantum mechanics, and many of you have been teaching quantum mechanics, so you may be familiar with many of the things that I do today. But my lectures will be a little different from how it has been done in traditional BSc courses. So these are the references on. So these are the references that I'll be using. And what are we going to cover in these lectures? So today's lecture and tomorrow, most of today's and tomorrow's lectures will be spent on motivating quantum mechanics, the subject of quantum mechanics, and the formalism as it is. So we will be, I will try to motivate what the connection between quantum mechanics and linear algebra. So linear algebra is language of quantum mechanics, and what I would do in these lectures, I'll be discussing the thought experiments which were done in the early last century, and we'll see how the concept of using linear algebra in quantum mechanics came into being, and then we'll talk about the formalism of linear algebra and basic postulates of quantum mechanics. In the later part of the course, I'll be talking about spin half systems, which are simple systems which are solvable easily, analytically, and which show all the features of quantum mechanics and its basic formalism. We'll also be talking about variational principles, because most of the problems cannot be solved exactly, and one has to use approximation methods. And finally, I'll talk about Bell's theorem. So let us start with the beginning. How did the whole idea of having a mechanics which is different from the traditional classical mechanics came into being? So let us start from the beginning, very beginning, and ask the question, what is a physical law? So physical law is a statement of nature which every experimentalist must arrive at. They should all agree on the law behind their results. And experiments which are done in different frames must give the same results. However, the description of physical law is dynamic. It changes with time. So why should the truth be a function of time? The reason is that the laws of physics are formulated on the basis of observations, and observations depend on the accuracy of instruments that we use. And therefore, as the experiments become more and more sophisticated and the technology develops, our overall picture of the nature changes, and we have to modify our laws, sometimes slightly and sometimes in a big way. So the laws that remain true with the advancement of technology, they become more, they gain more in stature, and those which do not match with the experiment, they have to be given up. And we know that we know how relativity came into being as science developed, which was developed by giants like Galileo, Newton, Euler, Lagrange, etc., and which was considered to be the theory of physics for almost 3 centuries. It was considered to be the theory till the early 20th century, and then some perplexing experimental observations came into being, and these observations could not be explained on the basis of classical physics, and that is how quantum mechanics was born. However, it was not the change from classical to quantum mechanics was not some change of parameters or models or something like that. What quantum mechanics required was a completely new way of thinking. These observations told that we have to change our way of thinking from objective determinism to subjective probability. And what does that mean? Objective determinism, as in classical mechanics, means that if you are given some initial conditions, then you have a certain law which tells you exactly what are going to be the final conditions of the system. And subjective probability, which is the basis of quantum mechanics, says that you can only predict the probability of an event taking place, and even the act of measurement is going to disturb the system. So your results are going to depend on the observer also. So this kind of change is not some minor change which can be accommodated by changing your equations or theory. You needed to have a new way of thinking. So how did this transition from old theory to new theory come in, and how does it accommodate the old theory? So basically, we talk of a domain of a phenomena. Let me call Dn as the domain of the new theory, and Do to be the domain of the old theory. So whatever we establish in the new theory must also be valid in the old theory, because it was already there and it was verified in the domain of the old theory. So in the domain of the old theory, there are some predictions which have been made and which have been verified. Those predictions must be made by the new theory also, and sometimes it may be easier to use the old theory to do those things. Just like classical mechanics is still in use, although we know that quantum mechanics is the correct theory, or classical electrodynamics can explain a lot of phenomena, physical phenomena, even though we know that there is a quantum theory of electrodynamics, which is called the quantum electrodynamics. So there may, in the domain of the old theory, it may still be useful to use the techniques of the old theory. However, the new theory will be able to explain phenomena in the new domain as well as in the old domain. That is what happens in the correspondence principle, or even in relativity when you take the limit v going to 0 or v much smaller than c, then you reproduce the results of the classical physics. So this new theory may bring not only numerical changes but also radical conceptual changes, as I said, and this will have a bearing in all of the domains. So what were these perplexing observations that brought this kind of a change from classical physics to quantum theory? So everybody knows that initially we thought there are two kinds of distinct entities, matter and radiation. And matter is described by the Newton's law and radiation is described by Maxwell's equation. That was the picture that was there in the early 20th century. And people thought that they are different entities and we understand everything. However, in modern physics was born then when these perplexing observations were made that light shows wave phenomena as well as particle phenomena. So it exhibits interference, which is a wave phenomena, and it also shows a photoelectric effect, which treats light as the quantum of photons as the quantum of light. Then there was the Bohr's model of atom, which could not be explained without bringing in some new ideas. Classically, if you have an atom and there is an electron moving around the positively charged nucleus, then the electron should radiate energy and finally it should fall into inside the nucleus, and we would not have a stable matter. But Bohr's model of atom explained this structure of atom by bringing in new concept of quantization. Then there was black body radiation. So black body radiation was the first indication that light actually is not a wave, but it consists of particles or quantum. So let us start with black body radiation. What is the black body? It is a closed container with a small hole in the wall, and it is kept in a oven of uniform temperature, and then it starts radiating energy. So at high temperatures, visible light emerges, and one can find the spectrum of this radiation and plot it. So this cavity contains radiant energy, and it is in thermal equilibrium with the cavity wall. And at a given temperature, this is the best radiator. Okay, so there is no other body which can absorb or emit energy more efficiently than the black body. The important thing about the black body radiation is that it is independent of the shape, size, and material of the container. That means it is a basic property of the radiation. So it must contain some physics, and this is the spectrum of black body radiation, which was observed. And the perplexing thing there was that there was no single law which could explain the whole of this spectrum. So there was Wien's displacement law, there was Rayleigh-Jean's law, and they described the different parts of this spectrum. There was no single law which could explain it. So the question was, how can there be different laws which have no connection with each other, which are describing the single phenomena? And Planck solved this problem by giving his formula for black body radiation, which was based on the fact that the radiation is being emitted in small packets, which were called the quanta. And the quanta, each of the quanta had an energy of h nu. And he calculated and he gave this distribution which fitted the black body radiation. So the hypothesis proposed by Planck was that radiation is emitted in quanta. So then there was photoelectric effect. So all of you must be familiar with photoelectric effect. You shine ultraviolet light on a metal plate, and then it emits electrons. And one can so one can study this phenomena classically. And what we expect classically is that if you increase the intensity of the light, then the kinetic energy of the ejected electrons should increase. Then secondly, no matter what is the frequency of the light that you are shining on the metal plate, there should be an ejection of electrons. And then at very low intensities, you expect some time lag between the light exposure and the time at which the electrons escape from the metal plate. However, what you found in the actual experiment was that the maximum kinetic energy of the ejected electrons is independent of intensity, but it depends on the frequency. We hear the frequency. And then there were certain frequencies below which no electrons were being emitted, and there was no time lag. So these so the observations were completely opposite to what was expected classically. And to explain then this phenomena, Einstein proposed that the light is not only emitted in packets like in black body radiation, but also it is being absorbed also in packets. Okay. So the light is being absorbed as small particles, and then one could explain this phenomena because what the metal plate is absorbing are single photons. Okay. So when the energy of this photon is more than the work function, which is the minimum energy required to release an electron from the metal, then only the electrons will come out. So all the three problems could be explained by bringing in this concept of quantum. And this quantum had energy h nu, where h is the Planck's constant. So the light is showing wave properties, and it is also showing particle properties. So what is the connection between the two descriptions? You describe the wave with the frequency or wavelength. You describe the particles with the mass and energy and momentum. So therefore there should be some connection between the energy of the particles and the frequency of the light. So these are some of the formulae which you're all familiar with. Energy and frequency are related through E is equal to h nu. Then the energy and momentum of relativistic particles are related through E square is p square c square plus m square c forth. If the particle is massless, then the relation is just E is equal to pc. And then you can do all these simple manipulations, and you can come out with the momentum of the quantum, which is h nu by c or h cross k. Then the third experiment, which showed that light is consists of particles, was Compton scattering. Compton scattering is the scattering of electrons and photons. So you have this X-ray source which emitted radiation, which was made to fall on a target, and then you looked at the frequency or wavelength of the scattered beam. So what you found was that the peak in scattered radiation shifts to longer wavelength. So the wavelength of the scattered beam was different from the wavelength of the incident beam, and Compton derived a formula for this. It could explain this phenomena by considering this scattering as a particle-particle scattering. So if you treat photons as particles, and electron-photon scattering gives you a relation between the energy of the incident beam and energy of scattered beam, or in other words, the frequency of the incident beam and the frequency of the scattered beam, which matched with the experiment. So in the classical picture, you have an oscillating electromagnetic field, which makes the charged particles oscillate, and then these oscillating charged particles again emit radiation, and therefore they can have any energy. But in Compton's explanation, which was called the billiard ball collision, that is the particle-particle interaction, the incident photon has a certain momentum p nu, which is related to the frequency of the light, and then the scattered photon makes certain angle, and so they scatter, and then both the photon and electron scatter at certain angle. One could find a spectrum of these scattered photons, and using this picture, one could explain the Compton scattering formula also. Here are the details, which are also done in most of the BSc books, I guess. So you can see that the equation in the red box is the energy conservation equation. H nu is the energy of the incident photon, mv c square is the rest mass energy of the electron, because it is at rest. And then the right hand side is h nu prime, which is the frequency of the scattered photon and the energy of the scattered electron, which is moving with the momentum PE. So using this, one could derive the change in wavelength, and it matched with the experiment. So Planck's hypothesis said that radiation is emitted in quanta, and photoelectric effect was explained by saying that the light is absorbed in quanta. So if it is emitted in quanta, it is absorbed in quanta, then it must consist of quantum only. That is what Einstein brought into the picture. So the importance of Compton effect, I already said, it was considered as a collision between two particles, and it established that light consists of particles which are called the photons. However, there is still the phenomena of interference and diffraction, which means that there are experiments, there are places like body radiation and Compton scattering, where the photoelectric effect, where the light is behaving like a particle, and then there are interference and diffraction, which we all do in the lab, where the light is behaving like a wave. So this is what Feynman called a logical tightrope. How do you explain something which sometimes behaves like a wave and sometimes behaves like a particle? So this is a quote from Einstein, that there are now two theories of light, both indispensable and without any logical connection. So diffraction and interference say that the light has a wave nature. Photoelectric effect and Compton effect say that it is a particle. So how do you explain both the things? But so that was about light, which is radiation, and we said that there are two different entities, light and radiation and matter. What about matter? Okay. So then de Broglie proposed that since just like light behaves like particles, particles also have wave nature, and he proposed this hypothesis, which is called de Broglie hypothesis, which says that each particle has a wave associated with it. And later on, Davison-Germer experiment established that indeed the electrons also produce an interference pattern, and therefore they behave like a wave. So de Broglie's hypothesis says, Planck's hypothesis says that electromagnetic wave has a wave nature, and there was strong experimental motivation behind that, as we just discussed. But de Broglie's hypothesis did not have any experimental motivation at that point, and he just said that why not particles also have wave-like behavior. So this hypothesis, as we are aware, could explain the both stationary orbits, and it predicted that if they have wavelength, if the particles have a wavelength associated with them, then they should also produce interference pattern. And this prediction was verified by Davison and Germer in their experiment. So so this is de Broglie's hypothesis. Lambda is h over p, so a particle of momentum p has a wavelength associated with it, which is given by h over p, and this wavelength depends on the momentum. Okay, and this predicted diffraction, interference, and matter of matter waves. These are called the matter waves, and they were verified in this particular experiment, which is called the Davison-Germer experiment. So here is the picture from this paper by Davison, which called R electrons waves. And there you could see, so what he's doing is, he has a nickel target, he bombarded electrons on them, and then the electrons were scattered in different directions, and he plotted the intensity of these beams against the voltage, and he found that the pattern that was shown was something which was expected from a wave. So at fixed angles, you find sharp peaks in the intensity as a function of electron energy. So this indicated that light behaves like light is behaving like particles. Particles are behaving like waves. So the light, matter, and radiation are no longer different entities which are described by different formalism. We need a new theoretical formalism which will be able to explain this kind of dual behavior. So what do you want now? What you want to develop a new theory, and what is going to be a good theory? It may not be able to tell you whether an electron is a wave or a particle, because we know that it is behaving like both. But it should be able to tell you that if you perform an experiment, then in that particular situation, is the electron going to behave like a wave or a particle? So this formulation of new theory was based on a number of thought experiments, about which I am going to talk now. And the thought experiments, in particular, I'll talk towards the end about Stern-Gerlach experiments, which will tell us how the theory has to be formulated. What is new about this theory that we are going to formulate? And we'll do that by taking analogy with the mathematics of light, and that is how we'll arrive at the concept of vectors and linear vector spaces. We'll start with the Feynman's double-slit thought experiments. So we are formulating a new theory. Why we are formulating a new theory? We are trying to motivate why we need a new theory and how we should work in this theory. Our basis is going to be the fact that radiation sometimes behaves like particles and sometimes like waves. And the same is true for matter. So let us start with the thought experiment. Feynman's logical tightrope means that we stop asking whether the electron is a particle or a wave. What we want to answer is when it is going to behave like a particle and when it is going to behave like a wave. Okay, so given an experiment, we should be able to tell whether we'll expect it to be behaving like a wave or a particle. And we need to develop a language for describing this kind of strange situation. Okay, so we need to develop, and we'll find that we need to develop a different kind of mathematics, which is going to be the language of quantum mechanics, which is going to be the language of the truth that we are all trying to seek. So what kind of language we seek is the theme of what I'm going to talk in the next 1 hour or so. So we'll talk about these thought experiments. Classical mechanics is absolutely not adequate to describe our world, because it starts with this assumption that there are two different kinds of entities. So let us quickly compare the two kinds of entities, particles and waves. Particles are localized, they are at a given point with fixed energy and momentum, and waves are spread over all space. And the second is that to describe a particle, you need at any particular time, you need to specify its momentum, its position and momentum, or some generalized coordinate and the conjugate momentum. Whereas to describe the wave you need to have some kind of function, psi x or fx, which characterizes the disturbance at some point at a time t. The particles evolve in time according to equations of motion. They may be Newton's. They follow from Newton's law, some equations of motion, and the wave function of the wave theory satisfies what is called the wave equation. The particles, if I want to find the position and velocity of a particle at a later time, then I need to solve these equations of motion with certain initial conditions. And once I know the equation of motion and I know the initial momentum and initial position and velocity, I can predict the position and velocity at a later time. In case of waves, what you are given are the initial values of the wave function and its time derivative. Then you can solve the wave equation, which tells you the evolution of the wave function, and then you can find the wave function at a future time. Now suppose a disturbance is propagating from one point to another. So I am saying that the particles have a wave associated with them, and I am saying that light is a radiation is a particle. So this is traveling from one place to another. So what is traveling? Is it a particle or a wave? How do we distinguish between them? So we know that the waves exhibit interference and the particles which are described by classical mechanics do not exhibit interference, and this is the basis of all the thought experiments. So Feynman's thought experiment based on the fact that on a very small scale, things do not behave like how they behave at the microscopic scale, or how we expect them to behave. we don't know how they are going to behave. Okay. So we will examine a phenomena which cannot be impossible, which cannot be explained in any classical fashion. And this phenomena has at its heart the essentials of quantum mechanics. And this contains the mystery, and we cannot make the mystery go away by explaining how it works. That is important. The quantum mechanics tells you how things work. It does not tell why the mystery is there, why it is happening, but it does tell you that how to deal with these systems if this kind of dual nature is being shown. So let us start with a simple thought experiment with bullets, which are particles. So you have a gun which is producing the particles, then you have a plate which has two holes. Then after that, particles come out of this gun and they pass through the holes, and they fall on a backstop at which I have put a detector which is going to count the number of particles at each position of the this backstop. So first you close hole number 2 and you let the particles pass through the hole number 1. As you make the detector pass through the screen, you find the intensity pattern of these particles which are passed through the hole. You find a pattern which is denoted in this figure by P1. Okay. Similarly, you close the hole 1 and you let the particles pass through the hole 2, and what you will get will be the pattern P2. And when you open both the holes, then what you will get will be a pattern which will have the sum of the particles. P1 and P2 are the number of particles when only hole 1 is open. P2 is number of particles when only hole 2 is open, and P12 is just the sum of the two. So we ask the question: what is the probability that a bullet which is passing through the hole in the wall will arrive at the backstop at a distance x from the center? That is what you are asking, and that is what is being plotted here. So why we are talking about probability? Because probability is the chance that the bullet will arrive at the detector, and this can be measured by counting the number of particles which arrive at a certain point divided by the total number of particles. So the ratio of the number arriving at the point x to the number of all the bullets which are being detected is called the probability, and that is what we have plotted. They arrive in lumps, one whole bullet at a time, and therefore the probability is add because the bullet has come either from hole 1 or hole 2. This is important. So P1 is the probability with only hole 1 open, P2 is the probability with only hole 2 open, and P12 is just the sum of the two. So if I am doing this experiment, which is like similar to interference experiment of waves, my result is that the probabilities just add. Okay? The numbers just add. Now let us do the same thought experiment with water waves. So I have a source of water, which is some kind of vibration is being given to the water, so it is producing waves, and these waves are made to pass again through the two holes. And beyond the hole, I have put some kind of device which is going to measure the intensity of these waves. So again, I do the same thing. I close hole 2 and find the intensity of the wave, which is found to be I1. This is I1. The upper one is I1. I have written I only. Then I close hole 1 and I measure the intensity of the water, which is coming only from hole 2. And then I open both the holes. And you know very well, you have all done optics interference experiments, that what you see is an interference pattern, and the intensity is not the sum of the intensities of I1 and intensities I1 and I2. Okay. And you can explain it by writing the expression for the wave, solution of the plane wave. So intensity can have, so one thing is that intensities can have any value. Whereas in the bullet experiment, the number is discrete number. So there is no lumpiness in the wave intensity. We can measure the wave intensity for various positions x, and we get I12. And I12 is not equal to I1 plus I2. So the intensity is not the sum of I1 and I2, and we say that the interference has taken place. And this is explained by bringing in the concept of a phase. So there are the two waves arrive at different points of the screen with different phase differences. So the place where they arrive in phase, for example, at the center of the screen, you will have constructive interference, and at other places where there is a phase difference of pi, the waves will interfere destructively, and that is how you get the interference pattern. So the mathematical quantity to express this fact is the height of the auto wave as h1 exponential I omega t, and h1 is the amplitude, omega is the frequency, and similarly for the second wave it is h2 exponential I omega 2t. So the mathematics is quite simple. We have all done it. When the hole 1 is open, intensity is h1 square. When hole 2 is open, then intensity is h2 square. Remember, h1 and h2 are the amplitude of the two waves. But when both the holes are open, then the height is h1 plus h2 mod square, and that is going to give me an extra term. Okay? So it is not h1 square plus h2 square. It is, there is an additional term which depends on delta, cos delta, and delta is the phase difference between the two waves. And as I said, when they come in phase, then the intensity is maximum. When they come out of phase, then the intensity is minimum. Is there a question or something? Okay. So in terms of intensity, I can write I12 as I1 plus I2 plus this extra term, which is oscillating with, as you go on the screen, and that is why you get the interference pattern. Now let me do the same experiment with electrons. So there's a question that is importance of thought experiments. So the importance of thought experiments is that they establish the fact that you need that particles can behave like waves, and waves can behave like particles. And we will see later on that these experiments were actually done. Okay, these were thought experiments at that time, and using the thought experiments, one could establish the dual nature of light and matter, and one could establish what kind of mathematics is needed to describe. The quantum mechanics formalism was developed. The ideas came from here, but later on these experiments were actually performed in the lab also. And they established that electrons also have wave nature. Do right now a thought experiment with electrons. So it's the same experiment as before, but now I have an electron gun. It may be a tungsten wire, and this gives away electrons which I can pass through either hole 1 or hole 2. Again, I look at the intensity pattern of the electrons by first keeping the hole 2 closed, then keeping the hole 1 closed, and what I get is P1 and P2. However, when I open both the holes, I get a pattern which is not equal to P1 plus P2. It is you again see some kind of interference pattern, and that shows that there is some quantity which is like the wave function, whose square is giving you the number of electrons that are being collected. So now the thing here is that electrons are particles. How do we know that? Because every time the electron hits the target, it can be a GM counter or something, there is going to be a click, and there are no half clicks. So the click shows that there are some particles which are arriving at the detector. Okay. So these clicks show you the number of clicks at a certain position, tell you what is the intensity of the particle. So electrons are arriving in lumps, and these are identical lumps, and the relative probability that an electron lump will arrive at a distance x from the center is what we are trying to find out. And this is the curve P12, which was like the interference pattern. So we are trying to now understand why electrons are showing an interference pattern, because they're coming in lumps. So either they have come through hole 1 or they have come through hole 2. Okay. So let us do another kind of experiment. Let us look at electrons which are coming through hole 1, electrons which are coming through hole 2, and let us look at the electrons which are coming when both the holes are open. Okay. So P12 is when both the holes are open. If this is not equal, if the electrons are like blades, like particles, then the sum should have been equal to the intensity when both the holes are open. because in case of wave, the wave is being spread, is being divided, and then the light ray gets after passing through the first hole gets spread out, and it can pass through both the holes. Here, electron is like a bullet. It is not broken, and it cannot go into both the holes. So how does it produce an interference pattern? So people thought of different things, that maybe there is a complicated path. It goes through hole 1 and then also goes through hole 2, and then they interfere and all those things. However, there is not any satisfactory explanation. So, but it was clear that there are some points where the electrons are less in number. There are some points where the electrons is more in number. And the curious part is that at positions where there were no electrons in the original one hole, or okay, thank you. So there are points where the intensity was more than twice the intensity when one or the other hole was closed. Okay, so P1, it was not just P1 plus P2, it was much more than that. So how is that possible at some point where there was very less probability if one hole was closed? It becomes a large probability if you open both the holes. How does the electron know whether the holes are open or not? Okay. So this again, so as I said, you have to have some complex numbers. You have to bring in complex number to explain this, just like we have for the wave phenomena. Because of the phase difference, you are seeing the interference pattern. So what is this quantity which is going to behave like the wave? It is the probability of arrival of these electrons, which should behave like the wave function. So the probability has certain waves associated with it. The probabilities add, and when they add like the wave function, and therefore you can explain. So for classical waves, intensity was defined as the square of the wave amplitude. Okay, and then there was a complex number to brought in as phase to show the variation. In quantum mechanics also, we must use complex number to explain this phenomena. Classical mechanics cannot explain this kind of wave behavior. Now, since the number of electrons which arrive at a point is not the sum of electrons that goes through 1 and 2, therefore this idea that electrons go through either hole 1 or hole 2 is false. Now that does not match with common sense, because electron is like a lump. So let us go one step further, and we try to see whether from which hole the electron is passing. Okay, it cannot get broken up. It is a fundamental particle, so it must have gone through only one of the holes. So let us try to watch the electrons, and something interesting happens there. So you put some device to which will give a flash if the electron passes through the hole in question. If it passes through the hole 1, you'll see a flash at hole 1. If it passes through the hole 2, then you see a flash at near hole 2. So that way you can figure out from which hole the electron is going through. Okay. However, when you do that, what happens is that the interference pattern disappears, and you just get a bullet-like probability pattern. Okay. So if we keep track of whether we saw the flash near hole 1 or hole 2, then we get the pattern which is a signature of a particle nature. So we have succeeded in watching the electrons, but in the process we have destroyed the interference. Okay, and we know that this is one of the postulates of quantum mechanics, that the act of measurement disturbs the system. So what we do now is that maybe this is the device that I have put to watch the electron that is disturbing the electron. Okay, so we can if we don't have the light source, if we don't try to watch the electron, then there is a wave-like pattern. If I try to watch the electron, then there is a particle-like pattern. So maybe this is going to the device that I'm using to watch the electron is disturbing the system. So let me try to reduce the brightness of light so that this interaction between the light and the electron becomes lighter. is weaker and weaker. When we turn down the brightness, what happens is, so there are two things happening. One is you are seeing the flash to figure out from which hole the electron has gone, and the other is you are hearing a click in the detector to figure out that the electron has arrived at a certain position. So these are the two things that are happening when you are trying to watch electrons. Now, when you turn down the brightness, you try to increase the intensity of the light, which is seeing the electrons. Then sometimes you hear a click, but you don't see the flash. Okay, which means the electron has gone through without you having been able to watch it. Okay, so which means that electron was not seen, but in some situations the electron was not seen. It could not. It escaped the photon, but it reached the detector and it created a click. So now I make 3 columns. In column 1, I write the number of electrons when I see the flash near hole 1. Okay, that is the number of electrons which have passed through hole 1. Second is when you have a flash near hole 2, which shows the number of electrons which pass through the hole 2. And in the third column, I write the number of electrons when I hear the click, but I don't see any flash, which means the electron has passed undetected, without being seen, either near hole 1 or near hole 2. So the ones which you have not seen, okay, are like the earlier experiment when I was not watching the electrons. And these electrons are going to show the interference pattern. So if you, when you look at the pattern for, those who are seen near hole 1 will have a probability distribution P1 prime. Those which have a flash near hole 2 will have a probability distribution P2 prime. And because they have been seen, they are behaving like bullets. The sum will give you P1 prime plus P2 prime. And in the column 3, you will see an interference pattern. Okay, so if the electrons are not seen, then they show an interference pattern. But when they are seen, then we do not see an interference pattern, which means the photon which is being used to watch them has disturbed the system. Okay, so what we do is we reduce the momentum, and which means we increase the wavelength. Okay, remember the energy is Hc by lambda. So I increase the wavelength, and in the process I reduce the momentum. So I am trying to make the momentum smaller so that I don't disturb the electron. Okay. However, as you increase the wavelength, at some point the wavelength becomes comparable to the distance between the two spheres. Okay, and you know that you will see the interference pattern only if the wavelength is comparable to the size of the hole. So we see a big flash through which hole the electron has gone. Okay, and at that time the interference pattern will appear again. So I cannot. So this way, by reducing the intensity of the photon beam, I can I end up creating the interference pattern again. So if I am trying to watch the electrons, I am disturbing the system. I am not able to see the pattern. I try to reduce the intensity of the beam by increasing the wavelength of the light. But in the process, I lose the information about from which hole the electron has passed, because I see a big flash and I cannot tell from which hole the electron has gone. And that brings us to this inherent uncertainty in our measurements, which means that it is impossible to arrange light in such a way that you can tell through which hole the electron has passed and still see the interference pattern. If you try to see the electron, the hole from which the electron is passing, you don't see the interference pattern. And no matter what you do, even if you keep on decreasing the intensity of the light so that you don't disturb, the moment you stop observing from which hole the electron has passed, you will start seeing the interference pattern again. So this is a new feature that I cannot tell with certainty from which hole the electron has passed if I am seeing the interference pattern. So whatever theory I am making now, the new law that I am going to find out should be able to account for this inherent uncertainty in the nature of things. And the complete theory of quantum mechanics rests on this principle. So what about the proposition that electrons go through either hole 1 or hole 2? So if I have an apparatus which can determine whether the electron has gone from either from hole 1 or hole 2, then I do not see the interference pattern. Okay. When the apparatus, there is nothing to disturb the electron, then so what is the statement? The first point, somebody is asking to explain the first point. First point is impossible to arrange light in such a way that one can tell through which hole the electron passed and still see interference pattern. So as I said, if I try to see from which hole the electron has passed, then the interference pattern disappears. So then I come up with this idea that probably I have disturbed the electron by trying to watch it, because to watch it I am making it interact with the system, with some device. So I try to decrease the intensity of the light which is being used to see the electron, so that I disturb it minimally. But when I do that, I increase the wavelength of the light, and at some point the wavelength becomes equal to the distance between the two slits. And instead of seeing a flash near hole 1 or near hole 2, you see a big flash. I think we had it somewhere. The big flash. Yeah, so there's a big flash. Okay, so this big flash, because of this big flash, I lose the information about the electron has passed. So I cannot have a probe which will tell me from which hole the electron has passed and still see the interference pattern. Okay. That was the first point. So when in the apparatus there is nothing to disturb the electron, we cannot say whether the electron has gone through hole 1 or hole 2. Okay, so if I don't disturb, then so is the electron passing through both the holes? That is the question. Because when I see the electron, when I am able to figure out from which hole the electron has gone, then I don't see the interference pattern. Interference pattern appears when the wave gets divided at the two holes and they interfere and give you the variation in the intensity. So this is the logical tightrope that we are talking about. That if I want to see the electrons from which hole it has gone through, then I don't see the interference pattern. And when I'm not seeing it, then I'm seeing the interference pattern, which means, and it indicates that the electron must have gone through both the holes. So how do I explain this thing? That if I'm not seeing it, then it is going through both the holes. So what is going through both the holes? Okay. So this is the thing that is going through both the holes is the probability. So I associate a probability wave. We'll come to bond interpretation of this thing. So we introduce a quantity which is complex number 5, which is analog of the wave function of the wave theory. Okay, so this is a probability wave, and this is a complex quantity, and therefore it acts like complex quantity and gives you a oscillating term. So when an event can occur in several alternative ways, then the probability amplitudes add. Okay, the difference between wave bullets and the wave was that in case of bullets, it was the probabilities which were adding. In case of waves, it was the amplitudes that are adding. Because when you add the amplitudes and square, then you get the oscillatory term and you get the interference pattern. So if the electron is showing an interference pattern, that shows that there is some amplitude associated with it, and it is a square of the amplitude which you are seeing on the screen. So this amplitude is actually the probability amplitude. And just like the wave thing, you see that this acts like a complex object and gives you the interference pattern. When I try to see it, then I just get P1 plus P2.
Ma'am, please unmute yourself.
Hello. Ma'am, your voice is not coming. You have been muted yourself. Yeah.
Okay, I'm sorry.
Yeah.
Is it okay now?
Yeah.
So at which point did I get muted?
Ma'am, still 20 minutes are left for 12 o'clock. 20 minutes are there.
Yeah. So could you hear the previous slide? I'm asking.
Yeah.
Could you hear me when I was doing this?
Ma'am, the moment you showed the double slit experiment, it was muted.
Okay. So this is the original double slit experiment, which was done by Young, and which was done with light waves and showed interference pattern. Okay. Now these experiments have been done with particle beams. So these are some actual papers which showed interference patterns for neutrons, for helium atoms, and for carbon-60 molecules. Okay. So these, so it was indeed confirmed experimentally much later. You can see the dates 1988, 1991, and 1999. That in the later part of the last century, there were experiments which were done, which actually confirmed that the particles indeed show interference. So this is, I'll just leave some of the details. You can see it in the slides later on. This is a double slit experiment with helium atom. This is a 1991 result. And the fringe width that was predicted using the de Broglie wavelength, treating the helium atoms as waves with wavelength equal to the de Broglie wavelength. The fringe width that was predicted was 8.4 micrometer, and the experiment verified that you indeed see this kind of pattern. So some more thoughts on double slit experiment. Just see how much I have done. 57. So some more thoughts on double slit experiment. There is some disturbance. Somebody has to unmute, has to mute themselves. There's some disturbance.
Dr. Vikas Tiwari, could you please mute yourself? It has been creating disturbance here. Vikas?
So in the double slit experiment, when we allow just one electron to pass through the slits, we consider the probability distribution of electrons, and we say that the probability function is splits into two. Okay, so what is causing the interference is the probability distribution. So there is a wave associated with the electron, and that wave gets divided at when both the holes are open, and then the secondary waves, just like in case of light, they produce the interference pattern. So this experiment was done by Taylor and with light. Okay, and so the question is, what happens in case of light? If you decrease the intensity of light, then do you see that the interference fringes disappear? So what this experiment did was to reduce the intensity of light, and even then the interference pattern was present, which meant that the photon, even with a single photon, you can get an interference pattern. So these are some of the experiments which were done with the particle beams. So with electron beam, and then 1961 was the first experiment done with an electron beam which showed interference pattern. Then there was an experiment done in 1989 by Tonomura at Hitachi, and there he also got an interference pattern with a very weak electron source. Okay, so now coming to the interpretation of double slit experiment, I can keep on reducing the intensity, arriving at the slits, and still one gets interference fringes, which shows that now this is related to the number of atoms that are coming. So each particle is going through both the slits. If you have a single particle and still you see a interference pattern, that means the particle must have gone through both the slits. So the matter waves are interfering with themselves also. Okay, so this is not the collective behavior of electrons that is giving rise to this interference pattern. Okay, it is not a collective phenomena that if you have a lot of electrons, then some will go through this and some will go through that. Even if you have a single electron, you will still have this distribution. So therefore, you have to associate a wave with each of the particles, and this wave has to be related to the momentum of the particle, because the particle has its momentum. And we cannot see the wave and particle nature at the same time. If we try to find a path of the particle, then we lose the fringes. This importance of this two-slit experiment was explained very nicely by Feynman, who wrote that a phenomena which is impossible, absolutely impossible to explain in any classical way. And this phenomena is the basis of quantum mechanics. We have to find an explanation for this phenomena. How do you explain the wave nature of particles? So in the Copenhagen interpretation of quantum mechanics, you come up with the concept of probability waves, which describe the probability of finding a particle at a given location. Until the particle is detected at any location along this probability wave, in principle, it exists at every point. Till you have made the measurement, you do not know where the particle is, because it's a wave which is spread all over the place. So the particles could be passing through either of the two slits if it was a particle, but since it has a wave associated with it, it will pass through both the slits. And as a result of that, you see the interference pattern. But if the particle is detected at one of the two slits, then it cannot, once you have seen a particle, it cannot pass through both the slits, and then you see a bullet-like pattern. So I'll just very quickly go over this. I don't know if people are familiar with path integral formulation of quantum mechanics. Path integral formulation says that if an electron is moving from point A to point B, it will take all possible paths, and there's a probability associated with each path. Okay, so in case of double slit experiment, when both the holes are open, then point A is the source and point B is the screen. Okay, so your wave will pass through both the holes, and then it will meet at B to interfere. However, when you try to watch the electron, your point B becomes the slit itself. You start the beam from the point of generation of the beam, and you are detecting it at B. So now B becomes the slit itself, and then from there a new wave starts. A new trajectory will start. So the trajectory will be from the hole till the screen, which will be like a particle trajectory. Okay, so you do not have the two paths interfering and giving the interference pattern. So when both the slits are open, one at a time, we get I1 and I2. When both the slits are open, then we find I1 plus I1, I2. When I repeat the experiment with slit 1 open but reduced intensity, then you start seeing that the energy starts coming in bursts, in packets instead of coming continuously. And you can keep on reducing the intensity, and you still find this pattern. So what we find is that the light energy is not continuous. In case of light, the energy is not continuous. It comes in bundles. And the discrete nature is obscured by the beam because the bundles come in so fast that the energy flow seems continuous in space-time. Okay, so this is how you explain the interference pattern of light if you consider light as packets of energy. So photons are also particles, so they also behave like electrons. But when you have an intense beam, they are continuously coming, and it appears that you are getting waves. Each of the bundle, like in case of photon scattering, each of the bundle carries the same energy and some momentum, and they are related through this relation which we wrote earlier for photons, E is equal to PC. So in case of photon, the energy is h nu, the momentum is h cross k, and you can find an interference pattern which is characterized by the wave number k. So now I am doing the experiment with the light beam, and I'm keeping the intensity so low that only one photon is passing through the experimental region, and I still find that I is not equal to I1 plus I2. And this is the indication that this wave function is associated not with the collection of photons, but with the single photon. Okay. So photons are not behaving like trajectories of classical mechanics. So what is this? What are these trajectories of classical mechanics? In principle, in practice, what is happening? Even if you have a okay, let me just talk about it because we have less time. So let us talk about the Born interpretation, which says that with each photon there is a wave associated, which is called the psi x, and this wave is the probability amplitude, and the mod square of this is going to give me the probability of finding the particle at x. With each photon, there will be a wave function, which will be a plane wave, and the plane wave, is characterized by k and omega, and which can be calculated from the momentum and energy of the photon. So the wave vector and the frequency associated with the wave is related to the momentum and energy of the particle. This wave interferes with itself, and it gives the oscillatory pattern, and that gives the probability that the given photon will arrive at x. So the photon arrives at some definite x, but from that you do not know the probability distribution that was there initially. So if you look at a single photon, you just know the position where it has come. To find the probability distribution, you have to do the experiment with several photons. Okay, so you wait for several photons to come, and then the number will that you measure at a certain position is going to give you an estimate of the probability function. So wave is associated not with the beam of photons, but with each photon, because even when we keep on trying the lowering intensity, even then we see the interference pattern. I mean, we make sure that photons come one at a time, and still in the end we see that there is an interference pattern. So if the beam is monochromatic, every photon is given by the same wave function and the same probability distribution, and a large number of these photons will reproduce the classical electromagnetic interference pattern, and you will not be able to see the probabilistic interpretation. So in the Born interpretation, all particles are described by probability amplitudes, and there's an assumption that they move in definite trajectory if not there. Now wave nature is not apparent, it is all there even if the particle is a macroscopic particle. Even if you have a macroscopic particle, even that has a wavelength associated with it. However, the wavelength is so small, much smaller than the size of the particle, that the interference gets hidden. Okay, the oscillations are so dense that you only see the average of the interference pattern, and that is why you see a pattern which looks like which is different from an interference pattern. So the basic thing is the wavelength. Okay, so every particle has a wave nature, and even when you are doing experiments with macroscopic particles, even then there is an interference that is taking place. However, because of the value of the Planck's constant, or because of the velocity being so small, the wavelength being so small, the interference pattern gets hidden in the average. So, so now the difference between the classical mechanics and quantum mechanics. Newton's law describes the classical mechanical work. They say that given any initial condition and the velocity of a particle, and if you know all the forces acting on the particle, then you can find a trajectory uniquely. This is called determinism. In quantum mechanics, there is no determinism. Okay, this certainty, objective determinism was destroyed, and this happened because of the Heisenberg uncertainty principle, which says that if the momentum of the particle is known precisely, then the position is completely unknown. If the position is known exactly, then the information about the momentum is completely lost. So if I run an experiment many times, and I measure the position of the electron, for example, observability position, then I will get a different result every time. So I cannot tell exactly, in quantum mechanics, I cannot tell exactly what is going to be the value of my observable if I'm making a measurement of a certain observable. However, I can tell the average value that I will measure if I perform the identical experiment many times. And we can find the uncertainty in my measurements, which is given by average of x square minus square of the average, okay, standard deviation. So I can find the uncertainty in position. If I try to reduce in uncertainty, then the uncertainty in momentum, which is defined in a similar way, is going to increase. I cannot determine from which path, from which hole it has gone, and still see the interference pattern. So the width in the momentum and the width in position are inversely related, and the product is given by Strauss by 2. This is your uncertainty principle, which essentially says that unlike classical mechanics, I cannot find the position and momentum simultaneously exactly. Okay. So what have we learned so far? That light sometimes behaves like particles and sometimes it behaves like waves. Particles, like electron, also sometimes behave like waves. And the uncertainty principle, which says that we cannot determine the momentum and position exactly at the same time. So we need a new formalism to describe this behavior, because we have, as we discussed, we have a formalism for particles, we have a formalism for waves, but now we are having entities which are sometimes behaving like particles and sometimes they are behaving like waves. So what are these waves? These waves are probability waves, which were established by double slit experiment for waves and for light, and by Davison-Germer experiment for the electrons. Both of them show wave-like behavior, and therefore we would like to introduce some quantity which will describe the wave behavior. So we attach an amplitude function, and the square of this amplitude function will be equivalent of intensity of the wave. So Bond called it the probability density, and the rules of quantum mechanics tell you how to calculate this probability amplitude. So basically, this is the wave function in quantum mechanics, and all the information is contained in the wave function. So once you know the wave function, and once you are given the system, what are the forces acting and all, then you can, the quantum mechanics techniques tell you how to calculate this wave function at a later point if you know it at an initial point, and if you know how the function is evolving, which is given by the Hamiltonian. So how are we going to do it? So we will now, I think, and this is a good point to take a break. We will start with Stern-Gerlach experiment, and which is actually also an introduction to a two-state system. And we'll see how the Stern-Gerlach experiment result tells me what kind of methodology I should use, what kind of machinery is used in quantum mechanics, should be used in quantum mechanics. So, so can we stop at this point?
Yeah, ma'am, you can take a break. It is such a nice lecture, so we can continue it after a break, because maybe you get tired. So, ma'am, thank you very much for such a beautiful introduction of the quantum mechanics. In fact, I must say that I have learned a lot of things like this one: matter, radiation, photoelectric effect, Compton effect, and everything, because I am teaching quantum mechanics in my college. But today I have seen quantum mechanics from a new perspective, from a new outlook. And today only I must say that I have gone through the importance of the double slit experiments. The things you have explained with the bullets and then with water waves and finally with the electrons, it was something very good, and some very nice things like that each photon interferes only with itself, and matter waves can interfere with itself. So some very nice introduction of the quantum mechanics you have given, ma'am. Thank you very much. And I have seen in the chat box that you have already answered some of the queries. But I think that there are one or two questions. So, ma'am, if you permit, then I'll take that questions, right?
Yeah, sure.
I can take, ma'am?
Yes, sure, sure.
Yeah, so in the beginning, there is one question related with the that photoelectric effect. Okay, I'm just scrolling through my screen. Yeah, that question is: are the emitted electrons of the photoelectric effect relativistic?
Photons are always relativistic.
Okay.
They always move at the speed of light.
Okay.
Photons are massless particles.
Okay. So
and massless particles move with the speed of light.
They are always, yeah, photon. They move with the velocity of the light. Okay. So I think that most of the questions, ma'am, you have already taken it up.
And I strongly recommend to all the teachers and students to take a look at Feynman lecture volume 3.
Yeah.
Because this is the best way to start, to get a motivation for why quantum mechanics is needed. So,
yeah, that double slit experiment you have shown, that is beautifully explained in that Feynman lectures. Okay. And another question is there, ma'am. Just last question I'm taking it up. Is the photoelectric effect of phenomena of inelastic collision and do not follow momentum conservation, while Compton scattering is an elastic collision of the photon and electron?
Quantum scattering is an elastic scattering, yes.
But the photoelectric effect of phenomena of inelastic collision, is it so?
Photoelectric effect is, yes, you would say that, yeah.
We can say that, okay.
The light shines on the target and electrons are emitted.
Yeah, that light gives the full energy to the electron and then it disappears.
And then it emits. It's emitted.
So again, thank you very much for the nice nice introduction of the quantum mechanics and for the first lecture you have given. So we will take a short break and we will return for your second lecture at 12:15.
Thank you.
Okay, thank you.
Yes, very good afternoon to all of you. I'm Manish Kapoor from Christchurch College, Department of Physics, and I'm very much feeling privileged and enlightened to be the part of this August gathering. And ma'am, I do have a feeling that you have started the topic from the very basic, and for us as a learner, it will be a bliss. And I would like to add few points so that we will get more enriched from your knowledge. And it is basically, one of our participant has asked about the single photon experiment. So, in the Stirling experiment, before going to the details of that, would you kindly tell us the latest status of single photon experiment to us, and then match it with us your mainstream of the second lecture. And other point is like how we whenever we are going to observe anything, we disturb the system, and that disturbance causes the layman's language uncertainty to the things. So in this regard, what is our latest idea, how do we comprehend in your words? I would like to just know. So I'm just passing this to you for your second lecture. And please, ma'am, tell us more and enlighten us more. Thank you, ma'am.
Yes, so when one talks about single photon experiment, what you're saying is that you make sure that at a time only one photon passes. Okay, and even then you see the interference pattern. This is when I say that there is a wave function associated with a single photon. So if you have a continuous beam of photons coming in, then you can consider it as a collective phenomenon. But even if you make sure that only a single photon passes at a time, even then you see interference pattern, and that indicates that there is a wave associated with every photon and not as as a collective phenomenon. Okay? And the second thing about the measurement disturbing the system. Okay? So this is inherent in quantum mechanics. We will talk more about it on second and third day. I'm going to talk more about measurement later on. But basically, this uncertainty is not because of the any limitation of the experiment. It is inherent in nature that you cannot. I can share the PDF of the lecture. Somebody is asking for notes in PDF. I will share the PDF of the lecture, and that can be shared. So we will talk more about measurement and uncertainty in future lectures. Okay. Yeah.
Yes, you can start.
Okay. So in the first part, I started by saying that in the first two lectures I try to motivate. Will be concerned with motivation. So I try to motivate why do we need quantum mechanics, and now I try to motivate why do we need the machinery that we use. That is the machinery of linear algebra. How do we know that we should use that? So I'll try to motivate that, and then therefore we'll do all that formulation of quantum mechanics directly in the what is called the bracket notation. How do we know that we have to use that language of linear algebra? So now my question is that how do we develop this terminology? And I'll start by looking at the Stern-Galag experiment, and then I'll do a thought experiment on Stern-Galag, what is called a Stern-Galag apparatus. So what do we do in Stern-Galag experiment? You have you make some silver atoms pass through an inhomogeneous magnetic field, and you look at the pattern of the atoms after they pass through this magnetic field. So let us start by looking at the expression for magnetic moment. If you have a loop of current, you associated a magnetic moment with it, and this magnetic moment for a particle would spin. This magnetic moment is associated to the spin. So what is the spin of the electron? How did we know there is a orbital angular momentum associated with the particle going in a charged particle going in a circle. What do I mean by spin of electron, and how did the concept of spin came into being? It is not because of electron rotating about some axis or something like that. It is an intrinsic property of the electron, and this was found in this was proposed after the result of Stern-Galag experiment. So you have these silver atoms, which are made to pass through an inhomogeneous magnetic field, and then you put a detector and you try to look at the a pattern of these particles. So as I'll argue in a few minutes, what you classically expect is that you'll get a continuous pattern on the screen, and what you actually see are just two positions where you get the electrons, and this indicated that electron has a spin half. So what is happening here? I have this silver atom which has 47 electrons. So 46 out of these form a total angular momentum of 0, and therefore the angular momentum of the atom comes on the spin of the next last electron. Okay, we are neglecting nuclear spin also. So this atom has an angular momentum, and here it is only because of the intrinsic spin of the 47th electron. The magnetic moment of the electron is proportional to the electron spin, as I wrote in the earlier slide. And depending on the direction of the spin, the magnetic moment will have a certain direction, up or down. And then this magnetic moment interacts with the magnetic field, and that gives rise to the deflection. So depending on what is the value of mu z, there will be deflection. So normally you would expect that mu z can take any possible value. Classically, you would think that angular momentum z component can take any value, and therefore there will be deviation in all directions, and you should get a continuous spectrum on the screen. Okay, so you can say that the apparatus is actually measuring the z component of the magnetic moment. So if the atoms are randomly oriented, then there is no preferred direction for the orientation of magnetic moment. All the every atom is oriented in a different direction, and mu z can take all possible values, and you will expect that there will be electrons at all points decided by maximum mu and minimum minus mu. But what we see experimentally are that there are just two distinct blobs where you get the electron, which means that so this is an indication that the magnetic moment is quantized. Okay, so original silver beam had magnetic moment pointing in all directions, but the result of Stern-Galag apparatus showed that there are only two possible directions, which are giving rise to one each of these blobs. So, which means that the spin of the electron, that last electron, can take only two orientations. Either it is in some z axis, z component is either up or down. So up component takes it to the upper plane, one of the point, and the minus component takes to the other point, and you can infer from that the z component of spin is taking discrete values, which that are say h cross by 2 and minus h cross by 2. So this says that the spin is quantized. Then and those of you who have done angular momentum theory, you know that if the angular momentum is j, then there are 2j plus 1 sz eigenstates. So 2 means 2s plus 1 is 2 means that spin must be half. So this was the experiment which indicated that electron has a spin half. if they had, I mean, there's nothing sacred about Z direction, you could have taken it to be apparatus to be in the X direction or Y direction or Z direction. So now let me start with my thought experiment. Think of this box, which I call SGZ hat, which is the which will be called as Stern-Gerlach apparatus, in which the magnetic field is in the Z direction, which means it will select the Z component to be H cross by 2 or minus H cross by 2. So after passing through this apparatus, the beam will be, which was unpolarized to begin with, will split into two beams, one polarized along the plus Z direction and the other polarized along the minus Z direction. So I call them Z plus and Z minus beam. So the outcome of the Stern-Gerlach experiment is to give you two beams, Z plus and Z minus. Now I block one of these beams. So in the second figure, I have blocked the Z minus beam, and now what is coming out of the apparatus is just the Z plus component. That is, all the electrons are polarized, have their spin pointing in the plus Z direction. In the third step, I put another Stern-Gerlach experiment in front of this beam. So since this is selecting the plus component, it will pass through it, and no matter how many Stern-Gerlach experiment apparatus I keep on putting in the path of the beam, I will keep on getting only the Z plus beam, which is fine. Okay. Now, so what has happened? This is just a summary of what I said. No matter how many Stern-Gerlach apparatus I put in that direction, there is only one beam coming out of Z plus and Z minus. So although silver atoms were oriented in all possible directions. So this apparatus is a measuring device which puts atoms which were originally in all possible states in either one of the two states, which is specific to the apparatus. So this apparatus is specific to the Z direction. Now, once I have used the Stern-Gerlach apparatus and put the beam to be in one of the two possible states, then repeated measurements are not going to disturb the system. I'll keep on getting the same orientation. Now I go a step further, and after selecting this Z plus beam, I put another Stern-Gerlach apparatus, which is SGX hat. So what is this X hat doing? This is selecting the electrons whose spins are oriented in plus X direction or minus X direction. As I said, there's nothing special about that direction. You could call any axis to be Z axis. So now I take the perpendicular axis and I put an apparatus which has a magnetic field pointing in the X direction. My beam was original beam, which has come out of Z hat and has been blocked partially, is giving me a electron whose spin is pointing in the Z direction. And now I make these electrons pass through another apparatus which is selecting spin projections in X and minus X directions. The result of this second Stern-Gerlach apparatus gives me, so obviously it is SGX plus, so it will orient the spin in plus X and minus X direction. So it will give me two beams. I'll call them X plus and X minus. So what does this mean? This means that 50% of the atoms in this SZ plus beam, which was coming out of the first apparatus, they are made of atoms which have Sx plus for the X component, and 50% are characterized by Sx minus. Okay. Now I put another Stern-Gerlach apparatus after the second beam, which is giving Px plus and X minus. I put another SGZ hat, which will again select Z plus and Z minus. Now you see this is exactly symmetric to what I did earlier. I had a beam polarized in X plus direction, and I put an X hat apparatus, and that gave me X plus and X minus. I block X minus in that, and what I get is only X plus beam. I make this path to SGZ hat, and I get back Z plus and Z minus. So I started with a beam which had only a Z plus component, but after passing through this set of arrangement of three Stern-Gerlach apparatus, SZ beam which has been removed has reappeared. Okay. So what do you conclude from this? you say that the second measurement, which is putting the X-hat apparatus, has disturbed the first measurement. First measurement selected the Z plus beam, but the second measurement has disturbed the system, and I'm again having both Z plus and Z minus. Okay, so the second measurement has put the system in states. So every apparatus has states specific to it. Z apparatus has states Z plus and Z minus is specific to it. X apparatus has states X plus and X minus is specific to it. So when I put the second apparatus, I disturb the result of the first measurement. So the third measurement is again bringing me both Z plus and Z minus. So first measurement, I make first measurement, which puts the system into one of the two possible states. The second measurement disturbs and gives you beams which are in the X plus and X minus states. And the third measurement again disturbs this beam which has come out of the second apparatus and puts it in both Z plus and Z minus states. So conclusion that you can draw is that the measurement has disturbed the quantum system. These boxes are nothing but the measurements. So the measurement has, in quantum mechanics, what it has done, the first one has put the system in states which are specific to the measurement. Z apparatus puts the system into a combination of Z plus and Z minus states, which are oriented, have spin oriented along Z axis and minus Z axis. So each of these boxes corresponds to measurements, and each of these measurements puts the system into states which are specific to the apparatus. We will see the connection with eigenvalue problem later on. So those who are familiar with the eigenvalue problem, every operator has certain special wave functions and special states associated with it, which gives back the which if you apply the operator, you get back the state up to some normalization. So this measurement is doing exactly that thing. It is putting the system into states which are special to that particular measurement. Now, once I have made measurement of the same variable, no matter how many times I measure it again, it is not going to change. The same measurement of same variable is not going to give you any new result. You will keep on measuring the same value. That is, the further measurements of the same variable do not disturb the system anymore. They do not change the system. But if I try to measure another variable, then I will disturb the system. And this disturbance can put the system back into a combination of the two states out of which I have selected one. So it brings back your Z minus. Now this is completely different from classical physics. That if I measure Fx, and I am destroying the information about Sz. Okay. In classical physics, the three components of angular momentum are independent. Okay. So what we are saying here is that we can never measure Sx and Hz together. And such variables are called incompatible variables. So these two measurements are incompatible. If you look at the angular momentum of a spinning top, it has it can have three components of angular momentum, Lx, Ly, Lz, related to the frequency, and you can specify all the three together at the same time, simultaneously. In quantum mechanics, you cannot do that. As we discussed in this thought experiment, if you try to measure one of them, you disturb the other one. How do I describe this kind of picture? What is the mathematical description of this kind of behavior? So we'll take an analogy with optics, and we'll see that the same methodology that we use there can be used here also. So we look at the polarization. It is very similar to what happens in polarization experiment. Suppose I have a monochromatic light wave, which is propagating in Z direction and is polarized in X direction. So you can see that this gives the electric field. The amplitude is along X hat axis, the first equation, and cos kz minus omega t tells me that the wave is moving in the Z direction. The second one is a linearly polarized light in the Y direction. So the amplitude is along Y hat and it is still propagating in the Z direction. Now I can put a filter which will polarize light in the X direction. Okay? So I can put a filter and cut down the. So I have a light polarized in arbitrary direction, a linear combination of x and y, and I can put the y component and.
Are you there, ma'am? Are you there? Ma'am, it is the audio is not coming. Are you listening, ma'am? There is some connecting problem. Pardon, ma'am? Am I audible? ये वहीं से उसी हैंडल कर पड़ा है द्विवेदी सर कनेक्टिविटीज
नहीं हम लोगों का माइक खुल रहा है ना
हाँ हम लोग का तो
माइक इज वर्किंग सर का तो माइक भी नहीं खुल रहा
हम लोग का तो खुल रहा है मेरा तो खुल रहा है ऑडिबल यहाँ पे आ रहा है यस मैम यस सर
हेलो मनीष जी आप अपने को अनम्यूट कीजिए पहले
यस सर
हेलो हेलो
हेलो
यस यस मैम हाँ यू आर ऑडिबल मैम प्लीज कंटिन्यू यस मैम
Yeah, there seems to be some problem at her end. He will join.
Yes, ma'am. Please unmute, ma'am.
Ma'am, please unmute yourself. Ma'am, please unmute.
I think I had lost the connection.
Yeah. Now you are audible.
Now I'm audible.
You have to tell me on which slide I was when I lost the connection.
The polarization idea of light. You are telling us the analogy
Okay.
for the polarized light.
Yeah.
Ma'am, X filters and Y filters you were just telling.
Right. So did you hear when I said that there's a misprint in this line? Can you see the screen?
No, ma'am. Right now it is not there. You have to turn that.
Yeah, I'll do it again.
Yeah, now it is visible. Yeah.
Okay. So, sorry. So did you hear when I said that there is a misprint in this line?
Yeah, it is clear.
Okay. Yeah. So, yeah, so we are trying to make an analogy with the Stern-Gerlach apparatus. So I have here X filter and Y filters, and there I had this SZ apparatus and SX apparatus. So SZ apparatus is analogous to this X and Y polarized light, and SX plus that I had there, I will correspondingly have rotated axes X prime and Y prime, and that will select the lights polarized along X prime and Y prime, which I showed in the next picture here. Yeah. So I have XY axis, vertical and horizontal, which will select the lights polarized along X direction and Y direction. And X prime and Y prime are making an angle of 45 degrees with X and Y axis. And the lights that come out of X prime filter and Y prime filter will be polarized along X prime direction and Y prime direction. And then as you see in these equations, I can write these vectors X prime and Y prime as linear combinations of X hat and Y hat. So I can write the Y prime, X prime and Y prime polarized lights as linear combinations of lights polarized along X and Y direction. Okay, am I audible and visible? Can you just confirm?
Yeah. It is audible and visible. Very clear,
okay.
ma'am.
Yeah. So now I look at what kind of mathematics we use in polarization, because this is very similar. There is an analogy between the Stern-Gerlach and the polarization experiment. We know how to deal with polarized light, and if we can use the same mathematics for describing our Stern-Gerlach type of situation or quantum mechanical systems. So in the triple filter arrangement, I have first filter, which will give an X polarized light. Okay, and X polarized light is a linear combination of X prime polarized beam and Y prime polarized beam. Just like I can write a vector in the X prime direction as a linear combination of X and Y direction, I can do the reverse also, and I can write the X polarized beam as a linear combination of X prime polarized beam and Y prime polarized beam. Then in the second filter will be an X prime polarized filter. Okay, so there are two set of axes, XY and X prime, Y prime. The first filter is along X direction. The second is along X prime direction. And this X prime polarized beam is a linear combination of X and Y polarized beam. So out of the X polarized beam, which has come out of the first filter, it will pick up the X prime direction. Okay. Now the third filter, I put a Y polarized beam, which is again a linear combination of X prime and Y prime. So this will select the Y polarized beam. So what we had done, we had cut out the Y component by using the X filter. However, now we after putting the X prime filter, I get back the Y component. Okay. So similarly, we can represent the spin state of figure atoms by some kind of vectors in some abstract space. But this is not the usual vector space. We'll see in a minute. So this is the analogy. Let us look at it carefully. In case of light, X and Y was my basis, and I could expand the X prime and Y prime vector polarized lights in terms of these. Here, by analogy, I have this Z apparatus, which is like the XY basis. Okay, so this Z apparatus picks up SZ plus and SZ minus. So I am representing the spin state Sx plus and Sx minus as vectors. This notation, where I have a vertical line and a bracket, is called a ket. So I write Sx as a ket vector, Sx plus as a ket vector, which is the being polarized in positive X direction. And I can write it as a linear combination in the second basis, prime basis, which is So Sx plus and Sx minus are corresponding to the x prime and y prime axis. And Sz plus and Sz minus are correspond to x and y axis. So I can write the Sx plus spin projection as a linear combination of Sz plus and Sz minus, and same with Sx minus. There's nothing special about Z or X direction. I could have chosen Sy plus and Sy minus also. And whatever is holding for Z and X will hold for those two also, Y and X also. The point is that your the number of states are independent states are only 2. Okay. So let us take this analogy further. Now I use a circularly polarized light. Okay. So circularly polarized light is a combination of linearly polarized lights along x and y direction with a phase between them. So the first box here you can see it is x hat cos kz minus omega t, and with y hat I have cos kz minus omega t plus pi by 2. So there is a phase difference which gives rise to circularly polarized light. So when we pass it with circularly polarized light to an X filter, only the X filter will come out. If I pass it through the Y filter, only Y component will come out. Okay. Now the circularly polarized light is different from the linearly polarized light along the X prime and Y prime. Okay. This I have already explained that there is a phase difference between the two components. So okay. So I can use this same notation using a complex notation where I write the electric field as a complex quantity where the instead of cos and sine I am using the exponential function. So I replace cosine z and cosine z minus omega t and cosine z minus omega t plus pi by 2y, the corresponding exponential, and the electric field is a real part of it. And then I can take out this exponential I k z minus omega t, which is the which shows the propagation of wave along the z direction, and then the amplitude is a complex quantity which is x hat plus E naught x hat plus I y hat. So using this complex notation, I am able to explain this phenomena that how so by using this treating these fields as vectors, I am able to explain the phenomena how a light which was polarized along x direction after passing through another filter reproduces the y component. And the same thing was happening with Stern-Galag experiment. So I am going to now represent my spin states as vectors in a linear vector space. Okay. So if I represent my states by vectors in a linear vector space, I can explain this kind of behavior which cannot be explained otherwise classically. So we will represent them as ket vectors, as Sy plus and Sy minus, or Sx plus and X plus minus, all of them as linear combination of Sz plus and Sz minus. And we'll do more about spin tomorrow, and we'll see how we get these expressions. So the moral of the story is that to be able to explain this kind of experiments, the result of these kind of experiments, I need to use the language of vectors. And that is the language that we use in quantum mechanics. We consider the state of the system as a vector in a certain linear vector space. We'll see what kind of vector spaces we need. And then using the methods of linear algebra, we can determine the state of the system at a later time, which is the object of the whole exercise. And knowing the position of, knowing the state of the system at a certain time, what is going to be the state at a later time. So we are going to represent the state of the system as vectors in a linear vector space. And the observables, which are the quantities or the measurements, they will be represented by operators. So making a measurement of a certain observable will amount to applying an operator to this state that I am representing with a vector. And that operators will take me from one vector to another vector. So we'll, in the next 40 minutes or so, we are just going to now define this mathematical framework. So what I need is a framework which is based on linear algebra. So we'll formally define what is a linear vector space, what are operators, and then tomorrow we will connect all these things with the physics, how they are used in quantum mechanics. So we are going to describe the Ashtanga-Log experiment using the language of vectors, and these have no connection with ordinary vectors having magnitude and direction. So I am going to define vectors in more general quantity than what you learned in high school physics, where you say that a vector is a quantity with something which has a magnitude and direction. That is not the idea. We define these vectors in a more by defining their certain properties, and this vector space, the space of all these vectors, has to be complex in order for me to be able to explain Ashtanga-Log experiment in the same way as we explain the polarization experiment. So let us start with the definition of a linear vector space. In our Euclidean space, we have 3 unit vectors, and you can extend this idea to any dimensions. And given the unit vector, you can express any vector of the space in terms of these vectors, and these are said to be forming a basis. This is a word which you are going to use frequently. So basis in the 3-dimensional space will be the unit vectors I hat, j hat, and k hat, or E1, E hat, E2 hat, E3 hat, as you say. So the set of the 3 unit vectors in terms of which you can express any vector is called the basis of the space. So we will now generalize this concept to define what is called a linear vector space. So and the vectors in this space I am going to represent by these symbols, the vertical line and some letter and then right bracket, which are called the kets. The kets come from breaking the word bracket into 2 parts. So you have bra vectors and you have ket vectors. So 1, 2, 3 and are vectors in a space. These vectors are defined by imposing certain properties. So you define a first thing you have to define how are you going to add these vectors. So we cannot visualize these vectors as arrows in certain space, but we can define them by checking whether we can check them whether they are vectors or not by checking these properties. So we need to have a certain rule which will define the vector sum. We need a multiplication rule which will tell me how do I multiply these vectors by multiplying with a certain scalar. This is like stretching the vector in ordinary vectors by multiplying with a constant. And they should satisfy this property that if I add any 2 vectors or if I multiply a vector by a scalar quantity, I am going to get another vector. This is called closure property. I will define, then this vector addition should satisfy distributive law, which means that if I multiply the vector by a plus b, the result is the same as multiplying b with a and b with b and adding them. So it is just like ordinary vectors, the rules which ordinary vectors follow. You can, at each step, with each statement, you can, in your mind, you can keep on verifying whether these things are satisfied by the ordinary 3-dimensional vectors or not. That is the way to remember it. Then the multiplication is distributive in vectors. That is the sum of 2 vectors. If I multiply it with a scalar quantity, it is going to give me the sum of the vectors which you obtain by multiplying each of the original vectors with that constant. So a times b plus a times w is going to give me a times b plus w. Then they satisfy commutative property with respect to addition. That is whether I add a and b to get c or I add b and a to get c, I get the same vector. Next is associative property. That is, if you are adding 3 vectors, then the order in which you add them does not matter. You can first add w and z and then add b to it, or you can add z to the sum of the b and w. Then there is a null vector which has this property that if you add it to any vector, you will get back the same vector. and there is a inverse corresponding to each vector. So A plus minus A is 0 in ordinary three-dimensional vector space. So there is always corresponding to every vector V, there is another vector minus V, which will give you the null vector when if you add the two. So you can see that we have not talked about the magnitude and direction anywhere here. And the numbers A and B, I have not said anything about them. They are called the fields. And depending on whether these numbers are real or complex, you talk about real vector spaces and complex vector spaces. So a set of objects which satisfy all those properties that I have listed on the previous page will be called a vector space. And it will be a real vector space if the field is real. It will be a complex vector space if the field is complex. So vectors themselves are neither real nor complex. Okay? So the vector space is real or complex depending on the nature of the field which is used to do the scalar multiplication. So now let us just check very quickly whether the traditional vectors that we have been using all along, whether they satisfy all these properties. So there is a rule for addition. Everybody knows that how do you add two vectors? Scalar multiplication is equivalent to stretching the vector. Multiplication by negative number will change the direction as well as magnitude. So and you multiply any vector with minus 1 and you get back the negative vector or the inverse. With a null vector, there is a closure property that the sum of two vectors is also a vector. Then addition and multiplication satisfy associativity and distributive properties. Inverse exists. Vector is corresponding to every vector, there is the opposite vector. Null vector is a vector with zero length and so on. So now let us look at another example of vectors, and which is what we are going to use. So let us consider a set of 2 by 2 matrices. Okay. So you have to look at the, unfortunately, this is the disadvantage of online teaching, that you don't have the blackboard where you can go to the previous part of the blackboard and say that, okay, this compare with this. So I can't do that here, but you can go back to the properties and check one by one whether each one of them is satisfied by this set of 2 by 2 matrices or not. So you have to, first of all, you need to have a law of addition. So you know how to add two matrices. You add component by component, element by element. You can multiply matrix by a scalar. And you know that the sum of two 2 by 2 matrices is a 2 by 2 matrix. So closure property is satisfied. Associative property is satisfied by matrix addition. Distributive property is satisfied by matrix addition. With a null matrix, which is 0, 0, 0, 0, which if added to any other matrix is going to give me 0. Give me the same matrix. With an inverse matrix, which is you put a minus sign before each of the elements of ABCD, you get the negative of ABCD. Okay, so this then tells me that, yeah, so these are the properties. And you have verified that each of these properties is satisfied by the set of 2 by 2 matrices, and therefore the set of 2 by 2 matrices forms the linear vector space. The next concept that we will use heavily is the concept of linear independence of a set of vectors. So suppose I have a set of vectors 1, 2, 3, 4, etc. I is an index here which goes from 1 to n, and if I add all of them, I'm going to get a 0 vector. Okay. You can always do it in the, for example, the 3 vectors in a triangle. You can just add them and you get a 0 vector. So I have a set of vectors 1, 2, 3, 4, n, such that this combination ai, summed over I is 0. This combination is called a linear combination. So the linear combination of this set of vectors I is 0. If you find that the only solution to this equation is that all the AIs are 0, which means you cannot make a linear combination of a set of vectors 0 unless you choose all the coefficients in the linear combination to be 0. Then you say that the vectors are linearly independent. which means that this equation has no other solution except the trivial solution in which all of them are 0. And you can see that this is, so you can, for example, if you're in a plane, your unit vectors are along x direction and y direction, and they will be linearly independent because there's no way you can have ax plus by equal to 0 unless both a and b are 0. So two perpendicular vectors in a plane are linearly independent. Similarly, the three perpendicular vectors x, y, and z axes are linearly independent. So the only way you can make a combination of x hat, y hat, and z hat equal to 0 is by multiplying each one of them with the zero multiplicative constant. Okay. So if this condition is satisfied, then you say that the vectors are linearly independent. If this is not satisfied, that is, you can find some solution which is non-zero and which satisfies this equation, then you say that the vectors are linearly dependent, which actually means that you can write one of these vectors in terms of the others. Okay. So for a set of linearly independent vectors, it is not possible to write any particular member in terms of the other members. Okay. In terms of, in case of linearly independent vectors, you can do that. So two parallel vectors, for example, are two non-parallel vectors are going to be, as I said, in a plane, two non-parallel vectors are going to be linearly independent. Parallel vectors are all linearly dependent. Similarly, you cannot write, you cannot add two non-parallel vectors in any way to form a null vector. So that is also a way of saying that they are linearly independent. Now, so the number of linearly independent vectors in a space is called the dimension of the space. Okay. In a given space, there is a maximum number of vectors which can be linearly independent. For example, in a three-dimensional space, you can have only three perpendicular vectors, three basis vectors. So any vector in a three-dimensional space can be written as a linear combination of x hat, y hat, and z hat. Any other force vector is going to be expressible in terms of x hat, y hat, and z hat, and therefore it is linearly dependent on x hat, y hat, and z hat. So the dimension of the space is the maximum number of vectors which can be linearly independent, and this is called the dimension of the space. So we define the definition of a basis in a plane. As I said, x hat and y hat are the basis vectors because you can write everything else in terms of them. In a three-dimensional space, you have three unit vectors. So it has the basis has three vectors. They can be x hat, y hat, and z hat, or any other three linearly independent vectors. Then a vector, similarly, in an n-dimensional space, any vector can be written as a linear combination of n linearly dependent vectors. So any set of n linearly independent vectors in n dimensions is said to be forming a basis. Any vector can be expanded in terms of these basis vectors as we discussed. So to define all the vectors in the space, all you need is the basis vector. Okay, so any vector v in the linear vector space can be written as a linear combination of the unit vectors or the basis vectors v1, v2, vn. Okay, this expansion is unique in the sense that if once you have chosen a basis, the coefficients a1, a2, an are fixed. Okay. If you want to add two vectors, then you have to just add them component by component. Am I audible? Hello?
Yes, ma'am.
Okay.
You are audible.
Okay. Okay, fine.
Proceed.
Yeah. So if I add any two vectors, each of them can be written as a linear combination like this, and therefore, when I add them, I just have to add their component. So you can add component by component, and you will get the sum of two vectors. So what is the advantage of having a basis? Once you have a basis, you have a concrete mathematical form for the vectors. Vectors can be abstract quantities, but once you have chosen a basis, you can express them in terms of the components, and these components give a concrete quantity with which you can do manipulations. For example, you can put them in a row and you can say that this column vector is represents my vector. So here again, the addition of angular of the vectors is defined in a way different from the geometric way which we have been used to adding vectors, because there is no picture associated with a vector, but there is just a formal definition, and therefore we can use that to define vectors formally, the addition of vectors formally. Similarly, multiplication of vector by scalar will mean I multiply each of the components of the vector by the same component. So AV is going to have the same kind of expansion with AI replaced by AAI. Okay, now how do I define the scalar product? That is the question. So in case now my vectors are vectors in a complex vector space, which means when I multiply, I can multiply a complex number also, and therefore I have to be a little careful about how I define the inner product. Inner product is similar to scalar product in ordinary vector algebra. So you define, when you define scalar product of two vectors A and B, it is ax bx plus ay by plus az bz. So can I do the same thing here? That is the question. So here, what is happening is, because I have the freedom to choose the multiplicative factor as a complex quantity, I need to define another kind of vectors, which are the, in some sense, adjoint of these vectors. Okay? So I define. So okay, I'm not defining it. So I have two vectors v and w, and I want to define a quantity like v dot w. If I was putting vectors over v and w, it will be v vector dot w vector. How do I define the product of v and w? I introduce this notation in which I write the left bracket and then v and then the right bracket. Okay, so the corresponding to each vector v, there is another vector with the bracket inverted. Okay, just take the mirror image of this vector, that is called a bra vector. So what I have in the first line is the ket vector v, and the second line beginning is the ket vector w, and and in the product the v is the bra vector. So I define the inner product again by telling the property that the inner product should satisfy. Okay. So first property that satisfies is that the product of v and w is the complex conjugate of w and v. Okay. So your first departure from the ordinary vector algebra, there a dot b is the same as v dot a. Here v dot w is the complex conjugate of w dot v. Okay. Second is that the inner product of a vector with itself is always positive. The norm of the vector it is called, and it is zero if and only if b is zero. Okay. So we say that it is positive definite. That is also like ordinary vectors. A dot a square is 0. A dot a is always greater than or equal to 0, and it is 0 only if a is 0. The third property is that if I take a linear combination of w and z in the ket, then the coefficients in the linear combination just multiply the inner product. Okay, so aw plus bz product with b gives me a b dot w plus b dot z. Now this property c and property a, they together tell me that if I take the linear combination in the bra vector, that is in the first factor, then when it comes out, when the a and b factors come out, they will become the complex conjugate. So this is something new that we had not seen earlier. That if I multiply the bra vector with a constant, then the inner product gets multiplied by the complex conjugate of the constant. Okay. So I have a basis, A1, 2, 3, 4, n, and this basis can be orthogonal or non-orthogonal. Okay. Okay, orthogonal will be when the inner product of any of the two basis vectors is 0. Okay, so this basis will be called orthogonal if it is pairwise orthogonal. So in the mathematical language, I say that I, J, K, etc. are form an orthogonal basis if the inner product of I and J is delta Ij. In fact, it is an orthonormal basis because if I is equal to, so this delta Ij is the Kronecker delta, which is 1 if I and J are equal, and it is 0 if I and J are different. So this expression I dot J is delta Ij tells me that if I and J are two different vectors, then their inner product is 0. If they are same, then the inner product is, then the norm is 1. Okay, so I have two vectors, V and W. And I can expand both of them as linear combinations of the basis vector. So you say that I have expanded V and W over the set of basis vectors I, J, K, 1, 2, 3, 4, n, etc. I takes values 1 to n. Then I can use all these properties that I have defined earlier to show that the inner product is given by sum over Vi star Vi, okay, if the basis is orthonormal. Okay, so this is a simple exercise. I want you to try it at home. That okay, you can see it here only. I have taken the inner product of V and W. I pull out the Vi's, they become Vi star. I pull out the Wj, they remain Wj. And then I use the fact that I dot J is delta Ij. So that removes one of the summation signs and I get sum over Vi star Wi. So I can write the inner product in terms of the components of the vector once I have chosen the basis. Inner product of V with itself is positive definite that we have already discussed. You can see it in terms of the components. It is clearer because Vi star Vi is the real is the norm of a vector which is always positive. Okay. So using this condition, we have shown that condition A, we have shown that the norm of a vector is a real quantity. Then I can express a vector as a column vector. So I just write all the components V1, V2, Vn. So the first line of the slide you see is V1 1 plus V2 2 plus V3 3 is the linear expansion of V in terms of the basis vector 1, 2, 3, 4, n. From that I pick out the components V1, V2, Vn and I put them in a column. So I can express a vector as a column. So I put a dot over the equal sign to show that this is not actual equality. V is an abstract quantity in an abstract linear vector space, and V1, V2, Vn is a real is a concrete column matrix. Okay, so this shows that it is represented by, and for this representation I have to choose a basis. So given a vector and given a set of basis vectors, I can express the vector as a column vector by expanding it as a linear combination and putting the coefficients in the linear expansion as a column. If I define the ket vector as a column, then the bra vector has to be defined as a row, so that V dot V gives me sum over Vi star Vi. So the row that represents the bra vector has the complex conjugates of the coefficients. So in a sense, this is like taking the adjoint of the matrix. When you take the adjoint of the matrix, you take the complex conjugate and you interchange rows and columns. So the adjoint of a column is a row matrix in which all the coefficients, all the elements of the column have been complex conjugated. Similarly, I can write the inner product of V and W in terms of components by writing V as the column V1 star, V2 star, Vn star, and the row as V1, V2, Vn, and multiplying the two. Now, what are these coefficients? V1, V2, Vn. Once I am given the basis and once I know the vector, I can find these coefficients. Just like if you have a vector A, which is AXI plus BXY, BXJ plus AXI plus AYJ plus AZK, you can find the coefficients AX by dotting V with I. So in the same way, I take the inner product of the vector with the unit, with the basis vector I, basis bra I. That gives me the coefficient in the linear expansion of V in this basis. Okay, now I put back this Vi in the expression, in the linear expansion of V, and I'll get this expression. This is Vi, not I. This is Vi. This is I, not Vi. Yeah. So I can write V as a linear combination of i's, and the coefficient of I in the linear expansion is inner product of I with V. I can do the same thing with the bra vector. And from this you can see that there is an operator which is sum over I, which is actually equal to the identity operator. That is called the completeness relation. In the Stern-Galag apparatus, I add the original apparatus, original vector for spin state of the atom, which were turning into states. The apparatus was turning the spin state of the atom into either spin up or spin down. Okay, and we represented states as vector in the linear vector space. So what is the dimension of that space? That was a two-dimensional space, because I could write any vector in terms of up and down. Okay. So now the apparatus, that X apparatus that I had put, had changed the state from the pure Z plus to a linear combination of Z plus and Z minus, which means the act of measurement or act of putting that apparatus changed one vector to another vector. The original vector was a pure SZ plus, and the final vector was linear combination of SZ plus and SZ minus. So something that the apparatus has done to convert it from a pure Z plus state to a linear combination. So how do we do that in this mathematical linear vector space? Turning one state vector into another state vector. That is done by defining what are called linear operators. So I have a linear vector space, which is a collection of objects which are called vectors, which satisfy certain properties. Now I'm looking for objects which will turn one vector into another vector, which we'll call the operators. So an operator is an instruction for transforming any given vector V into another vector V prime. Okay, so let me denote this operator by letter omega. So omega is operator which takes V to V prime, where V prime is omega times V. So if omega is turning the ket V into ket V prime, what happens to the bra V? The bra V is converted into a bra V prime by application of an operator omega dagger. So the complex conjugate of the operator. The adjoint of the operator omega gives me omega dagger. And so you have to be careful. The omega is multiplying the ket on the when you are multiplying, operating the ket V with the operator, you have to write the omega on the left hand side. When you are doing the same thing with the bra vector, you have to write omega dagger on the right hand side of the vector. Then we define linear operators. Linear operators are objects which satisfy this relation that we have on the screen. That is, if I take a linear combination of V and W, then the result of the operating with the operator omega is going to be a linear combination, the same linear combination of omega V and omega W. So their coefficients have come out linearly. So these vectors and linear operators are abstract entities which do not depend on the coordinate system or basis. Given a certain physical space, there is a linear vector space associated with it, and it does not matter what are the coordinates you choose to define them, what are the basis vectors you choose. The vectors remain the same, but the components change when you go from one basis to another basis. Okay. So given an operator and a basis, so this curly bracket has n objects in it 1, 2, 3, 4, n, which are n vectors, which define the basis. And with this operator, I can write this operator omega into a matrix form. How do I do that? I apply omega to J, which was the unit.
Pardon, ma'am. You're not audible again. Kindly check it from your end, ma'am. क्या रिंग करना पड़ता है कैसे सब तो है
There seems to be some problem at her end. She will join again, I think. Manish ji, there seems to be some problem at her end. She is disconnected now.
Pardon, sir. Some connectivity problem is there.
Yeah, she is disconnected. She will join. She will join again.
Okay, okay. We have to wait. Yeah, ma'am is here. Reconnected. Yes, ma'am. Please, ma'am, unmute yourself. You are visible now.
I think I lost the connection. Can you hear me now?
Yeah, yeah. Now you are audible. Kindly
yeah, I'm sharing the screen.
Yeah.
Yeah. Okay.
Yeah, it is now visible. Same slide is there.
Yeah, sorry. Yeah. So, yeah, I have logged in from 2 devices so that I can see when I am logged out. Okay. Can you hear me?
Yeah, sure. You continue.
Okay. So I have defined what is called an operator. I have defined what is called a linear operator. And then I have defined the matrix representation of an operator. And now I am defining what is called a Hermitian operator. So operator is Hermitian if the operator and its adjoint are the same. So remember, adjoint was the operator which acts on the bra, and omega, that is omega dagger. If this operator and the operator that acts on the cat, which is omega, are the same, then it is Hermitian operator, and Hermitian operator will correspond to the Hermitian matrices. The matrix representation of a Hermitian operator is going to be a Hermitian matrix. Okay. So now we come to the main thing, that is eigenvalue problem, which is the basic problem in quantum mechanics, solving the Hamiltonian eigenvalue equation. So I have an operator, linear operator, which changes a ket into another ket k prime. Now there are certain kets, which certain operators, which will act on this ket and give you something which is proportional to the same ket. They will give you back the same ket or something which is proportional to that ket. Such kets are called the eigenkets of the operator. So if omega acts on V and it gives you some multiplicative, multiple of V, then you say that V is an eigenvector of omega with eigenvalue small omega. This is called the eigenvalue equation. V is called an eigenket of V of omega with eigenvalue V. If there are more than one eigenstate corresponding to the same eigenvalue, then you say that the eigenvalue is degenerate. So it is possible that there are two vectors which will give you the same eigenvalue on being operated by the omega, then you say that the eigenvalue is degenerate. In quantum mechanics, you are looking for Hermitian operators. Because the eigenvalues of Hermitian operators are real, there are some properties of Hermitian operators. I don't have time to do everything in detail. Basically, the problem in quantum mechanics is to find the observables which correspond to Hermitian operators. And when you make a measurement of that observable, what the values that you measure are going to be the eigenvalues of the corresponding operator. So with each observable, we are going to attach an operator. We are going to solve the eigenvalue problem for the operator. The eigenvalue problems, on solving the eigenvalue problem, the eigenvalues that I get are the results of measurement of that particular observable. So making a measurement amounts to solving the eigenvalue problem for the corresponding Hermitian operator. There are certain theorems which are used in quantum mechanics. The first one is that the eigenvalues of a Hermitian operator are real. So when if I want the operator to be associated with the observable, the operator should be a Hermitian operator because the quantities that I'm going to measure are going to be real quantities, and the result of measurement are the eigenvalues. Then the second is that to every Hermitian operator, there exists a basis which consists of its orthonormal eigenvector. It is diagonal in eigenbasis and it has eigenvalues as the diagonal entries. So we'll discuss more about this maybe next time or whenever the need comes. I think I can stop at this point. In a minute, 2 minutes, I'll take any questions that you have.
Yes, ma'am. It's a very nice description from the Swedenborg experiment, its analogy with the polarized light, and then coming to the bracket notations, matrix formations, their measurements. It's a very elementary basis you have started and shown the whole set of rules and theorems for structuring the tomorrow's lecture. I would like, I am seeing as such no questions, but I have a, very strong zeal to know how.
Hello? Sir, I can't hear you.
Hello? Sir, can you repeat the question? Hello?
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 Hello.
Can you hear me?
Hello.
Just a minute. Can you hear me?
Hello.
Can you hear me? Am I audible? Hello? Hello? Can you hear me? Hello? Okay, so I could not hear the question. No, I did not perform the experiments, but the experiments have been done. As I said, I will send you the references of all the experiments which have actually been performed in the labs. Dr. Singh, I could not hear your question. There was some problem. So I could not hear your question. Can you please repeat it? So we can form a email group and where we can discuss even if there are more questions. Dr. Singh, I can't hear you.
Yeah, ma'am, we have just lost the connection. I have just joined it with my mobile. Am I audible? Am I audible, ma'am?
Yes, you are audible.
Okay, ma'am. So,
Okay. Yeah, I can hear you now.
No, I can't hear.
We have just completed the lecture.
You can write on the chat box.
Yes, sir. Can you write on the chat box? I can't hear you. I can hear the other people, but subsequently go in the field of quantum mechanics. Yes, physical significance of eigenvalues. You can hear me, right?
Yes.
So physical significance of eigenvalues and eigenvectors. Eigenvectors belong to the. So we'll see tomorrow that in quantum mechanics, when we said that we have to develop a new formalism, we define the system with the state vector, and the observable quantities are going to be operators, and eigenvalues are the results of the measurement. So we'll relate tomorrow everything that we have done today with the physical quantities which are needed to develop the mechanism, the formulation of quantum mechanics. So eigenvectors are states. Eigenvectors are a set of states over which you can expand any given state. So a general state in quantum mechanics can be written as a linear combination of eigenstates of a given operator. And the coefficients in the expansion are the probabilities that will be probability amplitudes that if you make the measurement, you will find a certain value. So the act of measurement brings the system down to one of the eigenstates. If you are measuring some operators, yeah, I'll surely share the PDF. I've just seen a couple of typos. I'll correct them and share the PDF. So I was asking, can we have an email group over which people can ask questions? And I'll share the PDF on that only. So again, we are going to talk about conjugate of variables tomorrow, which are Fourier transform of each other. Okay. So we are going to we'll develop the coordinate representation of state vector, quantum representation, and we'll see that they are actually Fourier transform of one another. So for going from one basis to another basis of conjugate variable, you need use the Fourier transform. And then there's a question about research work currently going on in the field of quantum mechanics. So I must make a confession that I'm a particle physicist. I don't do research in quantum mechanics. And Dr. Pathak, who will give you a talk in the afternoon, will probably be able to tell you the latest that is happening in the field. If you are talking about two different properties of the same particle, the question is if one's particle properties get disturbed while finding about another particle's properties, can we don't find their properties simultaneously? I think if you are talking about the Stern-Gala experiment, we are talking about the properties of the same system. So if you are making the measurement on the same system but different properties, okay, then there are situations in which you can measure both of them simultaneously. There are situations in which you cannot measure both of them simultaneously. So we'll discuss tomorrow what kind of variables can be measured simultaneously and what kind of variables cannot be measured simultaneously. Your question is one particle's property and another particle. So that means you are making measurement on two different systems. And those in general are independent. But if there is some kind of coupling between the two, if the particles are related to one another in some way, they are bound state or something, then then they can disturb. Whether you are considering the two particles as a single system or two different systems. Can we control the dual nature of matter? No. That is the whole point of this series of lectures, I think, and the afternoon also you'll see probably that this uncertainty is inherent in nature. So there's no way you can make more and more precise experiments to be able to. It is not a limitation of the experiment that you cannot measure X and P simultaneously. It is a property of the nature itself. So there have been theories which we'll talk about on the third day, which Einstein proposed and people worked on them, which are called hidden variable theories, where they thought that probably our theory is not complete, and if we have a better theory with more variables, we'll be able to tell definitely what is the result of an experiment. However, that does not happen. So such theories have a lot of inconsistencies. So this is inherent in the nature of matter. Can one of you unmute yourself and speak so that I know that my audio is working fine? Say
Yes,
something.
ma'am, your audio is working fine.
Okay, fine. Because everybody is writing in the chat, so I just got.
Ma'am, I also want to ask you one thing. How can we apply for fellowships in different universities? Because I am in first year and I want to go for research in particle physics only. Ma'am, can you help me?
So if you want to do in India, then there are a lot of research institutions in India which have their own entrance exams. For doing PhD in a university, you have to clear a UGC NET exam. If you want to do PhD in IITs or ICERs, then you have to pass the GATE exam. And after that, you apply, depending on the rank in these exams, you apply to the institute of your choice. And so if you are interested in particle physics, there are a lot of good places in India. If you want to do PhD abroad in USA and some other countries, then you have to appear for GRE exam. And you need to have a good recommendation, which is very important. And in Europe, the GRE is not needed, but they always look for whether you have done any research project during your MSc. So you can start working on some advanced research problem in MSc itself or after MSc to improve your CV. So are there any more questions? I don't see any of the organizers here. Okay, you are in first year of MSc? Bachelor's. Okay, so you have a long way to go. You have to do MSc, good MSc from somewhere. And you should always try looking for summer projects. For example, the science academies have a good summer student program. You can apply to them. Tata Institute of Fundamental Research has a summer program. Almost all the places have a summer program. So try
Yes, ma'am. That's what I was asking. I have applied for TIFR this summer, but for something else, I was asking. Is there anything else?
There is a Science Academies summer student program. Have you looked for that? Go to the Indian Academy of Sciences webpage. And they have...
The website shows error 404. I have looked through it.
Okay. Then you can write to individual faculty members. Just go through the list of institutions, and if you find somebody whose work you find interesting, you can just write an email and say that I would like to come and spend the summer with you.
Okay, ma'am. Yeah. I will do surely.
But your basics should be very firm. That is the first thing.
Yes, ma'am. I am trying to do.
You are in Christchurch College?
No, ma'am. I am in Delhi University.
Okay. Delhi University has a nice group.
SGTB Khalsa College. I am working under Dr. Shukanto Datta. You might know him.
I know. Yeah, sure. So can we stop now? Dr. Dwivedi is not there. Okay, then we'll stop here. You have a session in the afternoon also. We'll continue from here tomorrow.
Good afternoon, friends. So we are going to start with the second session. I will say the first exciting session of quantum mechanical applications. So this lecture will be delivered by, as you all know, Professor Anirban Pathak, Professor, Department of Physics and Material Science and Engineering, JIIT, Noida. Friends, before I invite him for lecture, let me give you some brief out about him. Professor Anirban Pathak is a theoretical physicist. He did his PhD from Visva-Bharati Santiniketan and postdoctoral from Freie University Berlin, Germany. He joined Jaypee Institute of Information Technology, Noida in 2002 and working as a professor in Department of Physics and Material Science and Engineering there. He is actively involved in teaching and research related to several aspects of quantum optics and quantum information with a focus on quantum cryptography. He is a fellow of the National Academy of Sciences, India, Nasi Prayagraj. He is a fellow of Institute of Electronics and Communication Engineering, IETE, and Optical Society of India, OSI. He is a visiting scientist at Pathak University, Czech Republic. He is also a member of editorial board of Quantum Information Processing, Springer Nature. At present, he leads a research group focused on quantum optics and quantum information with specific interest on quantum cryptography. He has completed several DST and DRDO funded projects, and present he has several ongoing projects funded by India and abroad. He has written 5 books, 6 chapters in refereed books, more than 100 papers in the reputed international journals, and many in national and international conference proceedings. He has guided 6 PhDs and a number of postdoctoral fellows. He is a recipient of 2017 Sri O.P. Bhasin Award in the field of electronics and information technology. I welcome you, sir, to this workshop virtual platform and request you to share your great knowledge on the topic Introduction to Quantum Gates, Quantum Circuits, and Quantum Computers. Welcome you, sir.
Thank you. Thank you, Dr. Dwivedi, for a relatively long introduction, but we will move to the main topic, but I guess probably more participants will join because the number is still low compared to what was in the previous session. So I start slowly and it will be a bit different from the usual session. I'll expect some interaction in the middle also, and I may ask you to answer certain things, especially the student participants, that what will be a state after a particular gate and things like that, that will clarify actually that what's happening. So before I start, a few words, there are much discussion on quantum supremacy, and what quantum supremacy is, like a quantum computer can do some task faster than any of its classical counterpart, or it can do something which can never be done in the classical world. So establishing that is difficult for various reasons. There is noise, the quantum system interacts with the environment and it collapses. It does not remain in the desired state for long, so we cannot make a big quantum computer. But if we can really make a big quantum computer, many things will change. So with this talk is planned in such a way that it will be a bridge between the last 2 talks, which Professor Misra has given, and something I will mention which will be elaborated in tomorrow's lecture of Professor Misra, because those will be required, and this will help you to understand next talk of Aditi Day and the next 2 lectures, next 2 application lectures in tomorrow, like your L7 and L8. So this is going to be a bridge for next 3 lectures on communication and the 2 foundation lectures which has already happened. So I'll start with simple idea of quantum gate, and then how it goes for quantum circuit, and then how we make quantum computer. So primarily, if you look at your computer, the computer through which you are attending this lectures, so if you want to go in the elementary level, so what is there? So there are ICs, so integrated circuits, and if you break those circuits, then there are flip-flops, and if you break those flip-flops, then there are transistors. So at the elementary level, there you know that NAND is a universal gate. So there are gates, and the gates are made up of transistors. And the problem is, these transistors are reducing in size. So there is something called Moore's law. So Moore's law states that number of transistors per unit area in IC doubles in every 18 months. So if it keep on doubling, then the size will keep on reducing. And at a given time, the size will be so small that quantum tunneling will start to happen. So you cannot go beyond that. So then one option is that you are happy with that and you skip that, well, this is the end and then I cannot have a better computer. And one option is that you exploit the quantum mechanics itself. So how the quantum mechanics is exploited? What is quantum gate? Is there any other kind of gate than the conventional gate you know? So I'll start from that and gradually I'll combine those gates to form circuits and then I'll tell you how the quantum computer works and where is the physics. So let's start with the presentation. So can you see the slide?
Yeah, it's visible, sir.
Okay, thank you. So I will start with the basic idea of quantum mechanics once again. So this was summarizing the certain things which has already been told in previous lecture. So for every physical observable, there is an operator in quantum mechanics. So the first question that should come in your mind, what is physical observable? So anything that you can observe here means measure. Anything that you can measure is a physical observable. So corresponding to that, in quantum world, there is an operator. So what you can measure? You can observe me, you can see me, but you cannot measure me. So I am not an observable. But you can measure my age. So time is an observable. You can measure my position. So position is an observable. So you can see a movie, but the movie itself is not an observable. You can measure the duration of the movie. So time is an observable. So physically, in classical world, whatever you can measure, those are observable, physical observable. Corresponding to them, there is an operator in quantum mechanics. So for position, there is operator, position operator. For momentum, there is operator called momentum operator and so on. The operator satisfies the eigenvalue equation. So what is the eigenvalue equation? Eigenoperator A operates on, say, eigenfunction f of x and gives you lambda times f of x. So f of x returns back with a constant multiplied by that, and that lambda is called eigenvalue. A is called eigenoperator and f of x is called eigenfunction. So the operator satisfies eigenvalue equation, where eigenfunction is the wave function in this particular case, and the eigenvalues are discrete values that a measurement can yield. So what does it mean? Suppose you want to measure a momentum. So momentum operator would work on the wave function of the system and give you the momentum eigenvalues times the wave function. So those are the values a real experiment can yield. So suppose you know that in a hydrogen atom or in an energy problem, that energy operator operates on the wave functions and it gives you the energy eigenvalues. So those are the values only you can achieve in the experiment. So a hydrogen atom can be in the ground state, first excited state, second excited state. It cannot be somewhere in the middle. So suppose E0 is the value of the ground state, which is minus 13.6 electron volt. The E1 is that divided by 4, so minus 3.4 electron volt. So it cannot be somewhere in the middle. You cannot have a state at minus 6 electron volt. So this can be seen in various ways. Means you know that from de Broglie wavelength you can come to this just by solving. From de Broglie you can find out this energies. Means solving Schrodinger equation you can come here. So energy is quantized. So that means that the operator or Hamiltonian operator operates on wave function and give you the energy eigenvalues. The word quantum means discrete. So since all energies are not allowed or all momentum are not allowed, only certain momentum values are allowed or certain energy values are allowed. So that's discrete and that's why it's called quantum.
So what I was telling in the morning, since the certain energy is allowed and others are not, so that's why there is a band gap. If all energies were allowed, then there was no band gap. And if there was no band gap, there was no semiconductor, no transistor, no quantum, no computer. Forget about this mobile phone, iPhone, online classes. So all these are possible. The understanding is possible because of quantum mechanics. So to understand the band, you need to solve chronic penny model. But this is something which is taught in the professional courses. Formal courses of quantum mechanics, and you must be familiar. And our task is not to discuss those textbook material, but I just want to draw your attention that even the laser. So if you look at a laser, two-level systems cannot work as a laser. So you need at least a metastable level, and you must be a three-level system or four-level system, three or more. So for the operation of laser, you need discrete energy level. So whatever modern technology you see, semiconductor and laser play a very crucial role, be it medical surgery, be it communication, be it military warfare. So, and all these are possible because of quantum mechanics. So these are the product of first quantum revolution. In the beginning, early 19th century, early 20th century, when Schrodinger equation was built and solved for many systems, we understand the systems better, and we applied for making these transistors and lasers and such applications. But quantum mechanics has some weird properties. So those weird properties have not been used, and without knowing them, you can understand pretty well some kind of moderate knowledge of quantum mechanics. You can survive with these things. But now we are in a situation where we want to apply the weird properties of quantum mechanics. So let's know what is those. Operators corresponding to physical observables are Hermitian to give real eigenvalues. So this is important, that if in a real systems, when you do a measurement, I told you that those are the eigenvalues which will become out. You measure something, you measure my position, you measure the distance between Calcutta to Delhi, you never get 3 plus 4i in any unit. Always you get a real number. So measurement outcome will be real, and that requires that the corresponding operator has to be Hermitian. So here is a point that most of the books, what has been taught as the definition of Hermitian has been taught as self-adjoint. So if you write H is equal to H dagger, that's the definition of self-adjoint. Self-adjoint is a stronger criteria than hermiticity. So all self-adjoint operators are essentially Hermitian, but there may be Hermitian operator which is not self-adjoint. But time evolution of a quantum state is described by an unitary operator, but measurement operators are non-unitary. So you have three kinds of operators. So measurement operators are different, which is non-unitary. You have a unitary operator which describes time evolution. I'll return back to it, and you have Hermitian operators for physical observable. So what is those measurement operator? So measurement operator looks like this is called Kate. So the whole thing is called bracket, and if you divide into two pieces, the first right hand side is Kate, left hand side is bra. So this is defining a state vector. So Kate I, bra I is the ith measurement operator when I am doing measurement in a basis where I is an element. Now this will come back later. This is describing Schrodinger equation, Heisenberg uncertainty principle. If there are two measurement operators which I have written as M0 and M plus, and they don't commute, then I cannot measure them simultaneously with arbitrary accuracy. So Heisenberg uncertainty principle in general is that if there are two operators and they don't commute, I cannot measure the corresponding physical observable simultaneously with arbitrary accuracy. So that's the general statement. A specific statement is that you cannot measure position and momentum in the same direction at the same time with arbitrary accuracy. Okay. Now, what are the operators which you need to know? And these are common. You just need to know the position operator X, momentum operator P, which is minus I h bar del del X, energy operator E, which is I h bar del del T. But this is something which you remember, and then life is simple. And we mentioned that Hamiltonian, H operating on Kate Xi. So this is supposed to be your wave function, and this is a eigenvalue equation that H operating on xi gives you E xi. So E is the eigenvalue, these are the energy eigenvalue. So when you write Schrodinger equation, you don't write the operator in both sides. Either you write operator for E or you write the operator for the Hamiltonian, which you write like P square by 2m, then your P square become minus H square, H bar square by 2m del 2 del x2 plus Vx operating on K xi gives you E xi, or you write H K xi is equal to IH bar. So this IH bar del T is the operator for energy. So you don't write simultaneously operators in both sides. Now, when you write the operator form of H, that does not have any time dependence, so that's called time independent Schrodinger equation. And when you write in this form, this is called time dependent Schrodinger equation. So if you solve this time dependent Schrodinger equation, it's a straightforward thing because there is a delta term and there is a del xi by xi. So del x by x, if you operate, it will become log x, and then you can simply write that K xi t is equal to e to the power minus IHT by h bar xi 0. Well, so this is simple. Now look at this. So we have already mentioned that the Hamiltonian is the physical operator corresponding to energy because it's giving energy eigenvalue. So this has to be Hermitian. So if I consider that this operator, which is operating on xi 0, K xi 0, is U, then what is U dagger? So if I want to take U dagger, then I will become minus I. So minus and minus will make it plus. H will become H dagger. So this H dagger is equal to H because the H is Hermitian. So that will make U dagger is equal to e to the power IHT by h bar. So only change in the minus. So U dagger is U inverse. And if it is so, if you multiply with U, then U inverse U is equal to identity. So U dagger U is equal to identity. Does not matter whether you are multiplying it from left or right. That's the condition of unitarity. The condition of unitarity is that U dagger is equal to U inverse. Whereas the condition of self-adjointness was U dagger is equal to U. So if there is an operator which is both unitary and self-adjoint, then that will be self-inverse. U represent a unitary operator, and this is what we understand as a quantum gate. So why is it a quantum gate? So that's the first question. So what is a gate? A gate is something which uniquely map an input state into output state. Think of a NOT gate. It will always map 0 into 1 and always map 1 into 0. So now, if I fix the input state xi 0 and I fix the Hamiltonian H, which describes a particular kind of interaction, and T, where T is the time. So if the Hamiltonian or the system and the time of interaction is fixed, then we have a fixed unitary operator which will always map a K xi 0 into a particular K xi t. So that's what a gate does. That's what a gate does. A gate simply maps an input state into an output state, and as it is doing that, so this is a quantum gate. So what have we learned? Any quantum interaction, if we can control it for a fixed time, so the interaction will map unique input states into unique output states, and that I can view as a gate. So a quantum gate is simply an interaction Hamiltonian which is operating for a fixed time t. Okay. So we'll give many examples, but keep this in mind that this is my quantum gate, and a quantum gate is a unitary operation. So I describe the same thing once again. The U dagger is equal to U is unitary, and U represents a unitary operation, and this is what we understand as a quantum gate. So the gate is reversible in the sense that if you can take from this gate, if U inverse exists, because U dagger is U inverse and U inverse exists, if U maps get xi 0 to xi 2 t, then you can apply U inverse and come back to xi 0. So this is a reversible gate. Whereas you think of, apart from NOT gate, any classical gate that you know, the traditional gates which you know are AND gate. You have 2-bit input and you have 1-bit output. So you cannot construct the input from the output. You think of NAND gate, OR gate, NOR gate. In all these cases, there are 2 input bits and output is only 1 bit. So input you have 4 possibilities, 0, 0, 0, 1, 1, 0, 1, 1, and input you have 2 possibilities, only 0 and 1. So you cannot construct the output input from the output uniquely. So they are irreversible gate. But quantum gates are essentially reversible. So what is it? Implementation will come to that via Landauer principle. But before that, we just want to mention that there are three kinds of logic gates. One is the classical traditional gates, irreversible gate like NAND or NOR. So output cannot be used to construct input uniquely. If there is a one-to-one mapping, one-to-one and on-to, so there is a bijective mapping that each output is connected to input, and you can from output you know which input it was, then it's called a reversible gate. Or from the output you can come back to input. So NOT gate is reversible in any case, because if you see the output is 1, then input is 0, and input is 1, then output is 0. So then there are some other gate called C0, it's called control NOT. Sorry, this is not CONT, this will be CNOT. So I'm coming to what is control NOT gate later. There is some 3-qubit gate, Trafoli and Fredkin. Output can be used to construct input uniquely. Input-output map is bijective. So these gates is achievable in classical world too, but soon people realize that quantum gates means initially there is a principle called Landauer principle which showed that to erase a bit we use at least kT log 2 amount of energy, where k is Boltzmann constant. So if I use, instead of irreversible gate, if I use reversible gate, there will be energy saving. But soon people realize that the quantum gates are always reversible, but the advantage is not actually in the energy saving. So for example, C0 gate can be in both classical reversible as well as quantum. But in classical reversible, the purpose is to save energy, whereas in quantum it can do magical things because superposition is allowed. Since superposition is allowed, superposition of state is allowed, so the output of the gate can produce some states which does not have any classical analog, like entangled state. So that will be described later. So superposition state can be present in the control bit, so output can be entangled. So that makes quantum gates different from the classical C0 gates. So now I start from a very basic, absolute basic. So this is the AND gate, and this is a NOT gate. So what does the NOT gate is doing? If you give A, it is always giving you A bar. So the gate is actually computing a function, f of x. So you give x, it gives you fx. You give a, and what is the function here? F of x is x bar. So your NOT gate is making a computation. F of x is equal to x bar, where x is input, x bar is the output. So you give x, it computes a function f of x and function f and gives you the output as f of x. Similarly, in AND gate you are giving ab, and this is the function of ab, which is the output. So what I want to stress here, that every gate computes a function, and every gate computes something. So it's doing computation. So that means a gate is a small computer. So when I make them, connect them, the output of one gate with the input of the another, and then so on, then I have a bigger circuit. So bigger circuit is doing bigger computation. And now you add many such circuits, then you have a real computer. So each gate is doing some kind of computation tasks. It's computing some function, and together they are giving me the usable computer. So one point, this AND gate is irreversible, whereas, and it throws away one bit, so there are 2 bits, but here is only 1 bit. And a gate computes a function, a gate uniquely maps an input state. That's the way I define quantum gate. So these are the reversible gate. This is AND is irreversible and NOT is reversible. So now we come to Landauer principle. So Landauer principle, these are the starting points of looking at quantum computing in the present perspective. So Landauer's principle of reversible logic, and the idea is that if I erase a bit, then we use at least kT log 2 amount of energy. So where from this come? I can give you a hand-waving argument. So you all know Boltzmann's entropy S is equal to K log omega. So where omega is number of microstates. So when you have two microstates, two possibilities, so that defines a bit that you have two possibilities, and then you write that entropy is S is equal to K log 2, and then you have only one possibility, so you erase the one of the possibilities and then bit value. So there is only one possibility, then you know everything, so there is no information. So okay, to understand that you need to know something else also. So is information physical? The information is physical. It's a physical quantity, and that's why laws of physics are applicable to it. So how do I understand that information is physical? First, you try to dissociate information from physical objects. So when I am talking, I am creating a wave, that wave is going and creating a vibration on your ear membrane, and that's why you can listen. So that's a physical process. When I write on board, with the molecules of the ink, I paint the molecules of the board. That's why you can see what I am writing. So that's how information storage in hard disk is in terms of magnetic dipole. So if it is oriented in this way, I call it 0. If it is oriented in the reverse direction, I call it 1. So everything, information processing, information storage, information communication from one place to other place, everything involves a physical process. So information is physical and laws of physics are applicable to information. A nice example. In the special theory of relativity, I tell you that the velocity of light in vacuum is the maximum possible velocity. For what? Who cannot travel faster than light? Of course, phase velocity can be faster than light. You know that phase velocity times group velocity is c square. So, information cannot travel faster than c. So that's laws of physics which is applicable to information. When I talk about black hole, I tell that nothing can come out of black hole. Then how do you know that black hole is there? Information comes out. So laws of physics are applicable to information. So if it is a physical quantity, there must be a measure. So the first such measure was introduced by Shannon, and it's called Shannon's entropy. So Shannon's entropy defines a bit. So this is defined amount of information that you know from an event. So there are event with 6 outcome or 7 outcome or 8 outcome. So there is a probabilities like P1, P2, P3, P4 of getting different outcome, and you are ignored about it. Then your ignorance is measured in terms of Shannon's entropy as summation minus Pi log Pi. So sum over I minus Pi log Pi. And this log is base 2. So when you know everything, there is only one possibility. Then it is 1 log 1 and 1 log 1 is 0. So when you know everything, then you learn nothing. You know that. What is your name? So if I tell you your name, you learn nothing. So what is information? Information is what you don't know. Information is your ignorance before doing an experiment and the knowledge you gain after performing the experiment. Okay. So now you think that there were two possibilities. So there are two microstates. Then the entropy was kT log 2. And when there is one microstate only, then you know everything. There is no uncertainty. Then it's log of 1 is 0 in any base. So delta S become kT log 2. And delta S is dq by t. So the dq or change in energy become kT log 2. So if you can follow, it's okay, but just take it as granted. Then otherwise, that at least kT log 2 amount of energy is required when I apply a AND operation. Because there were 2 bits and now here is 1 bit, so 1 bit is erased. So people thought that if I do for reversible logic, then I will be able to save a lot of energy in VLSI and such implementation. But soon it is realized that the amount of connecting wire is a lot. There are kilometers, and there is a joule setting, and because of the joule setting, the loss is much more than this kT log 2 amount. So this is not going to help a lot. But reversible logic is a circuit, is a thing in itself. So, but people realize then that quantum mechanics also means quantum gates are also reversible, and then from reversible computing was an intermediate step from the classical traditional computing to quantum computing. And here is an abstract machine called Turing machine. So first people introduced Turing machine, and then gradually we move to quantum Turing machine or physical Turing machine. So, okay. So whatever you do in an abstract machine, in a real machine, you have to realize those with a gate. So here are some examples. So since the gates are reversible, so as many lines will be there in the input, that many lines will be in the output. So if this is a n-bit string, this side will also be an n-bit string, and there should be 1-to-1 mapping. So this gate, this is called control, with this black circular box, and this is a NOT. So this is control NOT. So what does it control NOT means? If the control is 1, the target will flip, or a NOT gate will work on the target. And if control is 0, nothing will happen. So this is a 2-qubit gate. Now there is a control NOT. So this is called Toffoli. So if both of them are 1, then there will be a flip operation or a NOT operation. If any of them are 0, then it will not work. So if you combine such gates, then what you get is a circuit. So this is a circuit. So there are different models of universal gate. So there can be NCT, NOT C, and Toffoli. There can be NCT. So why you have to restrict to a gate library? If not, the circuits are measured with the number of gates. Suppose you are doing addition and I am also doing addition. Your circuit has less gate and my circuit has more gate, then your circuit is better. But unitary times unitary is always a unitary. So you can combine these two and then you can tell that I have a new gate. So unless you are doing measurement, everything is unitary. Unitary multiplied by unitary will be unitary, and you can claim that you have a smaller gate and you have a new gate. And you have only one gate, which is doing everything. So that cannot be compared. Apple cannot be compared with Orange. So you must restrict to a gate library. A gate library is a universal library through which you can do all kinds of operations. So in a traditional reversible circuit, irreversible circuits, NAND forms such a gate library which is universal. Here we have written something. In quantum gates, you need at least one 2-qubit gate and all possible rotations, that is single qubit gates. So if you can make a CNOT gate and all the single qubit gates, that will be considered as your universal gate library. Now we have to tell a bit on linear algebra. So bracket notation has already been used in the previous lecture. So I'm quickly telling you that normally you work in 3 dimension and you have 3 vectors A1, A2, A3, and then so you write suppose a vector A as A1i, A2j, and A3k. So there are many ways that you can write this. So one option is that you write this as A1, A2, A3. One option is that you write it like A1, A2, A3. And if this is the notation, then the unit vector I is along x direction, which is a unit projection along x direction. So that is 1, and 0 projection along yz. So this is 0, 0. So this forms, this I is 1, 0, 0, j is 0, 1, 0, k is 0, 1, 1. So this is the notation which I am following. And this forms the basis elements. Now, if I work in 2 dimensions, then I'll have 2 vectors that 1, 0 and 0, 1. So I normally call one of them, the first one as gate 0 and the second one as gate 1. So without going in further detail, we are just introducing the bracket notation briefly. The whole thing is bracket. So this side is called gate and this side is called bra. So this is bracket. So when I read this one, then I will read it like gate B. This is gate A. So this is, with this you can define an inner product as well as outer product. Inner product is just like dot product, and inner product is defined in this way. So your state vector is written like a column matrix B1, B2, Bn when it is n dimension. The corresponding, so this is the gate. Corresponding bra is a row matrix A1 star, A2 star, An star, and if you multiply, what you will get is this, and that's your inner product. So inner product, suppose you are this n cross, sorry, this is 1 cross n, 1 row n column, and this is n cross 1. So this will be 1 cross 1, that will be a scalar number. Inner product will give you a scalar number. Whereas outer product will give you, so outer product you just keep B1 in this side and take A1 in this side, then this will be a square matrix. So outer products are defined as gate A, bra B, and outer products are useful for many purposes, including defining the gate. So suppose I am defining a NOT gate, I can define it like gate 0 bra 1 plus gate 1 bra 0. So if it now work on gate 0, so what will happen? The NOT operating on gate 0, so when it work on gate 0, this bra 0, gate 0 will be because ket0 is a state vector which is normalized, so that will be 1 and I will have 1. And inner product of 1 and 0 will be 0, so they are orthonormal, so this will be 0. So this is, so not operating on 1 will give you 0, and not operating on ket0 will give you ket1. So you can write in terms of outer product. So how the outer product is written? If you know the map that this input state goes to this output state, then you can write that summation over I, ith output in ket and ith input in bra, and sum over I. So output I, ket of output I, bra of input I, and sum over I, you will get the gate. Well, so now we talk about a qubit, a bit. So a qubit, a bit is made up of two-level systems. So what is the difference? Suppose there are nucleus and there is an electron here and the electron here. So the electron classically can be either in the ground state or in the fast excited state. So that is a bit. A bit is any two-level system. A qubit, in contrast, can be superposition of this state. So unless you do a measurement, you don't know whether it belongs to ground state or excited state. The moment you do a measurement, it collapses to one of the possibilities. And this probability superposition is written as alpha ket0 plus beta ket1. And that defines that the two-level systems defines my qubit. And this is the space which is in C2, because alpha beta can be complex. So this is a two-dimensional complex Hilbert space, which satisfy mod alpha square plus mod beta square is equal to 1. This is the total probability. So mod alpha square is the probability of getting it 0. Mod beta square is the probability of getting it at 1. Now I can start with a single photon. There is a one photon and there is a beam splitter. So the beam splitter splits it into two pieces, means it's simultaneously in this path which I call 1, this path which I call 0. So if the beam splitter is 50-50, this is 1 by root 2 ket0 plus 1 by root 2 ket1. If it is 60-40, then it is 0.6 root over ket0 plus 0.4 root over ket1, root over 0.4 ket1. So then you can define with different probability, you can define different qubits. Now, if I put a detector here and I put a detector there, that will make the measurement. So on measurement, this qubits will collapse either to 0 or to 1. So, and now I make a product that if I start with a 50-50 beam splitter, so I have a state which is half of the time here and half of the time here, and then I put two detectors. So half of the time this detector will click, half of the time this detector will click, and they will click randomly. So on measurement, a quantum state collapses randomly to all possible states. So when it's a possibility between 0 and 1, while you do measurement, it will collapse either to 0 or to 1. And where it will collapse, nobody knows. So that's a completely random, that's intrinsically random process. And this intrinsic randomness helps me to generate quantum random number generator. So if I now put two detectors, they will randomly click on 0 and 1, and that will give me a true random number generator. So that's a product, ID quantic cell, and it's called quantis. So why classically you cannot have a quantum random number generator? Classically you cannot have a true random number generator. You think of a specific case that you are tossing a coin. If you know what force you are giving, where it's going, then how much force, how much is the air drag, what is the gravity, then you can actually calculate where it will fall and what will be the output. So it's a set of Newton's equation which you have to solve, equation of motion which you have to solve, and you will know the output. So that's not, before we are ignorant of many parameters, we are not predicting it, but it's not really random. Whereas quantum mechanics randomness is intrinsic. I often tell in my class that even Shah Rukh Khan and Amitabh Bachchan does not know what's going to happen. So not even Rajnikant knows what is going to happen. It's a complete collapse on random. So now, summarizing what I told, the ket0 corresponds to 1, 0. So that makes your life simple for doing calculations. Ket1 corresponds to matrix 0, 1. And my qubit is alpha 0 ket0 plus beta ket1, or alpha ket0 plus alpha 1 ket1. So I multiply this, then this will become alpha 0, 0, and this will become alpha 0, alpha 1, 1, and so this is my matrix. So check the effect of NOT gate introduced in the context of outer product. If you apply NOT gate on this qubit, then it will become alpha naught ket1 plus alpha 1 ket0. Now I want to introduce a new kind of matrix product. So we have talked about inner product, we have spoken about outer product. Now I want to tell you about something called tensor product. So if any of you are familiar with Mathematica or such software, so in Mathematica, this is inbuilt and this is written as Kronecker product. K is capital, P is capital. Kronecker product will do this. So this matrix multiplication is like this. AB, tensor product CD, then the left-hand matrix, you take the first element and the entire right-hand matrix will be multiplied. So we don't write this. This is for convention. I mean, this is for your easy understanding that A times C, then A times D, then B times C, B times D. So you say this was in a space C2 and this was also in C2. So this was a complex two-dimensional space. This is a complex two-dimensional space. But when they take a product, I'm in four-dimensional space. So this is how Hilbert space goes. So if you have a two-dimensional space gives a qubit. Another two-dimensional space you have a qubit. But when you make a two-qubit system, it is in four dimension. Now if you have an n-qubit system, this is 2 to the power n. So n two-level system, to describe n two-level systems, you need a space which is 2 to the power, a basis vector which is 2 to the power n cross 1. So if n enhances, suppose n is 100, you have 100 qubits. Then 2 to the power 100 is a huge number. So the problem is that our Hilbert space, or the space in which I have to work, increases very fast in this manner. And that's the problem, that solving quantum thing is not possible in the classical world. In quantum mechanics, the Hilbert space enhances like tensor product. And 2 to the power 100 is huge, means 2 to the power 100 is so much, means you think that you want to solve a uranium atom and each new everything, means every proton, electron is a qubit, and just consider that they are two-level system. So you have 235 such things, and 2 to the power 235 is bigger than the total number of atoms in the world. So even if each atom does a computation, means works for your computation, then also you will not be able to mimic uranium's dynamics in your classical world. So only a quantum system can simulate a quantum system, and that's the reason we need to build quantum computers. Classically, you cannot simulate a quantum computer, a quantum system. Okay, so explain it more. Some tensor product facts. So suppose you have a 2 cross 2 matrix and you multiply with another 2 cross 2 matrix. So the left hand side you take A11 and multiply with the entire matrix. So you have A11, B11, A11, B12, A11, B21. So you get this kind of matrix, which is 4 cross 4. So for a 2-qubit system, you will have this kind of structure, and the gate will be a 4 cross 4 matrix. So if you really want to simulate in your computer, firstly, the collapse on measurement cannot become simulated in your computer. But if you just want to see that how a circuit evolves, how a quantum state is going stepwise, that you can do. But when you have 10 qubit, then 2 to the power 10 is like 1024. So your gates or the circuit matrix size will be 1024 cross 1024, which you can to some extent simulate in your laptop. Even you can do 11 qubit, 2048 to 2048. But the moment it becomes 4096, your laptop will not do. You may have to go for a workstation. But you just increase one more qubit, even your workstation will not do. Then we have to look for sparsity in the matrix, and then Atos has a classical computer which is very big and sold to C. in Pune. They can handle something like 35 qubit lines. Anyway, this I will skip. So now the idea is that a qubit is a two-level system. So you have to explain it in a two-dimensional Hilbert space, and you can write it like a matrix 1 0 as ket 0 and ket 1 as matrix 1 0. Sorry, 0 1. Now, a gate is something which maps the input state into output state. So one possibility is that you remember this ket 0 and ket 1. So you can write corresponding bra 0. So what will be bra 0? Bra 0 will be a row matrix 1 0 and bra 1 will be a row matrix 0 1. So you write those bra matrices and put it here. And then you will get the matrix for NOT gate, so which I am writing here. So matrix for NOT gate is 0 1 1 0. So you can easily see that if it works on the matrix 1 0, so you multiply in this way. So first term is 0 multiplied with 1 and 1 multiplied with 0 gives nothing. So the first column, first row becomes 0 and then you multiply 1 0 with 1 0, so you get 1. So this operating on your gate 0 or the column matrix 1 0 will take you to 0 1, and similarly operating on 0 1 take it to 1 0. So you do it yourself in your copy and check. So this is the matrix representation of the NOT gate. So a gate can be written in, and this is nothing but Pauli matrix X. So Pauli matrix will be taught in details in Professor Misra's course. So I'm not going in detail. So what does it do? This flips a bit. It makes 0 to 1 and 1 to 0. So what does sigma y do? So this is the y Pauli matrix. So to take care of I have introduced another iota. So 0, 1, minus 1, 0. So if you apply it on gate 0, so you see, so first let me see the Z gate. So what does Z gate do? This is 1, 0, 0, minus 1. That's the Pauli Z matrix. It's operating on 0. You operate on gate 0, which is matrix 1, 0. You do the matrix of multiplication, you will see 0. If it operates on 1, then this term will come into the picture and then it will make it minus 1. So 0 remains 0, 1 goes to minus 1. So if you start with alpha 0 plus beta 1, this will go to alpha 0 minus beta 1. And similarly, there is an identity operator which does nothing. So this flips the phase, relative phase, this flips the bit, and this does both. 0 goes to 1 with the additional phase. So as if you first apply X gate, then you apply Z gate. So IY is equivalent to XJ. So these are the 4 operations which are very important, and these are quantum gates. So Pauli operations taught in the foundational ideas of quantum mechanics can be treated as quantum gates. Now, they are not the only gate. There are other gates also. So Z does a fetch flip, X does a bit flip. Now, if you do X and Y, you get Z. But these are circuit identities that this side is equivalent to this side. So there is another important gate in terms of Hadamard. It's called Hadamard gate. Hadamard gate is written in matrix in this way. So what it does? So if you again apply on 0, which is 1, 0, so that will take you to 1 by root 2, 1 by root 2. That means equal superposition of 0 and 1. So 1 by root 2 gate 0 plus 1 by root 2 gate 1. So 0 goes to 1 by root 2 gate 0 plus 1 by root 2 gate 1. And that has a name that's called plus state. And if it operates on 1, then this minus sign will work, and this will lead to gate 0, 1 by root 2 gate 0 minus 1 by root 2 gate 1. And that has a name minus state. So how to visualize this thing? So you can, when normally we talk about polarization, and you can consider that the gate 0 state is a horizontally polarized state, then gate 1 is orthogonal to it, which is vertically polarized. And then gate plus, which is 1 by root 2 gate 0 plus 1 by root 2 gate 1, is nothing but a 45-degree polarized photon. And then 1 by root 2 minus 1 by root 2 are the vector that corresponds to 135-degree polarized photon. So this can be single photons which are polarized in different angle. So, and Hadamard gate can be realized using a half-wave plate. Now, we are making a circuit. Suppose you have H, Z and H. So you put matrix of H, matrix of Z, matrix of H, and you multiply. The multiplication leads you to, you just after doing each step of the multiplication, I am getting 0, 1, 1, 0, which is X gate. So that means H, Z, H is equal to X. That's the circuit identity. So once I know the circuit identity, it often helps me to find other circuit identities. So for example, if you apply H in this side and H in this side, that is X, H, X, H, then this will mean that H is here, Z and H, H. Now H is a self-inverse gate. So if you can multiply H with H, H square is identity. So then H and H will cancel, so you will left with Z. So H, Z, H is X, and that can tell me that H, X, H is Z. So these are the identities which we often use. So you see, that's what we did here. I apply 2H, H square is identity, so they cancel, and then I get H, X, H is equal to Z. Now I introduce the other gate. The control NOT gate is 1, but if the control is 1, the target will flip, and if the control is 0, nothing will happen. So if my input state is 0, 0, it will go to 0, 0. If input state is 0, 1, it will go to 0, 1, because the control is 0. But 1, 0 will go to where? Tell me. In a control NOT gate, 1, 1 will go to where? I told you that if the control qubit is 0, nothing happens to target. If the control qubit is 1, target flips. So if my control qubit is 1 and target is 0, what will be the output?
One.
No, 1, 1. I tell that 0, 0 goes to 0, 0. So you will tell the output of both the qubit. That means the first control qubit will remain unchanged. The target will flip. So if I start from 1, 0, the control will remain 1 and the target will become 1. So then the output is 1, 1. 1, 0 will go to 1, 1. And 1, 1 will go to where?
Zero, zero.
No. Control will remain unchanged. So control is 1. So that's not going to change. So only target will change. So only target will flip. So if I start from 1, 1, then the output will be
1, 0.
Once again, try it.
1, 0.
1, 0, exactly. And now you see that what I told in the beginning, that map has to be bijective. You have 1, 0, true. So map has to be bijective. If I start from 0, 0, it will be 0, 0. If I do 0, 1, so 0, 0 goes to 0, 0, 0, 1 goes to 0, 1. There is no change. If the control is 0, nothing happens to the target. 1, 1 goes to 1, 0. So that's why the third line, 1, 0 goes to 1, 1. That's what's showing here the change. And 1, 1 goes to 1, 0. So this, the fourth element come to third element went to fourth. And this is a unique mapping. Looking at the output, you will be able to see what is input. So this is absolutely allowed in the classical world also. But now, if I write in the control qubit alpha ket 0 plus beta ket 1, then what happens? If the output qubit, so suppose the target is ket 0 and the input is control alpha ket 0 plus beta ket 1, then with mod alpha square probability, the state is alpha 0, 0, which remains unchanged. With mod beta square probability, the state is ket 1, 0, which become ket 1, 1. So the output state will become alpha ket 0, 0 plus beta ket 1, 1. And here is the magic. Now you cannot separate which one is the state of the first qubit, which one is the state of the second qubit. If the first qubit is 0, then the second is also 0, because that's the possibility, alpha 0, 0. If the first one is 1, then the second one is also 1. So this kind of state where you cannot separate the first subsystems from the second subsystem is called entangle. And entanglement has a lot of application. So we understand what is qubit, where from it comes, what are the physical realization. There are many physical realization. So one option is that to use it by optics. One option, like in optics also, we have talked about two options. One is the polarization. A 45-degree polarized state is superposed in 0 and 1, means horizontal and vertical. One option is that you have a beam splitter and reflected path is 0, transmitted path is 1. So a single photon is both reflected and transmitted unless you do a measurement. In superconductivity, with Josephson junction with certain states we use, so we can have many realization of qubit. But a qubit is essentially a two-level system. So you have to create two levels. So how can you do that? So here I give you some example. Many of you may be aware of quantum dot. So in quantum dot, it's just like a particle in box. So if you have solved particle in box, I mean, that's the simplest problem, you must have done it. You know that the energy levels are distributed as n square times certain constant and divided by L square. So if I reduce L, since it goes in n square, so the distance between the first and n is equal to 1 and n is equal to 2 is smaller than n is equal to 2 to n is equal to 3. And it is smaller than n is equal to 3 to n is equal to 4. Because it's going in n square. So the initial gap is E0, next time it will be 4 times E0, next time it will be 9 times E0 and so on. Because it's going in 2 square, 3 square and so on. Now if L is small, then the separation is even more smaller because L square is in the denominator. So a narrow quantum dot, these labels will be very wide separated. And if I take a radiation which takes from ground state to excited, fast excited state, will never take it from fast excited to second excited state. So if I work in this frequency range, I can forget about the third and fourth level and it will be an effective two-level system or a qubit. That's the quantum dot. Now, in harmonic oscillator, there is a problem. Harmonic oscillator, every qubit, every energy is separated by the same amount. So if you want to take it as a qubit, you will not be able to do. The pulse which will take you from 0 to 1 will take you from 1 to 2 also. And the pulse which will take you from 1 to 2 will take you from 2 to 3 also. So you will not be able to control. So what you have to do, if you want to make a qubit, you have to make an harmonic oscillator, because then the separation between the energy levels will be different. And if you want to make a multi-qubit system, each qubit must be different anharmonic oscillator. Otherwise, you want to excite qubit number 1, you will end up exciting qubit number 2 or qubit number 3 if their energy separation are same. So when you will make a quantum computer, whatever be the realization, they will have a kind of anharmonic oscillator geometry, and that's very important. Now, we were in quantum circuit, so you have already learned that if there are input states Ket0, Bra0, sorry, Ket0, Ket0, so this is the first qubit line, this is the second qubit line. You give 0 and a NOT gate. So what will be the state here? Tell me the question mark. So I told in the beginning that you have to work with me. So tell me what will be this question mark? So you are applying a NOT gate on 0 in the first qubit line. So after NOT gate, 0 will go where?
One, 0 only.
0, 1. First qubit will go to 1, and we have not done anything, so second qubit will remain in Ket0. So the input state here, which is the input for C0, is Ket10. And we know that if it is Ket10, then applying C0, since the control is 1, target is 0, the target will flip, and target will become 1. So the output will be 1, 1, and the measurement will, both the measurement will yield 1. So this is the application, this is the state here. You do the tensor product between this and you will get this, and then now this becomes the state. So this is your 1, 1, and the measurement will yield, both the measurement will yield 1. Now I change it. So I apply a Hadamard here, and then what happens? So this Hadamard will make it 0 plus 1 by root 2, or a plus state, and this is unchanged. And now with the half probability, this is 0, 0, 0, 0 will go to 0, 0, and with half probability, this 1, 0, which will take you to 1, 1. And this is the state which is called a Bell state, where you cannot separate between 0, 0, means you cannot identify, you cannot separate what was the first qubit state, what is the second qubit state. So this is called inseparable or entangled. Now if we do measurement, and in the first measurement is 0, the second one will also be 0. If the first one is 1, second one will also be 1. You will never get in this case 0, 1 or 1, 0. You will get either 0, 0 or 1, 1. So the property of this is entangled with this one. So even if these qubits are separated, one is in Earth and one is in Moon, I do a measurement on the first, I'll know what is going to be the outcome of measurement on the second. So Einstein was not happy with this. This circuit is called EPR, and Einstein introduced a problem called Einstein-Podolsky-Rosen problem, and he criticizes the situation that in quantum mechanics we are telling that unless you do a measurement, you don't know what is the outcome. So if there is a particle in Earth and another particle in Moon, and I do a measurement on Earth, and the particle in Moon know the state without being measured. And alternatively, the statement that it is measured has transferred faster than light to the particle in the Moon. But then the quantum mechanical realization is that the state is not local. State is neither located in Earth or Moon. It is non-local. The state is spread over, and we are measuring that statement, and you cannot actually do superluminal communication, because if I do a measurement on Alice and Alice got 0, say the first qubit, the second qubit which is with somebody in Moon who is Bob, and Bob does 0, Bob does not know whether it is because of the Alice's measurement or it is because of her measurement that it collapses to, or his measurement it collapses to 0. So you will not be able to distinguish between them unless somebody communicates that I have done measurement on Earth, and that communication cannot move faster than light. Anyway, so what is entangled? So this is the state which cannot be written as a tensor product of two states. So that's why it's called entangled. It's inseparable. Now we do something more. So I have a Hadamard gate, and then a NOT gate, and then C0, and you see what is the state. So this is how you have to do, and you will get gradually familiar with the state which you are getting. So we have NOT gate, which is like this. We have a C0 gate, which changes that input is 0, 0, output is 0, 0. Input is 0, 1, output is 0, 1. Input is 1, 0, output is 1, 1. Here is a change. Third goes to fourth. 1, 1 become 1, 0. And here is a Toffoli gate, which is 2 control. So first 6 qubit will go same places only when both of the first and second is 1. Then the third alternative, this 0 will become 1 and 1 will become 0. So here the flip is happening. So you see the change here, and everything else is diagonal. You can construct this matrix by writing the input output outer product. This can be realized using wave plate, and the same wave plate can be introduced. So this is half wave plate, and first axis is an angle theta. So this is optics, and you can choose the value of theta as 0, 45 degree or 22.5 degree, and you can find out that how to make Hadamard gate, how to make NOT gate, etc. But every optics is specific to a wavelength. So if I buy a half wave plate for 405 nanometer in my lab, it does not work for 810 nanometer. There is a unique gate called root NOT. So if I apply it twice, it works like a NOT gate. I will not repeat it. I will skip a bit of things. So circuit model of computation. So a computer is better if you require less number of steps. It can do fast. So which gate can be applied simultaneously? So this G1 and G2 can be applied simultaneously, even the G4, because output of one is not input of the other, but G3 has to be done separately. So this requires 2 time slices. So if the number of slices required is not polynomial, then we can do our polynomial, we can do the problem fast. So I can do it in fast. So there is a computational model and there is a circuit model. So if the number of steps required is less, is a polynomial, then we can solve the problem easily. Okay, so I'll skip some circuits. And now I tell you about, in tomorrow's lecture, CM Chandrasekhar from Math Science will tell you about IBM quantum computer and simulations, etc. So IBM quantum computer uses a gate library called Clifford plus T. So you can try today, means you can use your Google Mail and log in and try to simulate this kind of circuit. So this is a Toffoli gate, and this is not available in IBM. So if you want to apply this gate, so in IBM you need this many gates. So you have to decompose into the available gate libraries. So this is Hadamard, this is C0, this is X. These are the gates you know. You so far don't know T, and so that's a particular kind of fetch gate, and you don't know S. And this is called swap gate. So this changes A to B. If you start with a gate A, gate B input, it will become gate B, gate A in the output. So this particular things, HH, and in between a C0 gate is actually inverts a C0 gate. So this is equivalent to a C0 gate where the lower line is a control and the upper line is a target. But that's not allowed to be applied in IBM, so you have to apply 5 gates in place of that. Now, I want to tell you about the circuit, which Aditi will also speak. My next speaker will also speak. So I'll just talk about this, and it will be nice if you can practice it with me. And so this will help you to understand the next lecture. So teleportation is an example of a phenomenon which does not have any classical analog. So classical world, there is nothing like teleportation. So this is the term comes from an Isaac Asimov movie. So in an Isaac Asimov movie, there was that you disappear from your home and you recreated in your school. So here is initially this is the EPR circuit, that Hadamard followed by C0. So if you start with gate 0, initial state is gate 00. After Hadamard, the first qubit becomes 0 plus 1 by root 2 and second becomes 0. So this is the state. And now you apply C0 and you get the entangled state 0, 0 plus 1, 1 by root 2. So one of the qubit, the first one in this line is with Alice and the second one is with Bob. And Alice and Bob are separated. Now, a qubit is alpha ket 0 plus beta ket 1, which Alice wants to send to Bob. And you know that alpha beta can have any value because only restriction is that mod alpha square plus mod beta square is equal to 1. So if you want to send, alpha can be point to an irrational number which never ends. Then you have to make it. Alpha, you need infinite number of bits. But we want to send alpha and beta accurately every place. So what do I have to do? I apply the inverted teleportation circuit. So I apply C0 followed by Hadamard. So what is the state here? You had alpha 0 plus beta 1 in the first qubit, and then these are your second qubit and third qubit. So alpha 0 multiplied by this. So alpha 000 plus 0 1 1. So alpha, the one which was with alpha is in the first qubit, and 0 0 plus 1 1 is there. Beta ke sath 1 tha, so beta 1, then 0 0 plus and 1 1. So you have 4 terms, and then you apply a C0 gate. And in the C0 gate, the first one is, this one is control. So with the alpha, control qubit is 0, nothing will happen. With beta, control qubit is 1. So this arrow should have been before the Hadamard gate. So this will flip. So this beta will become 1 0, will become 1 1. So you see that this is the 1 1 term. And 1 1 will become 1 0. So this is the 1 0 term. So after that, you rearrange it in this way that this is 0 0, the third qubit, and you do a measurement. So if you get 0 0, the first two qubit, which is with Alice does a measurement, then you get 0 0, then the qubit of Bob will collapse to alpha ket 0 plus beta ket 1. So he does nothing. So the alpha ket 0 plus beta ket 1 is with Bob. If it is 0 1, then Bob applies a NOT gate, because Bob qubit is alpha 1 beta 0. So Bob applies a NOT gate, and 1 becomes 0, 0 become 1. He gets alpha 0 beta 1. So similarly, when it is 1 0, he applies Z gate. When it is 1 1, he applies IY gate. So application of this Pauli matrices create alpha ket 0 beta ket 1. So this state disappear from here and recreate here. So it's not like that you disappear and you recreate. So here was a qubit and here was a qubit. The information or wave function of this qubit disappear, and those information is gained by this qubit. So alpha beta is forgotten here and created here, and alpha beta is nowhere in the channel. So it's not like fax. In fax, you send a copy, and the copy is created in the other place, and you have your own copy. Unknown quantum states cannot be copied. If it could have been copied, then in one copy you should have measured position, in another copy you should have measured momentum, and Heisenberg's uncertainty principle would have been violated. That's called no cloning theorem. So you cannot make a copy. It is not like a letter. If you send a letter from Kanpur to Delhi, it will come through intermediate points. Say, from Kanpur, it will go to say Allahabad to Lucknow, Lucknow to Ghaziabad, and Ghaziabad to Delhi. So, but this is nowhere exists. It just disappeared. So the information disappear and recreates here. But it cannot be used for superluminal communication. Why it cannot be used for superluminal communication? Because unless the Alice classically tells that she has measured and got 0 1, 1 0, or 1 1, Bob does not know which unitary operator or which Pauli operation is to be applied to recreate this state. So, and this communication cannot be faster than light. So here are some other examples of state. So this is Bell state discrimination. So Chi plus, Chi minus, Phi plus, Phi minus, these are called Bell state. So these are entangled states, a set of entangled states, 2 qubit entangled states, which forms a basis. And we want to identify them without destroying. So this is a simple circuit, and now you know this is Hadamard, this is C0, etc. So this circuit was proposed by us some 20 years back or 15 years back. Later on, in a quantum computer, NMR-based quantum computer, this was realized by Professor Anil Kumar in IISc Bangalore. And when we don't have a quantum computer, and when IBM come and cloud, so we applied it in IBM. So IBM had a 5-qubit quantum computer, we applied it, and we had some circuit. So these are the real output. So this is one is with NMR, and NMR was used with a molecule. So how was his computer? The computer was a CH3Br molecule. So just like a chloroform, there was a molecule CH3Br, and we did it in 5-qubit quantum computer and got this result, which is analogous, but we find that the IBM quantum computer result is not that good. This result is better. So the bigger quantum computer is not always advantageous. How accurate it is, that's also important. It was a 5-qubit quantum computer. This is a result from a 3-qubit quantum computer. But the 3-qubit quantum computer, which was a CH3Br molecule, gave me a better result. So there is a measure called fidelity. The fidelity measures that how good is your copy. So input, you send a state, say you do teleportation, and instead of alpha ket 0, beta ket 1, you get alpha prime ket 0, beta prime ket 1. You can compare and find out how good is the copy. And these are some measures of fidelity. And you see that they are not 100%. So that means the gates introduce some error. And we have options for doing error correction. So that's what makes quantum computer possible. But to correct an error, you have to do a kind of encoding, and the qubit has to be encoded in many more qubits. So we don't have time to discuss error correction circuit. So this is the error correction circuit. But you can, now you learn the basics. You know what is Hadamard gate, what is C0, what is gate 0, what is gate 1, how you have to write them in matrix. If you log in IBM, you can drag and draw these gates and these circuits, and you can check that what is the output. And so actually what we do is we use a kind of majority voting technique. So for each 0, I create 3 zeros, and for each 1, I create 3 1. And then I see that majority of them are, after noise, majority of them are 0 or majority of them are 1 or not. So in quantum mechanics, there are two kind of error. One is bit flip, one is fetch flip. Okay. So this is the architecture of IBM quantum computer. But these are two architectures. So Professor Chandrasekhar will talk about in detail. So these are 5 qubit quantum computer, and then you can see that there are some arrows which are connected. So Q0 to Q1. So what this arrow means, I can apply a C0 gate, but Q0 will be control, Q1 will be target. I cannot do it other way. So when I have to do it in other way, then I have to apply this circuit that 2 Hadamard in the top line, 2 Hadamard in the bottom line, and then a C0 in between. So the C0 will be inverted. This white regions, they are denoting your qubits. They are, each of them can be visualized as an harmonic oscillator. But these are superconducting things. And tomorrow, Vijay will talk how he realized these things in the lab. And I mentioned that the energy loss is not a constant here, because we want to take quantum advantages, and energy required is a lot. So it's not like reversible circuit, because we have to cool it. And the superconductive quantum computer works in a very low temperature, and that requires something called dilution refrigerator, and the dilution refrigerator requires a lot of energy. So we are not interested in energy saving. We are interested in doing tasks faster than its classical counterpart, or to do tasks which cannot be done in the classical world. So this is the IBM quantum computer's architecture and what it means. So you see that both are 5 qubit quantum computer, but their architectures are slightly different. So if you have to draw circuits, I have to draw, and you see that this works in 0.21021 Kelvin. So this works, the quantum computer works at very low temperature, and these are different single qubit gates, and in addition, it can do C0 gates also. So we put in a 5 qubit quantum computer different gates and consider their fidelity for different possible states. And this has a name. This is called quantum process tomography. So when you do quantum process tomography, you see that the gates are not giving you unique fidelity. So each gate looks like very good, 9.9, 0.91. But when you have multiple gates, you are making a big circuit. Each of them are introducing error, and the error is cumulative. So after a few gates, the result will not be dependable. So the problem is that, the other problem is that the kind of quantum mechanics which is taught in your class is for closed system. So closed systems means when it has been taught that you are doing particle in a box, you are just doing particle in a box. Apart from the particle and box, there is nothing. But in reality, there is an environment, and it is interacting with the environment, and what I am doing as a measurement that it collapsed to one of the probable state. So it can, undesired collapse can also happen. So it can collapse to 0 or it can collapse to 1, your qubit. So you cannot make the qubit stay for long. So these are the problem. So it interacts and collapses. So this is called, and the state, your state ket xi become ket xi prime instead of remaining at ket xi. And this is called decoherence. Decoherence is the big problem. That's why we cannot make a very big quantum computer and perform all the tasks which it has promised. But gradually it is changing. So a few years back, there was a 5 qubit quantum computer was good, 8 qubit quantum computer is good. Now we have 50 qubit quantum computer, and the number of qubit is enhancing quickly. So this will help you to, especially the teleportation thing, will help you to understand the next lecture, and probably the gates and circuits which I mentioned will help you in the understand tomorrow's 2 lectures also. And a few ideas which I have told quickly, like bracket notation and Pauli operators, those will be further clarified in Professor Misra's lecture. So this is, in that sense, this is a bridge. And if you have any questions, I can take them now.
Sir, I don't see any question here in the chat box. So thank you very much for introducing us to this fascinating world of quantum computers, starting from Moore's law how quantum mechanical tunneling has come into picture as far as the devices is concerned, and how conventional gates are different from quantum gates, and how can we realize them, then how can we put those gates into a circuit and then ultimately to quantum computers. You have explained all these things basically, sir, in such a short duration of time in a very simple way. Thank you very much for the nice deliberation that you had with all of us. Thank you so much, sir. So, sir, we will end this session now, and we will wait for 5-10 minutes till Professor Aditi joins.
Okay.
Okay, welcome, ma'am. I am Dr. R.K. Dwivedi. Namaskar, madam.
Yes.
We will start at 3:45.
Okay.
Sir, shall we start with the proceedings? Okay. Professor Aditi Sinde is not visible. She is not visible. Okay, she has joined. Okay. Good evening, ma'am.
Good evening.
I welcome you all to the fourth lecture of the ongoing workshop on elements of quantum information. And we are fortunate enough to have with us Professor Aditi Sende from Harishchandra Research Institute, Prayagraj, and she is going to talk about the quantum communication. But before that, I'd like to share with you all a very brief introduction about Professor Day. She received her MSc in Applied Mathematics from Raja Bajar Science College, Kolkata in 1997 and PhD in Physics from University of Gdańsk, Poland in 2004 with Professor Marek Jukowski on thesis titled Manipulations of Quantum States and Their Non-Classical Applications. After her doctoral studies, she moved to Hanover, Germany as a Humboldt Research Fellow to work with Maciej Lewenstein at the Leibniz University. Thereafter, she joined ICFO, that is the Institute of Photonic Science at Barcelona, Spain, to continue her research on quantum information theory, condensed matter, and statistical physics. She won the prestigious Ramon y Cajal Research Fellowship during her time in Spain. She returned to India in 2008 and joined the School of Physical Sciences at JNU University before moving to Harishchandra Research Institute, Prayagraj, in 2009, where she is currently a professor in physics in Quantum Information and Computation Group. Professor Day has published more than 100 research articles in eminent peer-reviewed journals and has also collaborated with several world-renowned physicists. Her research interests includes quantum communication, detection, and quantification of quantum correlations, interface of many-body physics with quantum information science, etc. And she is the first female physicist to get the prestigious Shanti Sarup Bhatnagar Award of Science and Technology of Government of India for the year 2018. We welcome you, ma'am, on this platform. Welcome to the Christchurch College. And now this platform is all yours, ma'am.
Thank you. Thank you very much. First of all, I would like to thank the organizers for giving me this opportunity to speak here. So, I will share the screen.
Yeah, ma'am, you can share it.
I hope it is visible.
Yeah, ma'am. Yeah, it's visible, ma'am.
Okay, thank you. So I will talk about some recent trends in communication. In particular, I will talk about communication based on quantum mechanics. So in next 1 hour, I will try to convince you that if the present communication systems can be built by using quantum physics, we can get certain advantages, which is not possible to get by using classical protocols. So what do you mean by communications? What do you mean by classical protocol? All will be clear. I will be talking about that. So communication protocols can be broadly classified into two categories: communication without security and communication with security. So secure communication, which is also known as quantum cryptography or quantum key distribution, that is the communication protocol where information is stored or information is sent via in such a way that the receiver should have the key to open the lock. On the other hand, when we talk about communication without security, there is no issue of security here. So communication means information is only transferred in an efficient way from one place to another. And today in my talk, I will be mainly concentrated on communication without security. I think there is a talk on secure communication or quantum cryptography by Professor Anirban, Pathak. So communication without security also can be broadly classified into two categories. One is classical information transmission, another is quantum state transfer. So, in the first case, classical information is encoded in a quantum state, and quantum state transfer means sending quantum state from one place to another. So, I will mainly discuss about these two topics, and I will also explain what we mean by that. So, this is probably the first part of my talk. So, where I will talk about what is communication. And in both the protocols, the basic ingredients that we require is called something called entanglement. This is a property of a composite quantum system, which I will introduce and I will discuss, and I will show that with the use of by using these entangled states, one can enhance classical information transmission via quantum states, that is quantum dense coding. This is the first part that I will be talking about. So let's first discuss about what is communication. So I think in this audience, there is no need to emphasize the usefulness of communication devices. In this pandemic situations, probably every moment we realize the importance of communication devices, which help us to communicate between your friends, your relatives, and even to organize this kind of virtual conference. So the communication devices are extremely important, which include laptop and where we use internet to send emails, or the mobile phones, etc. Of course, there are also communication, there is a way to communicate between ourselves, like newspaper. So now probably we don't, most of us don't buy newspaper, but we actually read e-news, which are also helpful to obtain the information about about what is going on in the world. Of course, there are old communication devices that were also, now it's kind of obsolete, I should say. So television, radio, they also help us to get the information about the world. And so these are also communication devices. Post office actually is a very useful organizations which help us to also communicate different communicate informations from one place to another. So in any communication protocol that we are talking require at least two parties. Of course, there can be more parties, but let's concentrate on only two parties. Typically, they are called Alice and Bob. And also we assume when we talk about communication that they are situated in two distant locations. So, for example, one can be in Kolkata, Allahabad, Kanpur, Bangalore, and so on. And I call Alice as sender and Bob as the receiver. This can be old. Actually, I don't know whether you are aware of them, but they are famous artists, actors in Bengali cinema. So the Alice's task is to send some information to Bob. Now, this information can be classical as well as quantum. I will talk about both of them. Now, when we talk about classical information sending, that means, I mean that we want to send some bit to Bob. Bit is the basic unit in classical computer, which is one of the 0 or 1. On the other hand, when we talk about quantum, that means Alice wants to send some quantum state to Bob. Now, this can be a qubit, which is a basic unit of quantum computer, and this is quantum bit, in short qubit. This is an arbitrary two-dimensional quantum system. So these are the two tasks that I will be concentrating on. Now, any communication protocol typically has 3 steps. One is encoding. So where the informations will be encoded in a way. So for example, here I have done some encoding where Alice wants to send, say, the information that Alice is situated in Kolkata. instead of sending Kolkata, Alice could have sent this this word. Now it looks arbitrary, but it's not, because if you see that K I encoded to N and so on. So if you have I, J, K, L, M, and N, so 3 steps ahead, 3 alphabets ahead I have encoded. So there can be many encoding procedure that I can one can think. Now this is the first step, which is the encoding information that Alice wants to send. Then Alice will send via some medium. Now in current technology, typically we use optical fiber. If we think about the old way to send informations, can be a horse rider who actually take information from one king to another king. So in that sense, that horse rider was the sending thing. Similarly, you can think of post office, where actually post office, these organizations help us to send information from one place to another. So there can be many ways one can send information. Many medium can be used to send information. And finally, Bob gets the information, and Bob has to decode the information. So what do you mean by decoding? As I have told, instead of Kolkata, Alice could have sent some other alphabets, where I have done with the 3 alphabets ahead. So Bob should know or understand this the procedure that Bob has to actually understand that Alice wants to send this Kolkata. So this is the decoding procedure. So as I said, in communication protocol, in any communication protocol, typically there are 3 steps. 3 important steps are encoding, sending, and decoding. Now, since we are talking about encoding, and encoding will play an important role in all the communication protocol that I will discuss. So here just a very big, very important and quote from Landauer, where he said that information is physical. That means information must be encoded in and decoded from a physical system. So what do I mean by that? So what do I mean by encoding in a physical system? For example, in a classical world, encoding or decoding can be done by using colors of ball, or sign of a charge of a particle, or different wavelengths of waves or something. These can be used to encode information. And in the classical world, these all are distinguishable objects where we can encode information. Distinguishable objects mean in mathematically it's orthogonal states. So in classical world, encoding can only be done by using orthogonal states. But if we know in quantum physics, non-orthogonal states also exist. Of course, orthogonal states exist as well as non-orthogonal states exist in quantum world. So our aim is to see in this talk that whether by using this quantum physics, whether the encoding and decoding procedures can be enhanced so that the efficiency or the capacity of the communication protocols can be increased or can be enhanced. So before I start telling about the communication protocol, let us first discuss about briefly about some quantum property which is known as entanglement. If you are interested, this is a very nice review by Horodetzky. You can look. So again, when we define entanglement, we talk about 2 parties, Alice and Bob, situated in 2 distant locations, and like Kolkata and Allahabad. And suppose Alice prepares quantum mechanical state phi A in her lab, and Bob prepares phi B in his lab. So the joint state is in a tensor product Hilbert space, which is phi A tensor product phi B. So, in case of pure states, state is said to be unentangled or useless if Alice and Bob can prepare these states even when they are situated in 2 distant locations. So, for example, as I have told you, that one can prepare this 5-year tensor 5B even when Alice and Bob situated in two distant locations, two distant laboratories. So if I talk about a spin degrees of freedom, then Alice can prepare an up spin, and at the same time Bob can prepare another up spin. So they say spin half particle. So up spin of a spin half particle, this is up spin of a spin half particle. Similarly, up and down and so on. So this they are independently preparing, and they are not doing anything. So this is these states are unentangled or useless states. Now, why I am calling useless will be clear when I will discuss about the communication protocol. On the other hand, there are states which are entangled states, and I will show you they are very useful states. They give us some advantage over classical protocol. Now, these entangled states are those states which Alice and Bob cannot be or will not be able to prepare when they are situated in two distant locations. So mathematically, a state which is said to be entangled if it cannot be written in this tensor product form. A very important example of an entangled state is the singlet state. Probably you have learned this in the angular momentum chapter of quantum mechanics. So these zeros and one can be represented by, say, spin degrees of freedom, spin half, up spin, and down spin. Now, similarly, you can actually generalize, because the definition that I have given is for pure states. Now, for an arbitrary density matrix, you can generalize this definition. And but the main logic will be saying that to the useless or unentangled states are those states that Alice and Bob will be able to prepare even when they are situated in two distant locations. And entangled state, to prepare entangled state, they have to come in one place. So, for example, this is the definition of an entangled state, which is a mixed state. So it's a mixture of singlet and this, say, two up spin. Now, although the definition looks so simple, but here I just want to stress that given an arbitrary quantum state rho V, it is not easy to detect whether a state is entangled or not. And this is one of the main obstacle or one of the main important area or direction of void that is going on. So given an arbitrary quantum state, how to detect, how to confirm whether a state is entangled or not. And this is known as detection criteria, and that many people are working, including our group at HRI. Now, there are a lot of experimental progress in this respect. So, for example, if you talk about photonic system, then there are two kinds of polarization you can think of, whereas right-handed and left-handed circular polarization, they are ideal candidates for a qubit. And by using this photonic system, one can create an entangled state. Similarly, if you think of ion trap, then the internal levels of ion can serve as a qubit. And by creating an interaction between these two ions, for example, here you see the ion set trap. There are 7 ions set trap, and now by putting some interactions via laser, one can create an entangled state of these 7 ions. There are several other potential physical systems where entangled states can be prepared, like ultra-cold atom in optical lattice, NMR, nuclear magnetic resonance, semiconductor devices, and probably superconducting qubits, which are one of the potential or very now the one of the promising candidates for creating quantum computers. Now I come to the information transmission protocol, that is one of the communication protocols. So the task is to send some classical information to from Alice to Bob. Now suppose Alice wants to send the weather report to Bob, and Alice is situated in Kolkata, so Alice wants to send the today's temperature to Bob. Now there are several possibilities that the weather is sunny, it can be windy, it can be raining. Okay, snowing is not possible in Kolkata, but let's assume that is possible. So there are, suppose, the four possibilities. So that can, so in different time, Kolkata can have these four possibilities. Now, since there are four options, Alice wants to encode these four possibilities in four colors of ball. So if it is sunny, then it's a blue ball. If it is windy, then the gray. Raining is the green ball, and snowing is the yellow ball. So there are four options. That means log of 4 bits Alice wants to send, and that means 2 bits of classical information that Alice wants to send. So how to do that? Suppose Alice wakes up in the morning and finds that today it is windy. Then Alice will send the grey ball to Bob. And in another day, if Alice wakes up and finds that it is raining, which is actually very commonly happen in Kolkata, so Alice can send then the green ball to Bob. Now, as you see, that this sending can happen by any way. Suppose Alice puts this ball in a box and go to the post office and send it, or go to the courier office and send it. Now, Bob opens the box and finds, say, the green ball. Then Bob understands that it is raining in Kolkata. Remember, Bob is in a different city, say in Kanpur. If Bob opens and finds that the ball is yellow, then Bob is sure that it is snowing. Since these colors can be distinguished by our eyes, so they are the 4 orthogonal states we can talk about. So these are distinguishable objects. And so Bob can always decode the message. Of course, in the beginning of the protocol, they have fixed that this is the encoding procedure. That should be known to Alice and Bob before they start the protocol, because otherwise they don't know what is the encoding. So initially, Alice and Bob somehow will meet somewhere, and then they say, okay, Alice will tell that if it is sunny, I will send blue, snowing, yellow, windy, grey, and raining green balls. Now, after they decide this, they start the protocol. They went to 2 different cities and they start the protocol. And in these situations, Bob can decode the message. As you see, that to send these 2 bits of classical information, Alice requires 4 orthogonal states. That means 4 distinguishable objects. That means 4 dimensions. Now the question is, can quantum mechanics give any advantage? Indeed, it can. So this is how we will show. So before starting the protocol, suppose Alice and Bob a priori share a entangled state that I have already defined. Say, for example, this state. This is the singlet state. So where 0 can be a up spin of a spin-up particle, 1 can be a down spin of a spin-up particle. So Alice and Bob shared this state. Now, depending on the message, like if Alice is sunny, then Alice performs some unitary operations on her part of the system. Now, Alice is sunny, Alice will not do anything because this is the identity operator. If it is snowing, then Alice performs sigma z operator, windy sigma x, and raining sigma y, only on her part of the particle. Now, what do I mean? If identity Alice applies on her part, you see singlet remains singlet, because identity means nothing is applied at Alice's part. Interestingly, if Alice applies sigma z on her part, sigma z acting on 0 will give you 0. On the other hand, if it acts on 1, it will give you -1. That means this singlet state will go to one of the triplet states, that is 0, 1 plus 1, 0. Similarly, sigma x flips, so this will give you another triplet, and sigma y flips as well as give phase, and so it will give you this. So, depending on the unitary transformation Alice performs, Alice actually creates these 4 orthogonal states between them. So Alice and Bob creates these orthogonal states just by applying one of the unitary operator on her part. Depending on the message, Alice will perform this unitary operator. So shared state after encoding is this. Now Alice sends her particle to Bob. So we assume that here there is a mechanism by which Alice can send a quantum particle to Bob. So Bob has one of both the particles, and both the particles is either in psi minus state or psi plus state or phi minus state or phi plus state. So classically, if you remember, they were the balls of blue, gray, yellow, and green. Similarly, here they are these orthogonal quantum mechanical states, singlet and triplets. Now, since they are orthogonal, Bob can always perform a measurement by which Bob can distinguish them. And this is the decoding step. And so Bob can decode the message. So if Bob gets psi minus, Bob is sure that sure that Alice's weather is sunny. If Bob gets phi plus, then Bob is sure that Alice today in Kolkata it is raining, and so on. But interestingly, here note that to send these 2 bits of information, Alice only requires a part of a singlet state. Alice only performs encoding in 2-dimensional Hilbert space. That is this 2-dimension, which is the part of a singlet. So this is the model of the entire protocol, that the task was to send an arbitrary, send 2 bits to Bob. So classically, Alice requires 4-dimension or 4 distinguishable objects. And so it requires, encoding requires 4-dimension. On the other hand, in quantum case, Alice also sends 4 orthogonal states, but only encoding Alice does in 2-dimension, that is on hard part of her particle. So here this is happening because Alice and Bob a priori share an entangled state, that is the singlet state. So this is a good news. This is the real situation is much more different, because real situation they cannot share an exactly singlet state, but it will be a noisy state. So it is known that what will be the capacity, dense coding capacity of a noisy scenario. There are different noise can happen or decoherence can happen while sending, while decoding, or in different process, because as I said, communication is divided into 3 parts. One is encoding, sending, and decoding. So the noisy scenario or noise can come into the picture when initially Alice Bob shared the state, the entangled state, which was singlet state. Instead of singlet, it can be a noisy state. After encoding, when Alice was sending her part to Bob, there can be a noise. And these are the all questions that people have addressed already, at least in this 2-party scenario. When there will be many parties, things become much more complicated. Some results are known and some results are unknown. So some of the results were actually done by us long back and also with my student, but I'm not presenting that. Here, just to tell you that this dense coding protocol not only is just a theoretical protocol, it was proposed in 1992, 1996 by Anton Zeilinger group in Vienna. They have done the experimental demonstration of dense coding protocol. There are many other experimental demonstration, but here I just emphasize the first one, which was done in 1996. So summarizing, if I summarize up to now, so I hope that I am able to convey this message that communication devices are useful. Probably in this pandemic, this is of course we all realized in our life, in our daily work. Also, I introduce something called entangled state, and I show you that entangled states are also useful for transmitting classical information. That means to successfully do quantum dense coding. And I have also shown that the quantum mechanics help to reduce the dimension of encoding process, or to simplify the, or not simplify, but to the encoding dimension. So it actually gives you higher efficiency. Now, in the second part, I will talk about quantum state transfer. So in this part, the outline will be, as I said, the task is to send an arbitrary quantum state from Alice to Bob. I will first discuss a classical protocol. That means when the entangled states are not shared. And when I discuss that when entangled states are shared, then what will be, how we can transfer quantum state from one place to another, known as quantum teleportation. I will also discuss two important points related to quantum teleportation, that is signaling and no-cloning phenomenon. Okay. So again, the communication, Alice and Bob, they are two parties situated in two distant locations. And sender, Alice, wants to send some information to Bob. In this case, Alice wants to send an arbitrary quantum state to Bob. This is known as quantum teleportation, introduced by these 6 people in 1993. This is Bennett, Perez, Utters, Jotsa, Brassard, and this is Crepio, and this is Jotsa and Brassard. So, sending arbitrary quantum state on an arbitrary quantum state can be represented by that mathematically. So again, 0 can be a up spin of a spin-up particle, 1 can be a down spin of a spin-up particle. And alpha, beta are an arbitrary complex number, and we have to normalize any quantum state. So mod alpha square plus mod beta square equal to 1. So this is an arbitrary 2-dimensional quantum system, and this is the qubit. Now, geometrically, it can be represented in the sphere of a block sphere. Now, if the poles are represented by 0 and 1, so north pole is 0 and the south pole is 1, then the surface of the sphere actually represents all the this qubit states. Now, if I geometrically I think qubit like that, so you can see that if Alice wants to send an arbitrary quantum state to Bob, then actually Alice requires infinite amount of classical communication, that is infinite number of bits, because the surface of the sphere has infinite number of points. And so for each point you require 1 bit, each point you require 1 number, and in that way you actually require infinite numbers. So this is the classical device where infinite amount of classical communications or bit is required to encode any point of the surface of the block sphere, and this is the task. Let us now see if we can get any advantage when we move to a quantum device. So the scenario is the following. Alice wants to send this alpha 0 plus beta 1, where alpha beta are unknown, and Alice wants to send this to Bob. One possibility is that Alice creates this state, send it physically. That means put it in a box, which actually can keep the quantum mechanical state, and send it to Bob, say via courier. But this is not allowed. This physically you put it in a box and transferring, this is not allowed. So what is the way out? Again, suppose that Alice and Bob a priori share an entangled state, that is a singlet state. Then
the next step, so this is the joint state mathematically look like if alpha 0 plus beta 1 is in position with Alice and one of the particle of singlet is also with Alice. So this part, and this part will be with Alice. Now Alice performs a measurement on in and A. So two particles that she possessed. And measurement will be performed in this maximally entangled basis known as Bell basis that I have already discussed. This is this composite system, so singlet and triplet. Now, these are the entangled measurements. Now, suppose, because this is a quantum mechanical measurement, as you know, one of the measurement direction will click. As you probably have seen in your class, the single particle measurement, when you perform measurement in up direction or down directions, one of them click, and you can find out the probability of clicking and so on. So suppose psi minus clicks, and that means how to find out what will be the output state. So this is my joint state, and I sandwich this state from psi minus, from left. And psi minus is 0, 1 minus 1, 0. So the contributions will come only from these two terms. And if you take this inner product, then you will find that the Bob state will be alpha 0 plus beta 1. If psi plus click, again the contributions will be from these middle two terms, and the output state at Bob's side will be alpha 0 minus beta 1. If phi minus click, then the contribution is from first and last state, if you make a inner product, and the Bob state will be alpha 1 plus beta 0. Similarly, phi plus clicks, it will be alpha 1 minus beta 0. So there are 4 options in the measurement basis: psi minus, psi plus, phi minus, phi plus. One of them can click. Now that means these 4 options means it has log of 2 base 4 bits. That means 2 bits. So Alice now classically communicates her measurement outcome to Bob. So Alice makes a phone call and tells, okay, 5 plus clicks. So this is 2 bits of classical communication. Depending on the outcome, Bob performs unitary on his part. So for example, if Alice calls and tells Bob that, okay, psi minus, I got psi minus, then Bob will not do anything. Bob will, because the exact state will be alpha 0 plus beta 1. If Alice calls and tells, okay, I got psi plus, then Bob's state is this. So this is alpha 0 minus beta 1. And this is different than the original state that Alice wants to send. So depending on the classical information that Alice sent, Bob performs one of the unitary operator. That means in this situation, Bob performs sigma z on this state. Now alpha 0 plus beta 1, if the sigma z you operate, as I have told you, sigma z when acts on 0 gives you 0. When acts on 1, it will give you minus 1. So this will be plus, and so the original state can be recovered. Now suppose 5 plus click. Then Alice communicates to Bob. Alice calls and tells Bob that 5 plus. That means Alice say Bob's state is this. In this scenario, Bob performs sigma y and recover the state alpha 0 plus beta 1. So what we have shown you that if there is a shared quantum mechanical state, that is a priori, if Alice and Bob share an entangled state, then 2 bits of classical communication is enough to send an arbitrary quantum state to Bob. On the other hand, if there is no shared entanglement between Alice and Bob, then classically, or in case of unentangled or state shared between Alice and Bob, then Alice required infinite amount of classical communication or infinite number of bits to encode an arbitrary quantum state, to send an arbitrary quantum state to Bob. So we show that quantum mechanics help to enhance the efficiency while sending arbitrary quantum state to Bob. And this is the protocol known as quantum teleportation protocol, which was introduced by these 6 people in 1993. Now here there are 2 points. One is that whether really in this teleportation protocol, whether we have communicated faster than light communication. That means here the entire protocol is discussed in the non-relativistic sense. So even then, are we breaking the relativity, that is faster than light communication? It's not. After Alice's measurement, but before Alice's communication, the Bob state can be calculated, which is an equal mixture of these states, which is actually the identity operator. That means before protocol, Bob has no information about the input state that Alice wants to send. So this actually shows that there is no faster than light communication from Alice to Bob. Now, whether this is a violation of no cloning theorem. Now, no cloning theorem tells us that arbitrary state cannot be cloned in quantum mechanics. So here, are we copying? Are we have 2 copies of in or this input state that Alice wants to send? Because the no cloning theorem prohibits for arbitrary quantum state to be cloned or copied. So no quantum Xerox machine exists in the quantum world. So the answer is in the teleportation protocol, no violation of cloning theorem happens. Because when Bob has the input state, Alice doesn't have the input state, because as you remember that Alice performs a measurement, entangled measurement on her part of the entangled state and the input state that Alice wants to send. And after the measurement, this state collapsed to one of the entangled, one of the triplet or singlet. So this input and A after the measurement is either in side minus or side plus or phi minus or phi plus. And so there is no violation of cloning theorem. So when Bob has the input state, Alice does not have the input state. So these 2 are very important points in quantum teleportation. Again, the question is whether this is a theory. It's not. There are a lot of experiments on quantum teleportation. So there is an experiment where the 2 islands in Spain, in this upper tip of Africa, where La Palma and Tenerife is 143 kilometers away, where they have performed teleportation experiment again by Anton Zeilinger group. So it just shows us that there can be a teleportation experiment between, say, Allahabad and Varanasi. This is a bit difficult to have a teleportation experiment between Allahabad and Kanpur because it's 200 kilometers away. So in 2016, it was impossible to perform a teleportation experiment between Allahabad and Kolkata or Kanpur and Kolkata. But there is a breakthrough experiment in 2017-18 where it was by using a satellite, it was shown that it can be, the quantum communications can be, or entangled states can be shared between 2 cities which are 1200 kilometers away. This was by Professor Pan's group in China. So now it is possible to have a teleportation experiment not only between Allahabad and Kanpur, but between Kanpur and Kolkata. So this is a big achievement in the quantum communication theory, which shows that entangled states can be created in almost 1,000 kilometers far apart two cities. It can also be created. You can perform teleportation and other experiments in 1,000 kilometers in two cities which are 1,000 kilometers apart. Now people are trying to do such quantum communication experiment in two continents. Not only in the photonic system, but there is a ion trap, which I have already discussed. The people have done the experiment also. So there is an experiment in the Christoph Munro's group in US where they're able to teleport information between atomic quantum memory separated about 1 meter. So when there is a massive particle, then it is a bit difficult to have a long distance communication, but they are able to do it in a small distance. Now, even the small distance communication protocols are important because, say, if we want to build a quantum computer, then inside the computer, we may require information transmission from one node to another, which can be 1 meter away, and there, or even less than 1 meter away, and there we actually require this kind of these protocols or these implementations are important. And we know that probably two potential candidates for quantum computations now is ion traps and superconducting qubits. So any experiment, teleportation, and this kind of experiments can be important also to build quantum computers. There is also a new record. It was set for quantum teleportations with matter qubit. In the most of the demonstrations of quantum teleportation between remote atomic qubit, the atoms exist in free space. Now, in this new study where they discovered that trapping the atoms in optical cavities can overcome some of the previous obstacles, and then they actually, so as I have shown you that here the teleportation experiment in 2009 where it is 1 meter. Now they can go ahead and they can have a record-breaking distance of 21 meters, so which is pretty good, and this was one of the new records. Now, probably you can think that, okay, the final goal is to build not only the communication between two parties, because any kind of communication, when we are talking about, then we want to build a communication or we want to send information to many parties. Just like this virtual conference where we all are connected via internet, and so each of us can be called as node, and there is a internet network which actually connect us, and so that I can give this talk and you can listen, you can ask questions and so on. So final goal is to build a quantum network or quantum internet. That means we, as I have shown you, that entangled state is a useful resource to achieve the enhancement in quantum communication protocol. And so now one of the main challenge is to share entanglement over large distance. Typically now, if we have a large distance sharing, then the entire path can be divided into smaller parts, and then you perform measurement in between so that sender and receiver can share an entangled state. This actually known as quantum repeater problem. If all of them share a maximally entangled state, then one can show that there always exists a measurement protocol by which sender and receiver can share a maximally entangled state. But in a real experiment, this will not happen. So these all will be a noisy entangled state. And so it will be interesting to find what will be the critical noise value above which the protocol will be successful. Protocol can give us some quantum advantage. And this is the direction that we are working on. And several people several groups around the world are working. So in our recent publications, actually published in December, where we have considered different kinds of networks. So here it's a one-dimensional quantum network, and our aim is to connect, say, these yellow nodes. So we propose a protocol by which the entanglement, highly entangled state can be shared between these yellow nodes. Similarly, we actually also can generalize this network to two-dimensional quantum network. So you can think that these are the yellow nodes or the pre-decided nodes. We want to share some entangled state. After establishing entanglement, we can perform some communication protocol. So this we have proposed. So we found that when these states are noisy, then what will be the critical value of noise is allowed so that the final state is entangled, or final state has some non-local correlations which can be detected by certain method. And I'm not going to discuss, but if you are interested, you can look into our paper. And in that direction, there are several quantum communication networks where we extensively work on this problem. And if you're interested, then you can look. So the dense coding protocol that I have discussed, again, was between just a single sender and single receiver. So in these papers, we have, so in all these papers that I have listed here, we have shown that how one can send an arbitrary, one can send classical information by using quantum states in the classical informations can be sent to a different senders and receiver. Here I just wanted to mention, although it looks so simple, but it's not, because if we have arbitrary number of senders in dense coding protocol and a single receiver, this scenario is completely solved. So, for example, you can think that suppose there are news reporters who are trying to send information to the newspaper office. This means that reporters are senders and send their report to the editor of the newspaper. Then this is just a single person. So this is a scenario which we know a lot of informations, which we know what is the capacity, what is the optimal entangled state that they share so that the quantum advantage can be obtained. But suppose there are two editors where the sender wants to send information. And this is the scenario also is known partially, as you see in this paper. But if you have more than two receivers, this problem is still unsolved, and there are a lot of open questions and which still I don't know how to answer. And we are trying in our group to overcome those difficulties, but still question is open. So summarizing, I discuss about the quantum dense coding protocol, where I have shown you that when we want to send classical information, then via quantum states are giving us advantage over the classical protocols. When the shared state is not entangled, then the transfer requires more dimension. I have shown the infinite resource reductions when we talk about quantum state transfer. So when Alice wants to send an arbitrary quantum state to Bob, I have shown you that if they a priori share an entangled state, then we only require 2 bits of classical communication instead of infinite bit requests when Alice and Bob doesn't share an entangled state. So this is a infinite resource reduction. I have shown you that these are not only theoretical proposals, but there are experimental implementations, especially with by using photonic qubits, as well as by massive particles like ion trap and other. Finally, I give you a flavor that, okay, communication protocols are typically discussed when initially proposed. It was discussed for 2 parties. But now probably around the world, several groups are trying to build a communication network, or we are heading towards quantum internet, where our aim or our goal is to connect several senders and several receivers, where quantum state or classical informations will be transferred. Now here, all the protocols that I have described, the encoding part is done in such a way there is no security issue. That means encoding part, there is no lock, that Alice has not locked or Alice has not encoded the information so that the third party cannot gather information. Only the Bob can gather information. So this part I haven't at all discussed. I think Anirban and Professor Pathak will discuss. So this is the scenario where there is a requirement of cryptography, which has a much another facets of issues. And so there we will only discuss about in cryptography, the main task is to discuss or to describe classical information transfer, and where we use quantum states, and one can show certain advantage due to the existence of non-orthogonal states as well as entangled states. And so with this, I just wanted to, some of the results that I have presented is with my group. So this is my current PhD students who are working with me. And also I work extensively with the postdocs. None of them are now postdocs in our group, because Amit is a faculty in IIT Palakkad, Shiladito moved to abroad for postdoc and so on. But still we are working, and many works that I have presented or I have shown you or discussed are done by them. This is the entire QIC, Quantum Information and Computation group at HRI. So we have around 15 PhD students and 4 postdocs and 3 faculty members. And so Kanpur is close by. It's kind of good that even in this scenario, we can have a discussion, and I can discuss, but I hope that given an opportunity, I will like to visit your college, and you can also visit us. So thank you very much for your attention.
Thank you, ma'am. Thank you for this very relevant information about the quantum communication. And in fact, you have talked about the communication without security, and that about the quantum dense coding. And what I found very fascinating is the distinction between the classical protocol and the quantum protocol, how that quantum mechanics ease the things for us. And of course, the entanglement is there. Entanglement states can be created for over a distance of 1,000 kilometers on one hand. On the other hand, you have the teleportation of quantum information between atomic quantum memories separated by about 1 meter. So these are two very interesting facts. And in fact, the superconducting qubits, hopefully we are going to know about this in the tomorrow lecture. So this is something very unique for me also, because in MSc final I am dealing with the digital communication. And in digital communication, what we do, we first the sampling of the signal is there. And then for the secure transportation, we use the quantizing of the signal. But of course, this quantum, if this quantum communication, if we can build a quantum internet, then this communication will be much, much secure for the digital world, which is going to be have with us in the near future. Thank you, ma'am, so much for the information you have shared with us on this platform. And in the chat box, I have seen one question, ma'am. Can I take that question, ma'am, for you?
Yeah, sure.
Ma'am, one of our students, she has asked, what are the skills tools that a student interested in quantum information and computation is expected to equip with? Are there any prerequisites recommended? She is the MSc previous student of our college.
Okay.
So she is very much interested in this one.
So there are two questions actually I can see. One is by Shruti and Himanshu.
Shruti, both our students, ma'am.
Okay, can I answer one by one?
Sure, ma'am, sure.
Yeah, so first of all, the prerequisite is just to read quantum mechanics book. So I think the Griffiths book usually many colleges, universities follow for BSc and later in MSc. And the measurement and this pure mixed state that probably you also learn in statistical mechanics course. Because when we talk about thermal state, then that they are all mixed state. So pure and mixed states, if you want to learn, I will suggest, especially the MSc students, to go through Sakurai book, and that's really good. And all the measurements that I have shown you, you can very nicely see in the Sakurai book, because the Sakurai book starts with the experiment of Stern-Gerlach, which actually shows you that how the information is going when you perform measurement in different, that also of course in a single particle, but single quantum state, but that actually gives you the basis of what I am doing. And also the angular momentum chapter will give you the hunch of this, I think the two particle, the entangled state that I talked of. I am sure that in advanced quantum mechanics course in MSc, you have learned clear all this addition of angular momentum, where of course you have to you introduce what is singlet state and triplet state, and so these are the prerequisites. So any book where you can know, and mainly the part that I am focused on in the axiomatic definitions of quantum mechanics, which actually is the modern quantum mechanics. And so Sakurai has nicely. So I will suggest that, of course, the Griffiths and Sakurai is the prerequisite, nothing else. And then slowly you have to start calculating. And all the things that I have discussed is also, you can find Preskill lecture note in the website, which is Preskill is a Caltech faculty. So he has a nice lecture note, which is a bit old. When I started my research, I actually, that time this is a famous quantum information book is Nielsen and Chuang. Many people know that. But in my time, there was no Nielsen and Chuang. So we started learning from Preskill lecture note. I still suggest all my students to read. Moreover, if you are interested on quantum information, usually we have a basic, since you are in Kanpur, one can take some advantage. So one thing, HRI actually offered 2 quantum information and computation courses for the MSc students. So there can be a possibility if some students are interested, whether they can learn somehow. In virtual mode, it is possible even to join. That's a good part of the virtual mode. But so this is one thing. So this is the prerequisite part. Then there is a question, what kind of computer language we should learn before entering this field? Okay, that depends, because for example, I haven't at all touched that is when we talk about this communication protocol or in computations, I also work on the field where we talk about the implementation of these protocols. Probably, so I am a theoretical physicist. Implementation means I write down something and implement. I give a implementation protocol. So in that sense, for example, if you want to work, there are a lot of work in our group we do, where we use quantum spin chain or many body systems, which you also learn in, I think, solid state physics class, where it is a Ising model or quantum Ising model and so on. There you can also learn that how to diagonalize and so on. And these can be used to transport the communication protocol that I have described. So there are a lot of work going on at the interface. And if you are doing, it depends on which language you learn, because typically if you talk about numerical language, then I will say that Fortran or C++ is good to learn, where most of the colleges, universities actually teach Fortran and C++. C++ is a new subject, so what I understand from my student, that has lot of library which are developing, so people usually get. So Fortran 90 and C++ is good.
Ma'am, can we use Python or MATLAB for it?
Yeah, you can use, pretty good. Actually, the point is that depends on what you want to do. Python is very good now. I mean, as a new language. MATLAB is also good. But sometimes, when I am thinking, if you are working, the result that I have presented, what I call the quantum communication, if you just want to do with states, etc., then they are good. But if we want to work on many-body physics implementation of communication protocol or computation, then, as you know, probably from your condensed matter basic course, that you actually require a large number of diagonalization, etc. And for that, you require C++. Python is usually a bit slow. But otherwise, Python is pretty good. MATLAB is as well.
Yes, ma'am. Okay, ma'am. Really, your talk was very nice, very informative, ma'am. Thank you so much for enlightening us.
Thank you. I mean, I am really happy that I am connected, and we are close by, but unless there is a connection, but we don't know each other. Now we know each other. We hope there will be more communication, and I'll be really happy if I can go and communicate. I mean, I'd love to do that, but.
Yes, ma'am. Is there any pathway to connect this particle physics with quantum computing?
Oh, very good question, actually. I mean, now, okay, I have a very little knowledge about that. So I am really not up to the mark of that kind of communication. But I can say as as an outsider, I can comment, because I see a lot of archive paper. I'm trying to learn, but I'm very slow in learning. So there are these neutrino oscillations where people are able to connect something they find about multipartite entanglement and so on. So there are different flavors of neutrinos. Recently, there are papers where people are able to calculate that their entanglement and so on. But I really don't know into details. Okay. But there are people trying to
yes, ma'am.
connect.
Yes, ma'am.
So look at archive. I think it's
yes, ma'am. Yes, ma'am. Okay. Thank you so much, ma'am.
Thank you, ma'am, for answering.
Oh, there is another question. Maybe if you have time, I can answer.
Yeah, we have the time, ma'am.
Okay. So I probably finish a bit early, right? Okay, so how much entanglement is used nowadays? This is where Shruti Dubey is used nowadays in world and through space. When was it first started? Okay, so how much means if you are here, can you tell me what do you mean? I mean, quantity wise, you are saying. Are you here, Shruti? Then can you?
Shruti, I think she's not there. How much quantum entanglement is used nowadays in the? Practically, what is the percentage of using?
Yeah. So what I wanted to say that, as I said, I always demonstrate everything to show the advantage. I always demonstrate that the shared state is singlet state. But never, when you do an experiment, experimentalists will never be able to create exact singlet state. They will get a mixed state, which will have some fidelity with singlet. So typically, when they started, the fidelity was low. But now for a two particle, as far as I know, experimentalists can correct me, but it can be more than 99%. So they are almost close to the singlets.
Ma'am, there is one question from that is any measurement technique for quantum communication, quantum computers, especially in interference-based devices.
Interface-based.
Interface-based devices. Interference-based devices.
No, he has written in the next line, it should be interface. He's written.
Okay, that is interface-based devices. Yeah.
Okay. So, measurement is any measurement technique for quantum communication, especially in interface-based devices. Okay, that's, I mean, these things are developing in some sense. I mean, interface-based, if you mean that there are different kind of, but, of course, that should follow the basic quantum mechanical postulates. So that means Bond's rule, which we learn in our class. So the probability when you have psi, if I perform a measurement in the basis phi I, then the probability will be phi I psi modular square. This is always true, whatever device you perform. So, there can be a general measurement also, something called the measurement that I have talked of. Okay, so you go to, so the point is that probably you were talking about the measurement in an experimental sense, because 3D, 5D heterostructure. So I mean, that I cannot tell. I mean, I guess that maybe with a laser or something they do, but this I don't know the details.
Okay, thank you, ma'am. Thank you very much for being with us. We have shared much information with you and gained a lot from you. So thank you very much, ma'am.
Ma'am, in fact, I also want to ask you a question.
Yeah, sure.
There are many students in our college which are getting Inspire Fellowship. So it would be possible for you to basically just guide one or two students online so that they can learn some new things on quantum communication and make use of this Inspire Fellowship.
This summer you were saying?
Yeah, summer, yeah.
Okay. Yeah, it is possible. They can write. I usually take one or two summer meetings, but nowadays it's not possible, as you know, because of this pandemic. So actually, yes, they can join, of course. I am a bit tight because of lot of responsibilities. Not only science, but I have lot of administrative job that I have to do also. So. And also I have a lot of project students whom and I am teaching also. So, but summer maybe because this time I don't know here the MSc starts in January, so there are 3 semesters. So we really don't have any gap because and there are many shifts because PhD has started in September. So I am kind of teaching 2 courses I have to teach. So this way, but yes, if they get some time in May, June, maybe I am a bit free. So then I can surely.
Okay, ma'am. Thank you so much. So if I will get some good students, I can basically refer it to you.
Okay, thank you, ma'am. So with this, we come to the last session of the day 1 of the workshop on elements of quantum information. So from tomorrow, we will start the session at 10 a.m. Till then, take care and bye, everyone.
Bye.